Testing, testing. Okay.
Hello. All right. So thank you for your patience with my lack of coffee. Okay. So as I was saying, thank you all for showing up for the InnodeMC edition 13 or 14, or I can't remember what. Once again, thank you all to our sponsors, without which this event would not be possible. I am sort of starting to talk like 2 minutes before schedule, just so Alessandro gets his full 15 minutes. If you've been to those InnodeMCs before, you know that we tend to be relatively brutal about the timing. So you do have 10 minutes to talk, 5 minutes for discussion, at least. You can open it up before if you want, but at the 10-minute mark, we kind of will force you to talk. The idea is just, of course, to have as much back and forth conversation as possible. We do understand that, this is one of the key events where folks from Google sort of get the chance to share what they've been working on. So kind of unlike many other MCs, there's a bit more presentation style stuff, and we kind of understand that, and we'll make do. But if you can keep that in conversation format as much as possible, that would be perfect. All right. Did I mention anything, John? Sorry? Code of conduct. Yes, there is a code of conduct. Please do refer to it. That would be great. Whatever. We're assuming you're decent human beings, but if you need a fine print, there is some fine print for you. Okay. Without further ado, Alessandro, if you want to sort of grab the podium.
Hello, everyone. So let me first introduce myself. My name is Dmitry. I work at Android bootloader team and Android Calfish team. And today I'm going to tell you about the current status of the Android boot flow and what the future plans we have and what we're currently working in. I'm giving this talk in the context of the GBL, which I introduced last year here at Plumbus. So the main idea of the GBL is it's a Google initiative to provide the Android bootflow UEFI application to be reused by all the Android devices booted at the market right now. So the main goal is to reduce the vendor integration burden. So we really hope that integrating GBL should be easier than re-implementing the whole Android boot flow, because that's the current situation. And also ensure we can change the Android boot flow to support like new features, which is happening quite regularly. For example, like boot config adoption or protected virtual machine firmware loading, and ensure better security, performance, and alignment with the rest of the ecosystem. To better understand the problems we are trying to solve, here on the slide you can see I'm going to give you a quick recap about the Android bootflow. So here on the slide you can see the partitions, the typical partition set for the Android device. For this talk, we mostly care about the boot partitions, which are responsible for delivering the boot artifacts, such as device trees, kernels, boot config, RAM disks, etc. So let me quickly go through the partitions we currently have. So VB meta is a central verification metadata. So it's responsible for providing the verification metadata such as public key, rollback protection, and also have a signature and self-hash. So once we load the VB meta itself, we also verify the actual header before we go to verify the actual partitions. To verify the partitions and also to provide some other metadata, we have a descriptors list structure. But during the Android boot, we mostly care about the hash descriptors, which provides a hash for each individual partition. So once we load it, we can verify it against this hash to make sure that everything is fine with the integrity. Also, we have Google-provided partitions that's supposed to be generic across all the devices. So they all share the custom C structure. So we use a boot partition to provide the GKI, basically kernel and command line. Also initboot to provide the generic RAM disks, and PVMFV structure to provide the protected virtual machine firmware. So basically the first code which is getting executed once we start the protected virtual machine. Also, we have a vendor-specific partitions, such as vendor boot. So again, we have like a custom Android-specific structure to allow vendors to provide the vendor-specific command line, boot config, multiple RAM disk to be selected based on the device board we are booting it, and the boot target. For example, for recovery, we may pick the different RAM disk, and also multiple device trees to be selected during the Android boot as well. So like the same set of the artifacts can be shared across multiple devices. Also, to provide we can provide the multiple device tree overlays to be applied during the Android boot, and for this we use a DT table structure. So it's again the custom header to provide multiple device tree payloads and some associated metadata, which is ID and revision field, to do the selection at runtime. But we currently have the problems with all the approaches. So first of all, it's too Android specific. So we have to introduce this header, update, provide the new versions, and make sure the entire ecosystem migrate to the new ones. For example, we already know, and we also use a partition table to represent the development flow and ownership of the artifacts, and changing the partition table, especially if the device is already on the field, is really challenging. Also, we have some limitations around the component selection, such as device tree selection and RAM disk selection. So DT table structure doesn't provide a lot of metadata, so it's just two integer fields to do the selection, which is not usually enough. And we already see a lot of cases when the vendors actually checking the internals of the device tree, some properties such as like SOC ID, board ID to do the selection, which is not ideal. Also, another problem, which is related to the previous one, is DT table doesn't support the offsets, the alignment. So if we need to do the device tree selection, we need to relocate each individual device tree into the 8 bytes aligned address, and it's not guaranteed by the DT table structure anyhow. And also we have AVB verification problems, because if you we currently have to verify all the artifacts, even if they are not getting selected. So, and taking some of the vendor boot partitions can take like 150 megabytes. That's something we see on the market. So we have to verify the huge partition and then use like 1% of it. So, and To solve this problem, we found out that like, there is a standard and some also internal conversations going on around like FIT. So FIT is a flattened image tree, device tree based structure to provide boot artifacts. So it's proposed in 2008 by U-Boot, published under Apache 2 and used by Chrome OS. So FIT image is usually a regular device tree, but with some predefined node. So first of all, you may see on the right side of the slide, we have like an images node where each subnode represent some boot artifact to be selected and used. And also we have it has a configuration node, which each individual subnode of it represents the actual probably board or like the entire configuration that's supposed to be selected and used. So let me share how it's supposed to work. For example, on the left side of the slide, you can see the example of the configuration node. So it has a compatible string, which is stringly structure in device tree, which doesn't have any limitations on size. Besides, like it's probably 4 gigs, which is more than enough to do the selection. And also it points to each individual image. For example, during the selection, we're supposed to use a configuration board 1. It means that we need to use a kernel 1, 2 RAM disks, and device tree 1. So that's the way the selection happening. Here, the example of the image node. So basically, each image provide, like, for example, in this slide, you may see the kernel image and how it looks like before it's built on the DTS. And like these images, as I mentioned before, can be referred by the configurations. A couple of FIT features worth sharing. So like it supports the external data concept. So each individual image payload can be not embedded into the actual device tree, but appended on top of this with a predefined offset and alignment, which is really convenient. So we can align all device tree at 8 bytes, so we don't need to relocate them. It also supports the compression and verification of each image and configuration. So I'm happy to share what we are doing right now with a FIT. So our initial adoption plan is to make it possible to use FIT image as a part of the DTBO partition. So right now, we only supporting selecting the device tree, solving the DT tables structure problems. The way it works, if DTBO has a FIT, so we ignore the device tree provided by the vendor boot and do the FIT selection and use the device tree from FIT. So all the device tree must be external images to in the terms of the FIT structure, so 8 bytes aligned. And we introduce the UEFI hook to allow firmware side to do the selection of the configurations to make sure the GBL is not aware of the specific of the device. Here is how the UEFI hooks looks like. So basically, we provide the FIT, some additional metadata which we discover inside the image, and allow the vendors to provide the selected configuration offset back to us. And some further idea I'm happy to share is like we are also thinking about introduce a vendor FIT partition, so to fully replace the vendor boot, and also have some ideas maybe replacing the entire structure, and also to make it possible to update the individual parts of the FIT. We are looking for introducing the better FIT support into the AOSP and fastboot and AVB to make it possible to verify the actual FIT metadata first and then do the payloads. Here's a couple of useful links for you to check later. Yeah, we'll be happy to have a discussion with you and answer your questions.
Thank you. Hi, I'm Trilok Soni from Qualcomm, and we talked earlier about the upgrades when you will introduce this feature and removing this vendor kernel boot, and these upgrade requirements for the newer devices coming from the older firmware. Let's say they had a ABL, now they have to move to GBL, or is it going to be the new devices launches only or something feature, because this is going to break some of the partition schemes. Partitions are hard to manage, kind of when you do upgrades, even, yeah, unless you are doing a full upgrades, like everything new, like a new launch device on the older SoC.
Luckily, so like basically we cannot update the devices on the field from non-GBL to GBL. And since this fit initial support are coming with the GBL, it means that only the new devices can use it. And to make it hassle-free for the initial, for initial check of the idea, so we don't change the partition, we don't introduce any new partitions and rely on the DTBO, because it's like we don't need to do any work, for example, on the AOSP to support that, because from AOSP perspective, DTBO is just a binary blob. So, and if it's fit, nobody cares. But then bootloader have to make the decision about whether we're loading from fit or like vendor boot.
Thank you. I know I will work with you offline, but on the right guidelines in the VSR or whatever it is, CDD, as we go, we should figure it out.
I was just wondering what's inside AOSP to actually take care of that, what's been added to the AOSP to generate the images and so on?
Not really. So as I mentioned, from the AOSP perspective, this DTBO partition, which is currently usually used as a DT table structure. So AOSP doesn't know anything about it. It's just a pre-built, like this is a DTBO image and it will be on the final artifact. So luckily to do the initial check of the idea, we don't need to change any Android tooling so far. And generating fit can be done by the fit tools provided by U-Boot.
Yes.
So
we still got about 2 minutes to go.
thank you very much.
So is there any looking into Android devices with UEFI plus ACPI?
We have some internal discussions about it. So since we're adopting the UEFI, maybe ACPI is the way forward. But right now, we don't have any particular plans on this. And the answer is more no than yes. So yeah, no. Thank you very much.
All right. Thank you, Dimitri, and my apologies earlier for calling you another name. All right. Here we go. Tank Fai. Yeah, please.
Hello, everyone. I'm Tong Fei Fan come from the Qualcomm CSE team. Today, my topic is bootloader-based S2D. Yeah, the S2D stands for the suspender to disk, a feature also known as hibernation. As we know, the current Linux kernel already supports the hibernation feature. It can save the system snapshot image into disk before the system power down, and restore it, and restore the snapshot image during the next boot up. Some commercial products wants a quick way to boot up from the power down than the current Linux kernel hibernation mechanism. And the overhead is considered to boot up a temporary kernel one more time. So we considered how about use the bootloader? And then we propose the bootloader based I2D. When the bootloader is used to restore the system snapshot image, we call it bootloader based I2D. And when the kernel is used to restore the snapshot image, we call it kernel-based I2D. The I2D feature have two main processes: suspend and restore. The suspender begins with equal disk. Okay, let me see. Yeah, as the right side, the suspend begins with equal desk into the power state sys node, and after saving the system snapshot image, the system will power down, and the snapshot image will be restored in the next boot up. The left side is the shows the difference between the bootloader based I2D and the kernel based I2D restore phase. For the kernel based I2D, bootloader first loads a temporary kernel. Those are temporary kernel. In the kernel stage, the temporary kernel completes the desk driver probing and mounts the partitions. Then it will lose the. Then it will checks if the snapshot image is existed. Then restore the snapshot image is needed. As we know, the snapshot image is usually stored in swap format partitions. So the temporary kernel loads the snapshot image from a swap partition into DDR, prepares TTBR and other necessary contexts. Then it will jump to the CPU interface, CPU resume interface. Then the temporary kernel completes its mission and hands over control to the restored snapshot image. Finally, the system and device resume, return to the previous power down state, and completing the I2D process. But the bootloader based I2D, the bootloader directly loads the system snapshot image into DDR, and then jumps to the CPU resume interface. And unlike the kernel-based I2D, the bootloader does not lose a temporary kernel. And in the kernel stage, it does not start a temporary kernel for the I2D preparation. This slide shows the data for the kernel-based I2D and the bootloader-based I2D difference. The bar chart demonstrates that The bootloader-based L2D have more efficiency with a notable improvement in the boot KPI. The below are the detailed data. As we see, the suspend phase, the suspend time are nearly same for the two approach, kernel-based I2D and bootloader-based I2D. But in the restore phase, the kernel-based I2D takes about 3 seconds for load temporary kernel, and takes more time to restore the snapshot image. This is due to the data page is restored method reason.
Might be covering this shortly, Eric, but I was curious what is causing the 2 orders of magnitude in the time to restore the kernel image between those two? What, like going 21 seconds instead of, a quarter of a second?
The data based on the debug version image, and we not do the compress to the image. Only currently the bootloader-based actually only a prototype. Due to some technological reason, there have many limitations. So we not do the image compressor and others.
So I guess you are trying to say, maybe think we can correct me, and is that you are not using the compressed snapshots in the case of bootloader base.
Yeah.
Okay. That's why it's faster, of course.
Yeah. Yeah, as below the bootloader-based I2D, we can get that from the bootloader initialization to the restoring snapshot image and then jump to the CPU resume interface. It takes much less time than the kernel-based I2D. So the showing a clear advantage in the boot KPI. This slide is about the two store method for the page data in the snapshot image. One places the data pages randomly, and the other places the page data serially. For the randomization of the page data, the page data is stored randomly in the snapshot image. During the restore, it okay. It restore the data pages one page by one page. It is compatible mostly of hardware, software scenarios, but it is slow. This is about the serialization of the data pages. The data pages is stored serially in the snapshot image. So there is an opportunity to restore a large chunks of data in order, improving the efficiency. the current bootloader-based L2D prototype use this method for better efficiency and the simplicity. Okay. We also do some experiment on the mobile Android mobile device based on the bootloader-based L2D. From the data, it indicates that due to Android system have more data usage on memory, so the third band stage will take longer. But the restore stage, from the bootloader initialization to restoring the snapshot image and then jump to the CPU resume interface, it takes about 8 seconds. So the KPI is very good.
So I have a few questions. So in the earlier slide, you showed the restore function is actually now moved to bootloader to improve the timing. So, but the restore structures, whatever, are not an ABI from the kernel perspective. So if you had to move into a bootloader, that means you're saying that kernel and the bootloader will be released together to be able to make it work. Is that correct?
I mean, you want to ask the if we use the same structure compared with the kernel-based and the bootloader-based L2D.
So the structure itself is not an ABI. It's not part of a UABI. So you can't really pick up and use it anywhere, right? But in your case, you try to use it. That means that you're closely binded to your kernel version, and then the bootloader they have to go together to be able to get this working. Isn't that true?
If you're taking the structures from the kernel and then using that in ABL, yes, I think in case of this, ABL and the kernel has to be together. Because if there is a major kernel version upgrade happens, and if there is a change happens, then I think that if that's the case, then yes.
As it's not an ABI, you can't really say that it's major or minor. It's an internal structure, so it could change anytime. Yeah, yeah. One more question I had was the most time saving that you had was you changed the restore image format, I guess. That's why you said you have gained from 20 seconds to somewhere around 0.2 seconds. Why can't we actually do that in the kernel itself? Why do you want to? Yeah.
In the case of kernel, I think it was compressed format, and the default flow of uncompression is what it takes them. I don't know if they tried uncompressed one in that case of kernel. I guess that's what you're asking.
The significant timing change was only because of that compress uncompress thing. Temp kernel was 3 seconds. Sorry,
Okay, let me give you the use case. Okay, that will make sense. Sorry. Auto needs 2 seconds boot to camera and maybe some IoT stuff too. And that's where it all triggered for us to do this bootloader based. Sorry. Time out. Okay, time out, and we'll talk later.
Conversation in the hallway.
Yeah.
Thank you very much.
Thank you.
Yep. John Jeek. Yep. Thank you. All right, please.
Yeah, hello. I'm Jong-ik from the Google. So today I'm gonna talk about the Linux VM on Android via AVF. First of all, I'd like to share about the background and the motivation. So what is AVF? AVF is an Android virtualization framework, and it is designed primarily for protected VM, and it focused on the isolation for kinds of sensitive workload. So VM payload and resource uses are typically minimum and strict controlled. So we decide to do a kind of the experimental. Our objective was evaluating AVF for general purpose competing with the standard OS like Linux. So we want to evaluate two things. First of all, the feasibility. So can AVF host a full Linux distribution on Android? And the other thing is about the performance. Is the PKVM and the cross VM stack efficient enough to run heavy desktop level application like IDE or official games? So you might have a question about that. Yeah, why virtualization instead of the user space controller, a container-based solution? So first, the one thing is incompatibility. So Android uses Bionic libs, you see, and it's prevent standard glibc-based Linux binary from the running natively. So to avoid that, you might use a proot on the ptrace for syscall translation, but it causes a significant overhead. So we decide to use a full virtual machine with a standard Linux environment. So we released this terminal app in this year. So it is, as I mentioned before, so it is experimental feature. So it is under developer option. So if you enable this feature, there is a terminal apps, yeah, with the Debian OS. So this is a brief overall architecture. So we use web-based terminal. So and also we use Vertio flag for rootfs image, and we have some guest agent. And for VFs, we use Vertio input to deliver Android views event to the VM, and also we use Vertio GPU with the GPU stream for graphical acceleration. And also we use Vertio Net with the Android tethering manager to provide internet to the VM. And also we use Vertio FS to share SD card directory with the VM. So it is about the detailed architecture. So first of all, the secure web-based terminal interface. So we don't want reinvent the wheel. So because it's a very complicated to implement a terminal UI with Android native UI. So we decide to use existing ones like XTOM.js and TTYD. So we installed the TTYD inside the guest, and it serve a kind of XTOM.js. So the app which you saw is just a web view. There is only web view and connected to TTYD. For security, so I use enforced the mutual TSL. So post injected one-time client certificate to the VM side, and the TTYD use that, and it reject unauthorized connection. So it means other app except the terminal app cannot access to the VM terminal. Another thing is a lifetime aware resource management. So Linux VM does not know about the Android app event, but Android app has its own event. Right? If terminal is go to the background, it need to be use less memory to avoid the LNK. And also, if the Android side disk size is small, so the VM side storage also need to be squeezed. And also, yeah, so we implemented in the guest agent. Yeah, we communicate with the terminal app. So receive some Android side lifetime agreement. So it depends on that. And seamless integration feature. So as I mentioned before, we use Vertio FS to share the SD card. And also there is a eBPF prober inside the guest side, and it detects bind syscall and trigger tunneling between the host and guest. Yeah, we have some challenges in building the image because it is just too slow to build the ARM64 image from the x86 machine with the Pi. So we use upstream Debian cloud image basically, and we use cloud init to customize the image from our kind of requirement. And let me talk about the bridging inputs. So originally I wanted to use just a pass-through, but it is rejected because there is some blocker like under permission and focus trapping. So if we provide every event to the VM side, user cannot escape the VM. So instead of that, I decided to use a kind of event translation. So capturing event at the Android view side event like keyboard or mouse, and then it translates to the Linux side event via the button input. So it supports both the software IME and the physical keyboard, and the for meta key, we add some custom toolbar to inject a Ctrl Alt or some keys. And also mouse, Android has some API to grab raw mouse event, so we use that. And also for touch, we added the multi-touch support in the cross VM to support the multi-touch. Yeah. And the most complicated stuff is about the graphical stack. So first of all, our windowing strategy is a Western plus kiosk shell, which is full screen shell. Actually, we don't want to provide a desktop, a full kind of desktop window manager like a GNOME or KDE, because we thought it unsuitable for small mobile screens. So instead of that, by using kiosk shell, provide each GUI apps like make each GUI app look like a standard Android app with a full screen. So yeah. So yeah, so I use Western with a kiosk shell. So and each GUI apps, runs it in the full screen mode. And with regard to acceleration, so initially I use software rendering with Raspberry plus Zinc. So I can verify the functionality for support from the high CPU usage and low frame rate. So currently, we use a JPStream for hardware acceleration. So, but the JPStream mostly focus on the kind of Android edge guest and the Linux edge host, but it's vice versa. So, I need to develop backend which use Android hardware buffer to map guest GPU command and buffer to the Android host memory. So during that, there is some problem like we suffered a kind of ARM cache coherence problem. So because ARM's weak cache coherence support between the host and guest, so even it is coherence memory, it doesn't work well. So we added explicit cache plus core in the JPStream at certain point, like a VKQ submit. And also we need to implement zero copy. So for previous the JPStream implementation, it has some kind of copies during the composition and the JPStream. So yeah, so for solve that, the guest render directly in the map the Android header buffer and equal the set buffer from the Android surface view. So to implement zero copy. Yeah, so we can run some 3D games like it's a very basic game, but Super Tuxcat and the GBeam, or you can run some VS Code, like some IDs, and you can use terminal. Yeah, for summary, we address the architectural difference between mobile and the desktop. So we compound the AVF capability for general purpose computing. So we have some kind of future work and the questions or discussion point about we need more optimization because it's still huge. The image is still big. It's almost 1 gigabyte. So I think we need to slim down the imaging, and also we need to optimize the boot time. And also we want to use a GKI for this case as well because host use GKI. So yeah. If we can share the kernel, so it is kind of saving. Yeah. And also we want more seamless update via the cloud init. So if the because for now it is not the cadence of update the terminal app and the Linux terminal is different, so it has some compatibility issue. So we need to solve that by the cloud init, and also we want to implement variant compositor on the Android side for more integration, more seamless integration. And and also I'm curious about any suggestions about the use case and workload via this VM.
Yeah, so this is the same thing we kind of supported a year back, I think with Pixel or something, where you can do this application, the terminal one, and then bring your own distro kind of stuff. Did you find some more use cases beyond developers using it?
Yeah, I think it's just experimental, but we want to maybe discover some game experience or maybe prototype apps. So we want to improve the GPU acceleration much more, and something like that.
Mm-hmm. There is no question. I have second question. Are we done?
I have questions.
Oh, okay.
Yeah.
No question.
So one of the things I was curious about, so obviously you've got some customization to the VM image with Debian.
Yeah, right.
That provisioning is kind of a complicated process, I know.
Mm-hmm.
This kind of limits the cool kids these days, they're running other things. If they want to run a different distro, has there been any considerations about how we kind of solve that sort of provisioning in a more generic way? I mean, obviously this is something every VM hosting sort of service has.
Yeah, I think that's good point. Maybe we can just provide the GKI, maybe kernel image and some RAM disk, and maybe let any distro running on top of that. Maybe I think every app itself has its API, and terminal app is just one of the implementations. So I think if some OEMs or chip vendors want to implement on top of that, I think they can do anything on top of the every app, the framework and the cross VM. So yeah.
So I've noticed that it only has, I think the Virt.io FS only has access to the downloads directory. Is there a way or plans to give it access to the whole SD card? That would make the Linux more functional, in my opinion.
Yeah, it will. Yeah, so entire.
Oh, really?
Yeah.
Okay. I tested the early version.
Yeah. Yeah, that's great question. So I think CrossBeam itself has some API to deliver the security key. So I think it's doable if there is a strong use case. For USB, there is some kind of security console or maybe some something like that, as I mentioned in the Virt.io input. Yeah. So, but at least for security key, CrossBeam has its own API. So I think we can do that if there is some requirement. Yeah. Thank you.
So is that GK adoption? So you are saying that VM will right now is booting just stock Debian kernel or something?
Before that, we use just a stock Debian kernel, but we want to try the GKI instead of the Debian kernel because we implemented some ballooning features in the kernel. So, but standard the Debian kernel doesn't have it. So we want to use that feature with the GKIE. So yeah. Okay. But it's not mandatory, so it's one of our experiment.
Yeah, I can launch my own unprotected VM anyway, so I do not have to use this. So at least on the Pixel, you can do that. Not be Qualcomm devices yet, but yeah, okay. So that's the reason. Okay, thank you.
Yeah, thank you.
Kong? Oh. Yeah, we're gonna have to take it offline.
Hello, everyone. My name is Tong, and I'm from Qualcomm CSE Linux kernel team. I've been working in Linux virtualization areas for a few years. So today my topic is about the RAM dump for trusted VMs, which could be an efficient way to debugging like crashing without rebooting the whole device. So let's start from the background. So nowadays the secure guest VM is widely used on mobile device to run confidential computation. So when there is a crash happens in secure guest VM, the developers, they want to collect the crash dump for this VM, and maybe we can send it to the cloud server for further analyze. After that, the VM manager can restart the VM and bring the user case back online. And here we have some problems. So unlike the normal guest VM, the secure guest VM's memory is isolated from the host. So it can also contain sensitive data. So we must prevent data leakage. And also the fault dump can be very large. So there can be many devices and the many crash instances. So it requires significant storage, and it will be difficult to upload to cloud server. And third is that the crash can often happen when the user case is running. So we want the reboot of secure guest VM to be fast. And the collection of the crash dump cannot take too much time. And based on all these problems, we have the design for mini dump. So the idea is like we only collect the critical areas, and the VM manager will create a mini dump table. So it will contain several regions. The mini dump table will be shared to secure guest VM side. So in secure guest VM side, we have a mini dump driver, and it will provide the interface for the client driver to register their own regions. So when crash happens in secure guest VM, the hypervisor will then encrypt the memory of secure guest VM and give it back to Android host side. And then VM manager can dump this memory to crash dump file. There is another topic about the mem-expect. So mem-expect upstreaming is ongoing. So if it can be accepted, we may follow their design. And then let's go a bit deeper. There are many drivers in secure guest VM. So all of them, they want to register their own regions. So here we can take the watchdog driver as an example. When the watchdog driver tries to register its regions, it needs to provide the name of the region, the guest physical address, or you can say the GPA, and also the size. So all this information will be stored in mini dump table. And also, there could be few guest mem region in the VM manager. Each of them has its own GPA range. So when we try to dump a specific region, we need to find the corresponding guest memory region by the GPA address, GPA, and also the GPA range of the guest memory region. And then with the GPA minus the base GPA of secure guest memory region, we can get the memory offset of this specific region. And then we can dump with host virtual address plus the offset. So the VM manager can save it to a crash dump file. It will include all these regions in mini dump table. Also, we need another thing like the elf header in crash dump file. So for the offline parsers, it can load all these regions into correct address. So here, the kdump is used for, currently upstream kernel widely. So here we want to have a compare between the mini dump and kdump. So on the left side, kdump, it need to, when the crash happens, it need to load the crash kernel and also the a minimum root FS. So they are all loaded into the reserve memory. And then you can use like crash dump binary to do the crash dump. I think that's the flow for like microdroid or AVF. So the crash dump binary can dump the VM core by the HVC console. And then the cross VM, or you can say the VMM, will save it to the file system. On the right side is mini dump. So the mini dump only need to allocate memory for mini dump table, and the client driver can register into it. So when the crash happens, we do not need to load another kernel. The hypervisor will directly encrypt the memory of the secure guest VM and give it back to host side. And host side can dump the regions into the file system. So here is some data. We have the like dump file size, memory usage, and also the dump duration. So the main difference here is that kdump need that crash kernel and also some reserve memory. So firstly, the dump file size is different. For the kdump, it depends on how much memory you are using in secure guest VM. So typically, it will use about like 400 MB. 200 MB. So for mini dump, we only collect the critical regions. So it will take about 1 MB here. And also the memory usage, since kdump needs some reserve memory to load the crash kernel and also the minimum root FS. So here it's reserved about 31 MB. Mini dump, the extra memory is used for store the like region, the info for the regions. So it will use 4 KB for about like 100 regions. And also the dump duration, kdump need to firstly load the crash kernel and also the root FS, and then you can dump all this memory. So it will take about 8.5 seconds. And for mini dump, the dump is happened at host side, so it takes about 270 microseconds. So overall, we think that mini dump could be a efficiency, lightweight, and a secure way to debugging the crash issues. What's next for the mini dump? So firstly, the mem inspect upstream is ongoing, so we may follow their design after the acceptance. Another thing is that currently our design is based on the Ganyan hypervisor from Qualcomm. So we're thinking of if we can extend the support for other hypervisor, such as PKVM. And also, currently, the communication protocols between Android host side and the secure guest VM is based on the shared memory. We're also thinking of if we can like extend the support for other communication protocols, such as VirtuIO. Maybe it's more upstream friendly, I'm not sure. So yeah, I think that's all I have. So any questions?
So I'm curious as far as, I know there's been some work trying to push mini dump upstream or some support for that, right?
Yeah.
But yeah. Is there any quick update on the status on that?
Yeah, sure, you can go ahead.
So there is a presentation from Eugene. I don't know if he's here on MEM Inspect, I think today. Today's last day. So yeah, and we will talk about the latest status, what happened from the last Linaro Connect Lisbon meeting to here, and what we are going to do. No, it's changed the name. It's called now MEM Inspect. And we have also Pixel support for that, also some backend. And the framework has evolved so that it's not specifically Qualcomm specific backend. And other folks, NXPTI or even server can use it. So there is no limitation there. So yeah, it made a good progress in the last 6 months, but it's still not there. So we are expecting some sign-offs. 5 minutes. Oh, sorry. Yeah, if I can add, so if you are working on NXP or TI processor or any other SoC vendors, you may have run into the similar issue where size is a concern or encryption is also required. And also one of the things when we started, this started around 10, 12 years back in the days of Qualcomm in early mobile, where I think in some of the mobiles we're launching in China, where they want to do some sort of analysis or dumps collected on the device in the field. And they wanted to quickly store it into the MMC and then send it back for RMA. And there you cannot have even a 4 GB, 6 kind of 8 GB, 12 GB, 16 GB kind of huge files for us to do analysis. So that's where the original idea started. And now we are upstreaming. And again, then we extended this from the host side to the now VM world. And that's pretty much the journey of Minidump. We call it internally Minidump. Once it moves to upstream formal name, we will call the same.
So I would be curious, I suspect that hosting providers who also have, like the, I'm forgetting the term, the trusted, it's secure computing or trusted computing, I can't remember, where they're able to basically run their VMs in kind of encrypted memory or whatever. Do they have a similar mechanism in order to kind of securely capture dumps that the host may not be able to see? Like for that sort of encryption, is this something that might apply for those as well? Those use cases?
Yeah, you can go ahead. No. You can go ahead.
I believe you are asking about the CCA or TDX, SEV, SEP, whatever it is. So I don't think I have seen anything like that, but they do all of this encryption stuff and by hardware mechanism. So they can use it too, in my view. Like if your VM is running under RMM stuff, there is no restriction. And I have not heard about but anybody running into the big memory issue, but they will, in my view, because a server is the first one to get commercialized there. But there are a lot of folks here, so I'll talk to Anish, maybe Anish KV, and see if he has a similar. He's from ARM, so I'll talk to him.
Any other questions? Yeah, thank you all.
TJ? Yes. All right. Do we want to wait for like the timing or do we? Okay. No, you might as well. Hey, we'll buffer that. Go on.
All right, hi. I am TJ Mercier. I work on the Android systems team. And we talk about BPF, telemetry, metrics, and accounting. So next, yeah. What telemetry, metrics, and accounting? So here's a non-exhaustive list of some examples. So starting with the first one there, shared memory. That's basically DMA buff. It's a bit difficult to track because it's shared memory. So we have two views of that. We have a per application view of that that's in ProcFS. And we also have a global view of all DMA buffers on the system, whether they're in user space or kernel space only, mapped or unmapped, doesn't matter. That was added initially in sysfs, and I recently added a DMA buff iterator to get that information. So we also have the amount of network use, CPU time, file I/O. Those are also BPF programs, or one of them's a out-of-tree kernel driver. And we've got wake-up source stats for like power management. That was originally added in debugfs back in the day. Then it was moved to sysfs, and I hope soon we'll have a BPF implementation for that as well. Yeah, so you can see we have like a variety of sources where we get this information from. So I want to talk a bit about some of the challenges with these different sources. So the first one's debugfs. debugfs is not even mounted on Android user builds, so it's just not available. any longer. But even if it were, it doesn't have a stable API. So we don't really want to be in the business of adapting to like 6 different kernel versions for an Android user build. It's pretty inconvenient. TraceFS, trace points are awesome. We have tons of trace points in Android. One problem there is that upstream doesn't want all of them. So we maintain a bunch of out-of-tree patches for all of those trace points, which is not ideal. And also those trace points are supposed to have stable UAPI. So we have to get those interfaces right. And if we don't, we've got to, it can be challenging to modify those in the future. So it's more maintenance. Also getting data out of TraceFS. So you don't really want to be reading from TracePipe and parsing ASCII text and doing computation in user space, especially for events that are like really frequent, like schedule switch, or like you can imagine like every memory allocation or something like that. But fortunately, we have the ability to attach BPF programs to trace points and do that work in kernel and update a map in the kernel and then only read that out in user space like as needed. So this works pretty well for things that are monitored continuously or read frequently. But there's a better way to go for things that are read rarely and can be computed from like existing in-kernel data structures. Yeah, so the DMA buff iterator is really good for that. And then we have ProcFS, it's like largely the same issues as TraceFS. And then SysFS. So SysFS is built around this idea of a single value per file. And generally what that means is we end up with lots and lots of files, and there's a cost for that. So here's an example of a listing of the DMA buff SysFS files. This is what's required to run a YouTube cat video. So this is over 1,000 files for a few hundred buffers. Yeah, so each of these directories is an object, a DMA buff, and under there's like 2 attributes. I think it's like exporter name and size. And similarly for wake up source stats, we've got like nearly 2,000 files here. And the difference here is there's 11 attributes per file. So these add up quick. They take kernel memory. And another issue is that it's slow to read them all. Like to obtain the global state of the system, you've got to iterate through those, do an open read close syscall. That can take a long time, like hundreds of milliseconds and even over a second in some cases. So that's pretty slow. And then because it's so slow, you can end up with a non-atomic view of the state of the system because the state of the system has changed underneath you while you're reading. And that's not ideal. And then a third issue. So for each one of those SysFS file creations and deletions, multiple locks have to be taken. And we have seen lots of contention around those locks. And I have a flame graph here to show that. So this is a DMA buff, a bunch of DMA buff allocations in tree. On the left side is the allocate stack. On the right side is the free stack. And you can see like the huge size of these portions of the stack for just doing the SysFS work. It's pretty significant. So zooming in on the allocate here, that's like 70% of the time spent allocating a buffer is just doing the SysFS work. And like on the right here, that tiny little box is the page allocator. And same thing on the free side. Lots of SysFS work, tiny little pink box for freeing pages. So yeah, there's been a bit of a trend switching to BPF from these other interfaces. And here are some of the things that we get from that. This first bullet probably should be like blinking text and highlighted and have words like wow and amazing next to it. But basically, we get to define our own UAPI. And by that, I mean we control the BPF program that gets loaded into the kernel. We also control the user space that runs and consumes data from that BPF program. But the neat thing is that both of those get updated at the same time. They're on the same system image, so we can update those arbitrarily, like in any way we want. And for example, the DMA buff iterator that I added is a traditional DMA buff iterator. You just cat the file, it gives you text ASCII output. That's great. Didn't realize that could be a significant problem until JP's talk, who just walked in, where he found that doing integer to string conversion to get in seek printf can result in like a significant amount of runtime. So, fortunately, we can get text output out of these BPF programs. We can also get binary output, like through a map or through a ring buffer. So now we have the freedom to completely change that interface that's already shipped and go to binary for a bit more efficiency if we want. Yeah, so low overhead. For BPF iterators, like in the case of this DMA buff example, I can completely eliminate all of the sysfs work just by using the existing in-kernel list of DMA buffers and iterating through those. So like that huge amount of overhead for every buffer creation and deletion now just disappears completely. So yeah, that's great. And yeah, to make this practical, we need core, BPF core. Core is compile once, run everywhere. Basically allows you to have a single BPF binary that will run on multiple kernel versions, and it handles stuff like renamed fields or relocating fields and structures, and that'll just work without having to have special code for that for the most part. So right now we've got two things that are going to start using this. The first is the DMA buff iterator that I mentioned. That's upstream. It's in all the Android kernels, and we've turned off the sysfs stuff for our next Android kernel release. The wake up source stats. So Sam Wu has proposed a similar iterator solution for the wake up source stats. This could use some reviews if you're interested. And yeah, I think I'm going to skip this for time and talk about the future. So one thing I would like to do is convert DMA buff dump entirely into BPF. DMA buff dump is a program that like shows you all DMA buffs in the system. It reads through procfs, proc PID FD info, proc PID maps, looks and finds where all the buffers are, tells you what processes are using them, tells you what's in the kernel. That can take seconds to run because it does all that reading. So we can move that to a faster implementation using the existing task file and task VMA iterators, traditional iterators that are already in the kernel. But it would be really nice to just have a single BPF program instead. But in order to get that to work, we need open-coded task file iterator support. Unfortunately, that was previously knacked, like based on the use case, which is like checkpoint and restore. So I'm hoping we can get task file iterator, open-coded task file iterator support to enable this DMA buff dump use case. Be interested to hear people's thoughts on that. Kailesh Singh has been working on a lock contention tracing program. So the idea is use the contention begin trace point, symbolize the lock address that we get from that trace point, see if it's on a list of locks that we want to monitor, and record the latency for those locks and report that via telemetry. That works pretty well for global locks, a little bit of trickery to get it to work for dynamically allocated locks, which have variable addresses. But that seems to be working. And then wake up sources. So there's no config to disable the sysfs work for the wake up sources, unlike DMA buff. So we should probably add a config to do that, to just skip doing the sysfs work for the wake up source stats. And yeah, this last one, memory reclaim. So really this is like direct reclaim latency on a per application basis. That's kind of a proxy for jank and like audio glitches and stuff. So that's a good user-facing metric to have. And that's all I have. So yeah, any questions? Like Dave is...
Yeah, there you go.
So sorry, this may be kind of a silly question, but in the latest versions of Android, I know in the older versions, you could define a BPF target and it would basically compile into a init, which would load the BPF program at boot time, right?
Yeah, it's loaded by BPF loader. All BPF programs on Android are only loaded at boot.
Okay.
And there is currently, and probably will not be, vendor support for that anytime soon.
Yeah, so we basically added build support to let individual services be able to define their own BPF programs and load them.
Yeah, so really there's just a list of a list of binaries on the system image that we just walk through and load at boot time, very early in the boot.
Yeah, so we added support so you can do it dynamically at runtime as well, because certain services will use BPF to do like runtime behavior. So that leads me into the second question. So I think CPU is one of the use cases you mentioned.
Yes.
I think there's a time and state BPF program.
Yes.
Yeah. So we have a similar one where we use ring buffers, same idea though, but we also have to scale by not just frequency, but also IPC, because certain generations of SoCs will run, like the same program in fewer instructions, because maybe it's not like front-end CPU bound. So I don't know if that's something that others would find useful, but if we could maybe standardize on like a generic CPU credit type of interface.
Yeah, I mean, that's a good idea, especially given what I said about like the limitations around loading BPF programs at the moment. Yeah, in fact, the person working on that is right behind you right now. So,
all right, let's talk.
Yeah, I was just wondering, there is a little bit of overlap here with generic netlink. I'm not sure if this was like a consideration as a replacement for the CFS interface, or...
Sorry, I don't know anything about that.
Oh, okay.
So something's been moved to Netlink from SysFS?
Yeah, we recently had to switch the interface in Binder. In a similar fashion, this was like a collection of data that was reported up to user space, and it was like a perfectly tailor fit for generic netlink. And yeah, it was just, this seemed like a similar use case for it. So I was just wondering, why was there any consideration for it instead of PPF? But maybe.
Yeah, no.
Maybe not.
That, no. Nice.
How did you find the integration of like porting in all the new BPF infrastructure now? Because like it's pretty involved, right? Creating the skeleton, loading the program, things like that, compared to where previously you might have just simply opened a file and just read things.
Yeah, it was a bit challenging. Android has its own loader, its BPF loader. It needed multiple modifications. We had to, especially to get libbpf support. Wouldn't want to do it again. I hope it's not much more maintenance in the future. Well, I guess we'll see.
Yeah, just one follow up. So like, do you keep the program active, or is it just like a repetitive process that loads the program and does the BPF invocation?
They're all loaded and penned, including the maps and everything. It's all done at boot time. So that consumes memory and resources, right? Maybe it's reasonable maybe there's a use case that's reasonable where we would unload those, but I don't think we have one yet. Oh, yeah, last one.
One more, I'll stop.
Yeah. Okay. Right. Go on.
Okay. You mentioned in the previous slides, like there will be some new work about like a reclaim. Do you think that will be some trace point add, or there will be another iterator like thing?
Yeah, we actually already have out of tree trace points for that. So the work will be just doing the BPF side of that.
So any plan upstream the trace point?
Oh, we could try. Yeah.
All right. Thank you.
Yeah.
Sorry.
Right, Rinlan?
Yeah.
All right. Awesome. With your hardware.
Yeah, I bring our hardware. It's like everyone says that RISC-V on Android, but Android on RISC-V is a myth.
Do you need me to hold something for you?
Yeah, just put it here. Yeah, it'll be okay.
Okay.
And it will take time to power on. Let's hope that it puts up into the home screen when the QA is there. Anyway, so I'll just let it do it and wait for it. Yeah, and I will talk about my slides and hope that it works in the QA section.
Sounds good.
Yeah. Hello. Okay. Good morning, everyone. I'm from Andis and RISC-V IP company, and my topic today is about the AOSP on tape-out RISC-V SoC without RVA22 and 23. I came back to finish what I started. Well, for people who doesn't know what is RVA23 or 22, that is a profile for the RISC-V. It's like, well, basically, we RISC-V folks messed up in the beginning, saying that, oh, we just need to have the privileged instruction set, and on privileged instruction set, then everything should be fine. Well, it's not. It's just like, you need the system ready kind of thing, and specs to tell the software people how to target your thing to the standards. So they came out with this kind of thing called RVA22 and 23 that have different kinds of instruction sets. But, as a RISC-V company, that we already have our chips tape out that is not complying with the so-called standard, like it's coming after the manufacturer SoCs. So we need to cope with that. And I'm Greenland employee by this technology, as I say, and I'm currently humbly serving as a system software library working group on the RISE, which is basically like the Linaro for ARM, but the RISE is the Linaro for RISC-V. And my agenda here is like this. What needs to be done to get, the AOSP source code that is maintained by Google, which is targeting the existing standard down to the silicon of what we have here, like this one. And how exactly to do that? And why do we even care about this old school hardware that is long before the standard come out? And if we want to support them, who will be need to involved in the upstream? I mean, from Google. And when will Android for RISC-V ever become a thing? It's like many people talks about it, but no one shows you the hardware. Well, so what needs to be done? We can break down into several parts. The build system needs to be patched. The libc needs to be patched. And many system libraries around Bionic needs to be patched, such as libunwine, and the very heart of Android, the ART, and the many ship builds you need to tweak with. And optionally, like we need to serve our customer who wants to have the NDK to build apps they are running on their smart anything, then you need to patch the NDK. So for Swan, actually, that Swan has a very, very great hook that is called CPU variants. And for the old days, you have all V5, V7, and now you have ARC with different types of stuff. So you have the variant hook. So for ourselves, that we patched it to have this CPU variant with the basic CPU instruction set. But this is not enough. For functions in the Bionic, that we need to patch out the vector usage. I mean, RVA22 and RVA23 basically means that you need to have a SIMD-like, not SIMD-like, but for the vector kind of computation, but we don't have that back then. So in Bionic, very thankfully, to be honest, that Bionic 1 has a quick switch to turn off the vector support because the poor RISC-V vector emulation on the x86 is probably patched recently, but the performance is still not well. So the Bionic had this quick patch for us. And for libunwine, because people are expecting to handle the vector and many register that we don't have, so we need to patch it out. And for the ART, that is a big headache that even though we taught Swan that we don't have this kind of instructions, but R doesn't care about it. So we need to basically patch out any bit annotations, compressed, and vector crypto stuff. And that's not enough as well, because for the for the Arch runtime, and ASM under it, they have hard-coded assemblies. And some of the instructions we don't have, but we have equivalent custom instructions in Anders, so we can replace it with the functional equivalence to them. And for another thing is that, there are the code emission things that sometimes have the hard-coded one as well, that it doesn't respect the hint you give it to it, that you don't have this kind of instruction. It's just hard-coded to emit RVA and 22 and 23 stuff. It doesn't care about the configurations. So we need to patch it out. And this is like basically the same thing, but on different files. And for the pre-builds, one of the big stuff is the neural network sample SL driver pre-build. We're not sure why this is required in the boot process, but it got our boot process to ham, so we figure out that the instruction we don't have it, and it caused the LIGO to keep crazy spinning and try to respond it and blocking the whole boot process. So we got it recompiled. And for NDK, that is just like the Swarm, we can instruct the CPU variant saying that we have an Andis RISC-V CPU variant that has blah, 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 blah extensions, blah, blah, blah instruction sets. And we actually filed some bug report to Google on their NDK sample, and there are plenty of the native apps are not expected to be compiled with RISC-V. And thank for Google that most of the issues are resolved right now. So to recap, why do we even care about pre-RBA22 platforms? Well, economical-wise, user demands cheap products which are already tied to AOSP system. You can see maybe you have go to the bar in Tokyo. There are many this kind of tablet that let you to order things, or in the market there are kiosks, or there are smart POS machines, and even industrial side they would tend to use ARM v5 like KitKat. KitKat is still a thing. Maybe you don't know, but you go to this kind of thing, you push about Android, and it's 4.4. And they are still using this kind of hardware every day, and they are not really, they don't want to toss it into the e-waste. Or the thing is deprecated, but they want to have the replacement, and they can to Andis, and they can to Sci-Fi or other stuff to have this kind of hardware to do their thing and get the support they need. Oh, sorry. So if we want to support this kind of thing, who will be needed? Obviously, Google have to, change their upstream to make this kind of, like I said in the art part, that many of the things doesn't respect the configuration or the hinting that you have tell you in the very high level. There are many things that is hard-coded, assuming that you have this kind of instruction instead of having a on and off set or switch, stuff like that. And architecturally wise, I believe that many mainland China companies and this will be very interested in maintaining this kind of layer, just like the back days you have on v5 or stuff like that too. The hardware vendors are very, very willing to pay for the price for this kind of abstraction layers. And there are existing hardware that runs RISC-V Android, such as our Chilai here. And Alibaba, they have the Xuantie C910. And Sci-Fi is subordinary in mainland China is called Starfi. They have this JH7100 SoC. Both three hardwares are pre-RVA22, and they are running Linux, running Android right now. And people will ask that when will Android for RISC-V ever be a thing? Well, most of the most answer is that when the amount of chips are growing, and business-wise is that when the NDK is matured. Okay, I only have 5 minutes, so this is my last slide. The very, very important missing pieces is that the TEE, the trustee for RISC-V is not there, and this may have bad implication on financial apps because they requires a secured environment to execute. And customer-wise, that currently, because RISC-V is regarded as a non-stable API, so Google doesn't want to have the Google Play on it. And even for the mainland China market, they don't use Google Play. The third-party app store for RISC-V is still absent, and we are trying to get F-Droid on it, but it's a long shot. Okay, thank you all. If you have any questions. Answer no. Okay, let me check whether it puts up. I guess I accidentally popped my PCI graphic card during the fall, so yeah. Anyways, but there on YouTube you can see that the boot up process. So yeah. Anyways, I'm sorry that never live demo, I guess. Yeah, maybe I can set it up in the back after during the lunch time or something. So no questions at all. I mean, well, thank you guys.
You mentioned the Android build system type issues. What about the kernel itself for these platforms?
The kernel currently okay. This is a fun question that Google once removed the GKI, the Google kernel image, the general kernel image for that, but we're basically using the GKI and turning off the extension we don't have, and that's all. We use the GKI. The latest GKI. And actually, I believe that after the removal, there's a new branch called GKI-RISC-V64, something like that, and we're still rolling with that branch. Yeah.
Okay, thank you.
Thank you.
Sumit.
All right, so I believe we're at the coffee break mark, and we will be coming back. Just give me 1 second here. I think it's noon that we're coming back. Yeah. So next talk is at noon by William. All right. So I'll see you folks soon.
Okay, take your time. Yeah. Unless you want the audience.
See ya.
Hello? Yeah. Oh, you can take a bit. I guess it's not got the our stuff on there at the moment, is it?
As long as you don't take the application full cycle, I define my focus. Yeah. Yes.
Maybe.
Yeah, so either here or something else.
7 a.m. might be hard.
I mean, 7 a.m. is great for me. That's my work.
Okay.
That's only if we're under the.
Yeah. If it's 7 a.m. I am working typically, but I wake up. Tell to wake up, get dressed. But
I can also do the 9 to 10 one.
30 minutes.
我们是有一个后设的想法叫把毕业的行，这个行。会，应该说其实我们不会直接接触到客户，而是 IC 跟环境。因为其实 IC 公司是不做以现在的生态系来讲，就是稍微在做 architecture， 而且就是那个那个就是说是碰到呀。他们讲就是他们对大陆这边直接他们的领导人现在也就是以口卷来讲，我们不讲的，就是后来为了 AI 大概所以说，所以说就是比如说像，比如 BI 可能就会来多少的，真的去碰那个，因为其实我以前在 BI 的实习过，碰了几个后来就记得，就是也能在招人，然后后来就越来越少，就渐渐的就被淘汰掉，因为公司养你其实没有什么用法，就是你会遇到。你搞这种其实也赚不到多少，就是会凶啊，其实讲这些人对公司来讲就是往这些商业上就不好意思，我现在有点像帮你把这个资源用在打，不好意思。
So Miguel will send out something saying this is not experienced anymore. Support merge.
因为抱歉，我刚刚听你的口语，我以为说是
experiment just being all through it.
话要小心一点啊，我就行。哦，我在那个，我在马街市场那边的时候。地方是哪？ OK， 地方是哪？羡慕你，我感恩接下来我自己开始。还有没有？但是那个我们没有谈。那老师，我今天为什么要拿这个就是后来写出来？因为我做 Android reporting， 应该说我的指甲，我第一份工作在 NC 的时候，非常非常顺利，可以说是昂11昂9。
I'm gonna read you it.
我那时候知道应该是。
I said. We'll confirm that. Todd confirmed that it is like 2 million devices, and even the OG guy, the running the hash. 2 million devices running the Rust hash map.
当时大概的时候，是我跟一个老外的生意，结果他们当时有一个案子，在
Yes, that.
结果上面
Yeah, right. Like how many? It shows the distribution of user space.
这个 task 就两个，
Which I guess
然后或是很像这样 process，
not a direct, upgrade versus, but there's a.
就是我想说，就是他们
Well, like the grade, you get a pass and Rust security.
就我后来就不高兴，就是应该跟我跑去问，就是
Yeah, get a shirt with that.
有没有干什么？就是到底上面
I'll ping the chat. I'll ping the chat.
越是小孩，就是越是话，
I'm trying to figure out, everybody attending here, hey, can I share?
一个英文的我知道，所以就自己发，那后来，然后我就对我自己我就来好，我是想拿着咖啡机，the taste of the bench is better served cold。你有没有看那个打法的教父？教父里面有一个经典台词，就是 revenge is the station of 那个，然后就是那几个例子，就是讲说复仇，就是到底要冷的上场，然后就喝一口水，然后后来想一想，人太调戏，我怕被裁判告，我说我不像 TST， 就告了些几个高潮2分手，到时候3个告我说，这是你们报纸要你们告我，真的假的？因为是有种不满。
No, he told me to be vague. Like 2 million plus devices. Not like direct, not a fixed figure.
这是整个上面有打码。
Oh, yeah.
就看起来就会是 enjoy 的样子，就是 enjoy 那个开启到主画面之类，就是开起来就是长这样，开起来就是长这样。
It's my badge.
对。
Get a coffee. As well.
就是刚刚我非常难摔到，
Because
下一个要
I'm careful with if
包
that's.
尤其是时间不多，给我15分钟，这个 MC 的非常看其他的所以你们今天跟郑他们老师有报东西，是需要我们算是比较还蛮多人的然后就是有些人像这大个体我也希望没有机会，大家对对对，目前现在在其实我也主要但是因为有时候会找不到人，那要自己下去接。对，就我们就是那个马尾，所以我们要排，然后如果找不到的话就自己然后就是我好奇，就是你们的修是，比如说到，因为我在 LPC 这边，其实因为我们是比较好的公司啊，所以我们的修是有时候会要修到说，就是拿示波器去量。一些 shoot 的 pro， 而你们的修是像我在电子学校，但做的是做在中央，那时候他们可能就是会验证各种方式，然后发现做不太对的时候，就是运动的时他就会拿过去，然后在那些讯号，然后再所以那个搓会是你们听友的要做的事情，我们听友 OK， 因为这个刚讲的是比较很早。就用这种词啊，这个你知道这种其实这 其实跟之前我们还有一个跳线，对，
他们会接很多，
对，
所以你也会这样，
就被迫要学，对，就是因为理公司就是被这样，对，
因为我以前我在我们
哦，
然后就是我就看他的文件，然后他们会接钱，然后我自己去玩，那其实我没有接过，我是能够把他们的成效建加什么加，就这样子，然后很困难，因为就是要用那个显微镜，然后手很抖。
我懂的意思。
对，我那时候玩一下，但是我不是把，他比如说接一条小线，因为那个
很细啊，而且其他有些那种经线是大的。
它有一些那种线搞标，就像有些是你或者是我的公司开的，然后我可能不知道我就是真的把那个线，就是一步那条线，
就是稍微换一下之类的。
换一下然后它就少了。因为然后我后来才知道说，功率比较高的，或者在开机上开错的，然后就换个就少了。
我之前也是有发生过，就是它这种背面这种有金属片，然后就是不小心手摸到，因为那时候有点汗，然后就被短路了。对，然后这种事就是不行。
我马上这个是什么？这个是你
手持的可以进来，然后其实我不用报关税，其实我们公司有出具一个真正，就其实你在 VJW 的时候，它就有一个那个 business sample， 就是什么商业样板，然后我们其实就真的有报，不过我们当然金额拿的很少，先拿100美元，对，然后这你刚刚看到那一块，其实它台币造价250万，因为它是 distribute， 就是我们当初是找台积电代工。然后这种很少量讲的，台积电的价格是超过，所以我们那颗要250万。然后老板就说带来要给我小心，要给那个时髦给我的话就是要150万哦。还好啦，还好，就是没有，就模仿。对，这是我发错一大堆了，就是我就单纯是那个强调的，就是很流畅的讲，但就是我发的错。对，
那这个问题它是接近内。
OK。
对。
了解。
我你是跟他
没有
接近的啊。
问词真的是很厉害。其实我之前很想去你们配歌，因为我很想跟着问词去就是相关的配歌，问词。就是 credit 差太多，因为其实我问题有很多 open source 的一些 credit， 他不知道他们这个 all in 的 SOC 然后在做这些科目，所以他其实有可能这个当然就是他的几个字，就是也是有种就是早知道就应该要去多弄一些这种就是像我们这种，
他说的意思也应该是说分析过，尤其是我们在我们这里，然后这样子。
对，就是有点像这都是 for the ones that are ready， 就是就是有办法能够照顾那些就是有的那个事情，然后我们这种就是还是会就是要乖乖一口哈努力刷对，然后要 SWE 的那个。因为后来做的话，就是一些 code test 的时候，就是难度上的差别是就是就贵公司的那次有些那个刷题，所以说他那个时候的最后出来，就是当时玩出了跟 SWE 是一样的，就是收费。
我们就是收费。
你们是收费的业哦，所以
他没有分他。
因为我自己，因为我之前有念，就一般都有就是购取他们那个 CD 卡，然后其实 CD 卡部门那个 CD 卡部门他们就说他们不会像苏伊这边的那个，
但公司大部分都是
OK，
大部分，然后后来才有一些比较特别的那个，他们会考。
对，就是那时候跟我们讲说 CD 可能会考答案，就是他的答案就是。真的很硬体的答案，对，就是那种就是来我们来画一下电路，然后我虽然会用我7分的，我不是 拿过一杯，我没开始好啊，就是那个他们好像比较偏像对对对，后面的话，那就没办法，就好吧。讲完了，我问过你们，面试的时候，他就说就这样讲，他们玩，有话他们变，他们毕竟是考的，是的，不一样。这也好奇，就是在就是苦口上工作的，你是第一份工作在苦口？没有，我之前在完全不同的在美语跟完全，你也是靠农场的，哦，了解，因为很多证据他是靠农场，该不会你也是那个？对，所以目前现在有说就是可能有一些排挤，那好奇是说就是你刚刚说可能也可以讨论。哦，就是好奇说，就是大部分都是有哪啥事情，比如说跑的嘛，全部对，因为我们的那些 credit 是来自OK，就是我们上出去的 credit，然后他会报回来，他会报回来，然后我们会去看 server 的问题，最近这个某个 credit 是比较严重的，然后我们会总是会有人要去看，看到我们就是那个，你们有点像那个。急诊的，就像你刚刚讲 triage，就是你们用急诊的那个伤病分类，先过去。然后呢，就是可能知道的是，我们前阵子那个急诊变动的走那所以蛮多时候是找不到的。OK。开始急诊，然后那个找到了，然后没有这个，或者没有这个病。OK。所以我们还蛮多自己觉得，还蛮常遇到的，要做。去修的，那说去修，其实通常第一件事情就先看看我要去修的方法。对，你搞不好自己有，你搞不好自己搞，然后就是会，我觉得有点像自己去看他们那些，然后看一些症状，一些描述，先来对一下，看一下，对。但是我还是有遇到那种确实要去，还要自己修，对，所以就是有一点。不错啊，我觉得听起来蛮好。通常我自己觉得，因为通常效果的话，我都会想要说，我们不能去特别是我在做专业的，所以我其实的话，其实在找办法，可能去看说之后，然后可能做一些配合，然后去跟他当时的，大部分其实我觉得很难打，我觉得最困难的是那个航拍，一定是有在哪个地方被烂的，然后。想要看那个，我们其实有一个开发，我都知道，就是当一打开这种有一个人是有参与过，完全懂，在好会这边也重要，而且就是讲对，就是因为我们历史这边，应该大部分是在边大概就是像比如说我们这种 application processor 就会跑边 studies 也会有一个叫 LPC， 就是 LPC。Business Test Project， 那它就有一整条 business， 然后我们就有点像 system validation， 就是比如说是设定的时刻，然后就在做 system validation， 就是 LPC 上，然后有报了某个 test， 然后就这边要先报，就是它整个 either 把它非常或 either 就是我们真的证明说是让它会发生在起对，就是所以就你刚刚讲的，我们拍个。减 OG， 突然就不见了，我靠！火烂死。也蛮好的哦。你有类似做加热电或者是赖之类的？有零件在哦，但是可以加，但是 OK。好。不会说那个，其实不是本来有，应该是说你在分析。在前面然后就是我有些时候就是如果人会，因为有些人特别是外国人，他会来那边有一些外国人，我比较了解，但其实我你也讲过他的，好久以前没关系，忘记了，好，还是这个题目的，我觉得。没有。
Well, you're not live, right? Oh, you're there you go. Sorry. Take it. All right.
All right, welcome back, folks. So next presentation by William, if you want to, or Peter, whichever of you.
Yeah, you can wait a minute over there. Almost there.
Hi, everyone. My name is William McVicker, and Peter Griffin and I will be talking about Pixel 6 support upstream and on Android mainline. Wait one more minute, but I will go to the overview slide just so you guys can kind of see what we're talking about and get your questions brewing. Okay, I'll go ahead and get started. So Peter's going to actually start us off. He's going to talk about the upstreaming that we've been doing, what we have so far, what we're working on, some challenges, and then I'm going to talk about how we're integrating this into Android and the challenges we face there as well. So I'm going to hand it off now.
So quick update on the upstreaming progress. One of the main things that's landed is support for ACPM. So that's the power coprocessor that's used for DVFS, interfaces with the PMIX on the SoC. So that's given us CPU freak, and it also unblocks enabling the regulators and power domains. Mailbox was also related to ACPM. We've enabled some of the base PM stuff recently, like CPU idle, CPU hot plug. That, due to our non-compliant PSCI firmware, was actually a little bit tricky to get enabled, but that's landed upstream now. And also we've landed some of the PMIX support, specifically for NVMem, which allows us to have Android reboot support, so we can reboot to bootloader and can kind of control the device a lot more, which is useful for CI and things like that. So, and of course, there's been like many driver cleanups in various, throughout the tree. So functionally today, with a pure upstream build, you can control the device over USB, like ADB reboot, ADB shell, that kind of stuff. We've got full Android reboot support, so you can reboot to the bootloader, reboot to recovery, that kind of stuff. UFS with Gear 4 and Hibernate support, so you mount your file systems and all that sort of stuff. And we've got the base level of PM support, so CPU idle state, CPU freak, and Hibernate for UFS. So, it runs nice and cool when you run the upstream kernel. And additionally, like the low speed interfaces like iSquared CD, SPI, all the base SoC drivers like Watchdog, pin control clocks, that sort of stuff. Oh, got electric shock off that one. So we've also enabled some upstream testing. We've got Linux Next boot testing. So this recently caught an oops on in the UFS stack a couple of weeks ago. We've based it on the Lenaro automation appliance. So there's a picture of it there with the phone. So it's kind of a circuit board with a 3D printed enclosure on top, and that's running like boot tests every day. And you can see some example of like the dashboard and the results, and those results should also be being pushed back to kernel CI. So yeah, we're looking to expand the testing and add more than just sort of boot tests as we go. So pain points. I'll start with some of the resolved ones because they might be useful for other folks in the audience. So I spoke a little bit about the PSCI issues with hot plug and CPU idle, so I won't go back over that. But we did add I added a new API to Syscon recently, so you can register your own custom reg map. So this is useful for like devices that may have been hardened. So you have a lot of drivers that expect to be able to write these registers using Syscon, but on Pixel 6, only the firmware can write some of these registers. So now an SoC can register their own custom reg map with Syscon, and all the client drivers don't have to change, but this custom reg map knows it needs to do an SMC call. So there's several kind of users of this API now as well, so I think it's kind of generally helpful for quite a few other SoCs. Also, we've added a new API to the PHY subsystem recently. So quite a lot of the downstream drivers, they kind of combine the glue and the PHY into just one driver. And when you come to upstream it, it's quite difficult to cover all the use cases because of like the PHY subsystem. It really gives you power on, off, and calibrate. So this has helped us for UFS Hibernate support, but I would imagine it will be helpful for some of the other drivers where they've kind of munged the controller glue and the file into one driver. And we've had some success, like the bootloader had some assumptions on layout of DT nodes and things like that, where then it wouldn't boot if that was different with the upstream DT, and those have been kind of fixed, so that was nice. The ongoing pain points. So 2 years ago, we spoke at Plumbers about overlays and how, like in Android ecosystem, they use that a lot to support lots of different variants of like pre-production variants of the hardware and silicon. And that's still an issue. So upstream, we only have the production Pixel 6 supported. Doug Anderson's recently kind of restarted this topic on the mailing list. So if anyone out there wants to kind of see overlays supported upstream, I would encourage you to chime in on the mailing list. We've also hashing out some stuff to do with the regulator core at the moment. So we have like 2 PMICs that have interdependencies between them, and Andre's been working on that. So that's currently going on the mailing list. And yeah, another one where people here might be able to help. Quite a lot of these drivers that we're changing are used on ARM v7 kind of platforms, and we don't actually have any hardware to test on. So as we moved more towards enabling display, it would be really handy if we had some like XNOS v7 platforms to check we don't break the drivers.
Hey Peter, Saravana here. I had a question, and if it's not important, we can move on. Hey, so for the regulator stuff, what changes did you have to make because of these kind of interdependencies? Is it something firmware development can't resolve for you, or?
So I think it's Andre that's been working on it, but the first iteration, yeah, Mark's there in the audience. So could you shut Mark Brown the mic?
So the design that he's going to try and implement, which should resolve everything, is that we make a fake device for each regulator and then use defer probe on the those fake devices, so the deferred probe infrastructure can sort out the ordering with loading everything and getting the tree to work properly. We don't see why that shouldn't work, but I haven't heard anything about his results trying it yet.
Okay, is the current issue that regulators are class devices and those don't kind of probe defer? Is that kind of?
Yes. So the issue is that if you've got one device for all the regulators on a PMIC, and you've got two PMICs, then if one depends on the other, that's fine. If they both depend in a cross-wired way, then device A probes goes, oh, I need device B, I'll defer. Then device B probes goes, oh, I need device A, I'll defer, and things don't work very well.
Okay, I wonder how this followed downstream, but sounds good. Thank you. If possible, CC me in the future ones. I'll update my mailing maintenance address soon, and then I can try to keep an eye and help if I can. Thank you.
Okay, will do. Yeah, so what's coming next? We've got quite a lot of stuff on the list. Automatic clocks, chip ID, a random number generator, the patches for the regulators, for the PMICs, fuel gauge, charger, power domains. So all of that stuff has been through a few different versions already. So I would expect it to land in the next release or two. And then moving on from that, we're looking at the dependencies of display. So IOMMU, Mali, and DRM display driver. And whilst this presentation's primarily about Pixel 6 upstream, you'll have noticed that Doug sent some initial patches for Pixel 10 and the Laguna SoC, and Roy in the USB team has been sending patches for the USB controller driver and PHY, so support's kind of starting to land there for that as well. So yeah, I'm going to hand over to Will now to talk more about the Android integration.
Yeah, and we have steps here that you can follow to get started. I'm not going to talk about that, but there's a link and some steps there to build in Flash. So yeah, I'm going to talk about the intersection of Android. So just to give a quick background, so we only have 5 minutes. Oh, sorry. Where do I find the question? Oh, Doug, go ahead. Can you go ahead, Doug?
Sure. I was just going to mention for Mark Brown's regulator thing, we actually did solve something like this on the TI bridge chip controller. I can give you the exact pointer, but we ended up creating a bunch of sub-aux devices, and then each of the sub-aux devices could individually defer their probes, and that way we could start them in, they could kind of have codependencies in that way. So I don't know if it'll solve the same problem.
Yeah, that's the design that he's off implementing at the minute.
Okay, cool. Sounds good.
Great, thanks. So just to give a quick background, we support Pixel 6 on all our Android common kernel branches all the way back to 5.10. So we're using that as our target for testing GKI. And but as you can imagine, there's a lot of technical debt that we have there. We have about 200 plus out-of-tree drivers there to support a fully functioning device. And so our goal with upstreaming is to reduce that technical debt and make the maintenance a little bit easier. This also allows us to provide a platform that's closer to upstream. If we start upstream devices, then there's a lot less downstream differences. It also gives us a chance to identify gaps and areas of improvement where we can pass that on to the Pixel team or to other partners when we find patterns that can be improved. And then it also allows us to test earlier. We can test on Linux Next when we have support upstream. So here's some links that you can find the guide to build the target and flash it onto your device. We now have an upstream target to build directly from Android mainline. So you can boot that to Android recovery mode at this point. And here are some challenges that we found so far with trying to boot an upstream kernel with Android. As you can see and imagine, there's a lot of user space compatibility issues. For example, upstream uses the sock at 0 node to organize the MMIO devices together. This is something that we recommend everyone should be doing downstream as well if you have a downstream tree, so that when you start to upstream, you don't run into these issues with SE Linux and your house having issues finding the files that you have. Peter kind of mentioned this before, but one thing about modularization and using the ARM32 devices, we've run into issues where the ARM32 devices don't have an ARM architected timer, so modularizing the timer driver has been difficult. So we've had to work around some of those issues. And then board support, overlay board support is another thing that we're having to work around downstream to be able to test different devices in the lab in the CI. So I want to open it up for questions. There's steps here also to build this new target, but I want to give time because I think we'll have like a minute left. Any questions?
If you said this earlier, is there any plans to do newer Pixel phones like the 8 or 9?
So Pixel 10 is started. You can see some changes on the list. We plan on working on that. Mostly Doug is going to be leading that. But yeah, as Pixel 6 becomes older and older and support gets dropped, we do plan on continuing with newer devices. Okay. Great. Thank you.
Tiffany? All right. The floor is yours.
Hi, everyone. I am Tiffany Yang, and today I'm here to present on how we make KUnit work for us and to pose the question, should we ever work for KUnit? So in order to introduce this topic, I wanted to present what I consider kind of a perfect comment at the top of the linear ranges KUnit test. Obviously, this is very long. I'm not going to make you read this right now, but I would recommend that you go read it all the way through at some point because it rocks. The first part that I want to highlight is why I think unit testing is kind of controversial in the kernel. And I think it's mainly because in a lot of different areas of software development, unit testing is used to have coverage. And what that results in is a bunch of tests that kind of test that your code does what you wrote and doesn't actually test the correctness of your code. And so if you actually ever change anything, it also requires you to change the tests, and that just makes everything slow and terrible. But this next comment is more to highlight why maybe you should want to write unit tests, why I want to write unit tests, and kind of describes like the policy for the types of tests that you want to write, which is, maybe write like a small set of well-selected tests and ensure that they test your logic as well as possible. So in order to kind of formalize this, I've organized unit testing into a set of weaknesses and strengths. The first thing that I want to say about its weaknesses is that I don't think that we should use unit tests to replace end-to-end testing. I mean, maybe you can sometimes, but really you shouldn't. I think it'll make your life worse. There are several limitations of unit testing that make it difficult, namely when you write a test or a unit test, you have to know like what your failure state is. In order to actually find other failure states, stressing or fuzzing are probably better. But the other thing that's challenging about that is that you have to actually be able to represent your failure state. If your code is broken because a lot of the things that are dependent on it are not behaving how they should, but you're not actually able to represent what it is about your code that's making it work wrong, you're going to have a pretty bad time writing unit tests. But there are a lot of things that make it really awesome for developers. Namely, you can write reproducible, or you should have reproducible tests, which allow you to reproduce errors. You isolate the code under tests, so you know that when it's broken, you can see that it's actually your code that's broken because of your test. Having these tests allows you to maintain code more easily. People can see, it provides a sort of documentation in that people see what the correct usage of your code is, what a good input and a good output is. And it also allows you to change how you do something and have the confidence that the thing that it's supposed to do is continuing to work as expected. And so this last part is that KUnit makes writing unit tests and running unit tests really easy and configurable. And since once you organize your tests, adding extra test cases is pretty easy and it's pretty boilerplate, which is a very good opportunity to use Gen AI. But once again, for the reasons that I covered in the beginning, I wouldn't recommend using Gen AI to just develop a bunch of like a whole suite of unit tests, because who knows if those tests are going to be useful. So altogether, these things are going to make your life easier. They're going to speed up your development cycle. And in order to kind of talk about that, this is basically a slide cobbled together of like different things that make KUnit cool. My main experience in working with KUnit was converting a set of binder tests or binder self-tests that we pretty much never ran because it required blocking a bunch of threads at init. So you can't run that in production. And even without having to like build the whole image and boot it, I don't know why I have 5 minutes here. It took like 10, it took a very long time to run. And so we actually thought it was broken for a while, but it turns out that it was just slow. Whereas now that it's been converted to KUnit, I'm running like a set of 75,000 different combinations of freeing different pages. And it takes about 25 seconds both to compile and run it on UML. And then on QEMU running x86, it takes about like 35 seconds, which is way faster whenever you're making any changes. It also allows you to test across a variety of different architectures, which Case highlighted in a recent FFS change that he made. And then Thomas Weisho is actually extending with his KUnit UAPI patch. And finally, here are just a set of, different things that are available in KUnit that maybe people don't know about. I'm not going to go through them all, but they're on the slide if you want to see. But basically, these are just examples of ways that people have made KUnit work for them. And then further illustrating the flexibility of KUnit, here's some other recent work people have done that basically, you can use KUnit to basically write a stress test. You can use a proof to write fewer tests and prove correctness. You can, modify UML so that you can run the tests that you actually want to write. The world is your oyster, So basically, the main takeaways that I want you to have with regard to like getting started is when you're fixing a regression, write a unit test. That's a really helpful time to know that you are, you're not writing something trivial. You're trying to fix a problem that actually exists. And once again, a lot of the functionality that was added to KUnit, and one thing that's pretty awesome for us is that if the functionality is not there, a lot of times you can add it. So yeah, you should start, except for the fact that it's not actually your oyster, because if we didn't have these challenges, then we would probably have millions and millions of tests. So there are certain things about writing unit tests in the kernel that make it extremely difficult. There is a form of dependency injection that allows you to do function redirection. It's kind of hideous, and that's a problem. Second, within Android specifically, the way that we write in KUnit tests is makes any workarounds you might want to have pretty limited. And then finally, there's this very common and very hairy problem of shared global state, which, you know, in the core kernel is like very, it's basically everywhere. And so in order to actually get the isolation that you want, you can't. So to go into this a little bit more, so you're able to redirect calls in the code under test, and that is really great if you want to always, you know, expect a certain output from a call that you're making. Unfortunately, you actually have to modify the code that you are stubbing out instead of the code under test. And so a lot of times you want to stub out code that doesn't belong to you. And I'm pretty sure most people don't want you to add all of these macros to their code because, once again, it's hideous and it just kind of pollutes everything. So that makes it difficult to actually get anything upstreamed in order to run your tests. The next problem that we have in Android is that we run our KUnit tests by loading them as a module, which means that you can't run, KUnit has the ability to run like early init tests that are not available to us before boot. And it also means that, you know, if you want to modify code, if you want to put in like a compiler macro in order to do something a certain way when you're testing and not when you're not testing, you can't do that. And any changes that you make need to have pretty much negligible impact on performance because these are, you know, the same kernels that are going to be running on actual devices. And then finally, there is that issue of shared global state that I mentioned before. You know, we have the ability to mock out certain functions, but it's very, very difficult to mock state. It's very, very difficult to actually like isolate state. You don't know if a downstream call of a downstream call is something that touches a global data structure. You just you can run into a lot of problems with, you know, unwanted side effects by running your test code. You need to make sure that you are you need to make sure that you're cleaning up all the time. But this also creates a problem because it means that you don't actually have the isolation that I was describing before, and you don't actually have determinism when you are, you know, touching shared state on a running instance of a kernel. Because you don't have control over what other people do with the data structures that you touch. So in order to address these problems, this is one of the first questions that I want to ask is, what are some ways that we can kind of work around some of these challenges? There was a global free list that we were accessing in KUnit that, in the binder test that I converted, and that created a problem for us. And so the way that we ended up getting around that was accessing that global state through a local pointer in a struct. Obviously, this is not going to work for everybody because it increases the memory footprint of, you know, every instance of the thing that you have. And another way to kind of get around this sometimes is to be able to refactor code to make it more modular, to try to avoid all of the extraneous state that doesn't actually necessarily impact the code that you're trying to test. And then hopefully somebody can present a better solution for some of these challenges. And the second question that I want to ask is whether KUnit is even the right solution. You know, there are ways to build kernel source outside of the kernel, and that is really nice when you want to have more control, but they can make things very difficult to maintain. So one example of this is ClockNet Sim, which is a clock and network simulator that was really nice apparently for testing timekeeping code, but you know, every time the kernel changes, you have to go through and fix everything else. And so maybe we can, you know, keep the simulator code actually inside the kernel. An example of that is kfuzz test. Or what if we just refactor for easier testing out of tree, like Liam and Lorenzo did with last year's VMA factoring. So open to the audience now.
You mentioned that there's some conflict when you run these K-unit tests with the running kernel. But I wonder if that's even like a valid case. Like, do we even want to be running K-unit testing on a running kernel, right? It seems that it's just better off to create some sort. I'm not familiar with K-unit, but it seems that we're better off like isolating that K-unit environment from the running kernel.
Yeah,
In a way, I don't know.
Yeah, no, I think that is like one of the things that I wanted to ask about is whether, anybody else working on Android thinks it would make sense for us to be able to have like a test only kernel. That way you can mock things, or not mock things out, but you can use compiler directives in order to just like change the pointer of like a global thing. Or, I think it gives you a lot more flexibility, but then once you start adding that code, there are always going to be other people who are running on production. And so whether that code is actually upstreamable or we're going to have all of these out of tree patches that make it difficult to maintain, might cause problems. Yeah.
So I just want to add like context. So we do have debug kernels, but I think the idea for KUnit is that we want to be able to add KUnit tests to CTS and to require partners to run these KUnit tests with CTS. They are running with user builds and production on a production device. So we can do additional KUnit testing with debug builds and maybe get better coverage there. But if you want to create a CTS test and require people to run these tests, then it needs to be for user build.
Cool.
We have to have that solution.
Thank you. That's good context.
Might be a dumb question, but when you say that you want to put something into a CTS suite, but then you also say that you want to be able to remove extraneous global state from it, my question is, I would assume the people that screw up their kernels and do the bad things are probably the people that are messing with the global state. They're, they're still going to pass the KUnit test, but they'll have messed up the thing that would stop it.
So, well, when you run your CTS test or VTS or whatever test it is, that's going to be in a lab and you're doing it to certify your device. You're probably not going to run those during while the user is using the device. So you can reboot your device and then all your states reset.
Cool. Does anybody have an opinion on whether we should, continue using KUnit? I think I love KUnit, and which is strange because one of the things that I loved most about kernel development was not having to write unit tests. But I think it's a really awesome tool, and I think that sometimes we get these regressions where you have to kind of contrive the user space user space input that is causing problems. Yes, Alice.
We get better at running user space tests when we have kernel patches in Android.
Could we get run better?
For example, binder lib test.
Do
we run that? I don't think so.
Sorry, we're gonna have to cut it short because we're gonna.
Okay.
Sorry. I'm sorry.
Sorry.
Yeah, no problem. You wait.
What? It could be in case of it. It's an AOSP.
Okay, hello everyone. I'm Yiwei, a software engineer from Qualcomm CSE Linux kernel team. And today my topic is the cooperation between CPU and system level cache by using NPM. Okay, first let's have a brief introduction to the NPM and the resource control file system. NPM stands for the Memory System Resources Partitioning and Monitoring. It enables the cache partitioning using bitmaps and the maximal percentage limits. It also provides the binary bandwidth control for quality of service. To make NPM more practical and easy to use, we need a standardized interface so that's where the resource control file system comes in. So it was originally introduced for the Intel Resource Director technology, and now ARM is adopting it for ARM, and it will assure the cross-architecture consistency. Okay, let's see a very simple example for better understanding. we can create two partitions P1 and P2 and assign the task to task 1 and task 2 to them respectively. And now we can change the settings change the bitmap settings in the schemata node. That will ensure that the task 1 will take the first two cache portions and the task 2 will take the last two. Okay, so far everything looks well, right? But there are always problems. There's limitations that some memory system components or MSCs, they are not fully compliant with MPAM specification. They may not have the compatible registers that the MPAM driver can detect, or they cannot even detect recognize the MPAM tags. So one of the system is the system level cache, or SLC. It is located between the DDR and various on-chip device clients like GPU, NPU, or ISPs. It provides high-speed caches for those clients to improve the system performance. So it is originally designed for the client-based usage. So however, we can just implement a solution here by simulating some virtual clients as MPAM partitions here on the system level cache. So now we get some available MPAM partitions on system level cache, but this is the first step. And due to the number of the maybe the clients on a specific system, it is fixed. So the partitions we can simulate is also limited. So here comes the next problem is that if the system-wide partition number is constrained by the lowest hardware supported partition capabilities. That means if we can only simulate two partitions on the system level cache and directly feed them to the MPAM driver, the system overall, the available MPAM partitions will be also restricted to 2. And actually, this is not acceptable because we still want the fine-tuning abilities for other memory system components. Okay, so far we got that those memory system components, some of them is important to the system, and we want to tune them while maintain the sufficient MPAM partitions available. We can just tune them. So to achieve this, we can introduce a translation layer before the MSCs that doesn't natively support the MPAM. MPAM hardware just will attach a part ID tag to each data transactions so that this transaction can be identified and traced between different memory components. So our newly introduced translation layer will convert the incoming part ID to the MSC specific IDs that the hardware can interpret. So, we can just the conversion relies on the mapping tables. So we can just using the SCMI banded protocol to program it. And also we can add a new resource type. We can call it mappings in the resource control file system to we can allow our users to configure the relationship between the incoming part IDs and the MSC specific IDs. Okay, after resolving above issues, now we can just apply the solution to many use cases. That's a very simple one is that we can let some noisy neighbor thread completely bypass the SLCs. For example, we can treat some background download and software upgrade thread as a noisy neighbor, and we can just isolate them from using the SLC. And this will help to prevent the interference with our critical foreground tasks. So it will ensure a smooth user experience. Okay, here's another example use cases. And we can just, since we have the sufficient MPAM partitions now, and we can implement more complex cases that involves using multiple partitions and mapping them into different partitions in on the SLCs. Nowadays, foldable screen devices are becoming popular, so there will be more parallel workload on the devices, and so as just it is similar like to the high performance gaming scenarios. So in such cases, we can just put some, we can apply more complex strategy on that. For example, we can just find out the most critical tasks and apply more cache resources to them. And but we need to be careful because we don't want to hurt other threads too much. So and also we have the MPAM monitors. It will help us to track the cache usage and the bandwidth usage to specific threads, and so we can tune the configuration for each group accordingly, and maybe in the dynamic mode. So it will help us to achieve the better performance and make it lower power consumptions. Okay, here we have a very simple unit test for that to show the difference between these cases. Here we run two bandwidth MEM tasks in running parallels, one as a benchmark and the other as an interference workload. In the default cases, we will run both. The task will share the SLC to simulate the interference. And in the mapping cases, we will just let the interference task excluded from the SLC usage. So in the 16 megabytes B copy throughput test, we can see there's about 8% improvement here. So actually, there was some difference between this after applying these solutions. Okay, so that's all from my focus. And any questions? Yeah.
So I'm curious the idea of this partitioning the SLCs by tasks.
Yes, correct.
So I guess how generalizable is this? I know you could customize it very specifically for a specific use case, but is there something where you could say, okay, we want to give system tasks a certain percentage, and then the foreground application a certain percentage?
Yes, this is very typical usage, right?
Okay.
So because we currently in our testing platform, we don't have too much, just mentioned before, we don't have too much partitions we can simulate. So we just maybe have two partitions we can do that. So current test is based on these limitations. And in our maybe later platform, we can just enlarge we can do more maybe fine tuning and works on that. Right.
Okay. I might also suggest, I know Kais had a talk about the libQoS and some of the QoS talks, and so we'd be interested in trying to kind of tie some of this in with that as well. Thank you.
Okay, thank you.
Sarah.
Yeah, I had a question. Yeah. So this translation layer you're talking about is like an extra hardware that you built and included in the SoC. Is that what it is?
Can you say it again? A little noisy. I didn't hear that.
Sorry, the translation layer that you're referring to, that's an additional hardware that Qualcomm has designed and included in its SoCs. Is that right? Is my understanding correct?
Yes. Yes, correct.
Okay.
This is specific hardware because.
And then have you upstreamed like a driver for it? Has that been done yet? Or?
Yes, we are in the process to do that because we just mentioned that we are just switching to use the resource control system, and that we are involving a new resource type on that. So this is what we are doing now. Yeah.
Thank you.
Community can catch.
I think adding a new type to res control might not be the best plan. As you said, you want cross-architectural compatibility.
Yeah,
There's a
right.
trick here you might be able to get away with, which is to say you only have one bit of portion. So now user space has to pick 0 or 1, and that gives you the value to use for the mapping without having to change res control and have that on other architectures as well. So I would push back on changing res control as much as possible.
Yeah, but yes, we can, things we act, but this is, we are trying to solve this problem, and because there are some misaligned with maybe the available partitions between different memory system components also. So we are just want to maybe put it more wide in a more wide usage. So I think we can have a more discussion on that.
So I was wondering if you could maybe briefly talk about how lossy using this hardware feature is, because on x86, it's like Intel RDT, it is quite lossy. So the way that we've looked into solving this in the past is actually having the CPU scheduler throttle threads if they're chewing up a lot of memory bandwidth. Obviously, like a totally different approach to the solution, but like, yeah, could comment on maybe like the overhead and how to like reason about the trade-offs there.
Not quite sure, not quite sure about that.
We'll talk afterwards too. It's fine.
Yes.
Thank you.
Okay, so no questions, and then we can finish early.
One quick comment in addition to what the other person was saying, that not only will it, when you throttle it now, it's going to make that particular thread look like it's more CPU intensive, right? So it's going to cause CPU frequency to go up because it's going to take longer to finish copying or whatever.
It's not copying. I'm not sure.
I think what you're saying is it's gonna like CPU util goes up, right? Because like it's essentially it's stalled on memory accesses more than it would be otherwise. Is that right?
Yeah, that's what I'm saying.
I guess, yeah, it's like the trade-off is memory bandwidth as opposed to CPU bandwidth. It's yeah, nothing's free.
Thanks.
Yeah. Thank you.
Thank you.
Isaac? All right.
Okay. Hi, my name's Isaac, and today I'll be talking about how we plan to transition our shared memory use cases in Android to MemFD, and how we plan on deprecating the anonymous shared memory or AshMem driver. So starting off with some historical context about AshMem. AshMem is a memory allocator that's implemented on top of the shared memory virtual file system in the kernel. And the way that it's used in Android is to allocate memory regions that are backed by TempFS and share those regions across processes using file descriptors. AshMem used to be part of the staging directory in the kernel until it was removed in version 5.18 about 3 years ago in favor of MemFD as the preferred way to share memory between processes. Even before that, though, we were already working on trying to transition our shared memory use cases to MemFD by introducing the A shared memory interface, which is just meant to, and adding MemFD support to it, which this is meant to just abstract the details of what allocator is being used between MemFD and AshMem away from applications, so they don't need to worry about those details. So just a quick comparison of about HashMem and MemFD. They both associate these shared memory regions that they manage with file descriptors. However, the way that you interact with the file descriptor is a little bit different depending on the type of the file descriptor. However, this is all kind of abstracted away anyway by the A shared memory interface. So that's hasn't been too much of a headache in terms of migration. But one thing that HashMem did have that MemFD didn't was support for what was called in HashMem unpinning buffers, which just allows user space to tell the kernel, hey, this region here, you can free it up if there's memory pressure. Ultimately, this was deprecated since it wasn't really found to be useful or offer any notable performance benefits. And this is, something that's not supported in MemFD and probably doesn't need to be. One of the benefits of using MemFD instead of HashMem is that MemFD is completely upstream. And HashMem is something that we maintain locally. So one of the consequences of that is that HashMem is only tested with whatever testing we do in Android, not like MemFD, which is tested not just in Android, but there's other tests that run outside of Android. Something that comes to mind is like K-self-test, for example. And another win with using MemFD is that the SE policy for it can be written so that you can specify what processes can share memory with each other, which is very different than what we have for HashMem right now, where anyone can use any HashMem buffer and allocate it and so on. So now I'm going to talk about some of the challenges that we faced while migrating from HashMem to MemFD, as well as some solutions for those challenges. So one of the problems that we faced was compatibility with upgrading devices. In particular, with Project Trouble, we are able to update the Android operating system independently of the vendor software. This kind of became a headache with our initial plan to just remove HashMem support on newer Android versions, because any SE policy that was in place for HashMem is no longer applicable to MemFD. So that means you have to update both the vendor and platform SE policy to be able to use MemFD, but then that basically defeats the whole idea of Project Trouble, and now you have to couple vendor and platform updates together, which is not great. SE policy was not the only domain in which we ran into this issue. Other issues, other domains were like seccomp policies, where some codecs aren't allowed to use some of the syscalls associated with MemFD. And again, it would involve updating vendor seccomp policies to be able to fix that. So a solution that we came up with was just to restrict when a shared memory, or that API interface I was talking about, allocates MemFD. And we've thought to restrict it to only allocate MemFDs on launching devices, and if an application is compiled or built for a newer version of Android. The reason for doing this is to give vendors the opportunity to update their SE policy to work with MemFD, as well as give app developers the opportunity to fix any issues that they have with their apps that they may encounter when using MemFD, which actually feeds into the other challenge that we ran into with this, which was that some applications do indeed make assumptions about the shared memory file descriptors that they receive. So here we have application A, which gets a memfd, and then sends it over to application B. Application B goes and says, okay, well, this is definitely an ashmem FD, and uses an ashmem ioctl command on that, and of course that blows up. So to be able to make sure that these apps can continue to work, one idea that we had was to add support in memfd for ashmem's ioctl commands. Now, one thing I want to specify here is that this is just temporary, and we plan on using SE policy to restrict the applications that can use this functionality, such that those applications are all applications that were built for older versions of Android. That'll make sure that we don't create any unwanted dependencies on this functionality, and that we can deprecate it once those applications have been required to update to a newer target SDK or API level. The other challenge that we faced when migrating over was the way that SE Linux handles memfd. Right now, by default, the way that SE Linux handles memfds is that it associates the memfd with the backing file system type, which on Android is tempfs. This has an additional consequence that you can't really, when you're writing SE policy, you can't distinguish between memfd and any other tempfs file on a tempfs mount. So this leads to policy like what we have up here, which is that you can say, oh, process A has these permissions to any tempfs file, which is not great from a security perspective. So you can kind of work around this a little bit by using type transitions, which is the first line here, where you say, okay, if process A creates any tempfs object, then label it as process A tempfs, and then you write policy using that label. However, this doesn't fix, well, it does reduce the scope of what process A and B, for example, can access. It doesn't fix the issue that we're still talking about tempfs files and not just memfds. So one solution was, well, actually something we ended up doing was that we upstreamed upstreamed memfd class support in SE Linux, which makes SE Linux treat memfds a little bit differently now. So what ends up happening now is that SE Linux will associate a memfd with the security context of the allocating process, and now memfds are no longer treated as files, but as memfd files of a particular security context. So what this ends up translating to is that now this policy that we wrote before for processes A and B to be able to share memory with each other becomes a lot simpler, like what I have here below. Besides the obvious aesthetic appeal that, yay, smaller policy, it actually does exactly what we want, where we're just talking about process A and B sharing memfds with each other and not all tempfs files that they allocate. So this is great in terms of being able to write fine-grained policy. And the way that we would want to use this is to allow make this, so right now in the kernel, this is something that you opt into. So for launching devices, it would be, something that we would want those devices to opt into this so we don't mess up upgrading devices. And finally, in terms of deprecating ashmem, the idea here would be to constrain what applications can allocate ashmem buffers. So again, we would just allow older applications to allocate AshMem buffers. And as they're forced to update to be built for newer versions of Android, that set of applications would dwindle until it's non-existent, and then we can hit delete on the driver. So just really quick to recap, the plan would be for a shared memory to allocate memfd on memfds on launching devices, and leverage the memfd class SE Linux support to be able to write fine-grained policy and temporarily support ashmem ioctl commands on memfds, and then deprecate the disallow allocations by constraint. With all that being said, I would like to open the floor to discussion, please. Yes.
So if I understood the unpinning feature, I think that is pretty useful for gaming workloads, because it's kind of like the semantics I think we need are basically madvise free, where you can specify a VA range that you just won't need until the next frame. And so you can either zero it out and free it, which takes overhead, or you can tell the kernel, free this whenever you want and zero fill it on demand otherwise. So I think we can do that with memfd, but I do think that actually is a useful feature for gaming, for like scratchpad buffers and stuff like that.
I see, but it's achievable, like you said, with madvise.
Yeah, so I might have been misunderstanding what you were referring to.
Oh.
So ashmem unpinning does something else. It allows you to say, this memory, I might need it later, but it's okay if you free it. And then later you tell the kernel, hey, now I need it. And then the kernel will tell you, hey, I freed it, sorry. Or, hey, I didn't free it, you can use it. So for example, you might like have an image and you have a decompressed version in memory, but if there's memory pressure, then just free the decompressed version and re-decompress it.
I think in general, madvise free usually fits the bill. So I haven't heard of anything otherwise.
Yes, I was a bit curious about that ioctl support that you added for memfds. I guess that's the support going in the memfd to, ashmem usage, and I wonder if it's, the wrapper layer is complete, meaning if you create an ashmem, is it real an memfd in the kernel, and then you can pass it and use it as a memfd elsewhere as well, or there's no usage for that?
Are you saying that, like, would it be useful to make it so that ashmem?
Yeah, like the ashmem API basically becomes just a wrapper, and it's memfds really in the kernel.
Yeah, that was something that we wanted to do. There's just not a clean way besides hacking open to recognize, oh, you're trying to get an ashmem FD. Here you go. Here's a memfd.
Okay.
So it wasn't really the clean solution, although a very nice solution if it worked. But yeah.
Okay.
Okay, and that's all. Thank you, everyone.
Thank you. Kalesh?
Okay, we go quick, right? Hi everyone, my name is Kalish and this is my colleague Juan. And today we will talk about some of the challenges we faced with running apps built for 4 KB devices on 16 KB Android devices.
Yeah, I'm going to give a brief summary. Why 16K, right? With 16K page sizes, we have like 4 times less page faults, and this translates to faster booting time. Like basically the device is going to boot at least 1 second faster, and the apps are going to launch from 2% to 3% faster. Sorry, 30% faster, right? And another metric that is very important is like a couple of months ago, we take the power consumption benchmark, and then we found out that the devices say in average 5.5% power. And just this morning, we just received the news from our infrastructure benchmark team that they run the performance benchmarks using the most famous game apps. And then it's like the benchmarks, it turns out that we are saving 5% to 7.5% power with 16 kpI sizes. So this is very good. And here is the problem that we have. For historical reasons, Android compiled like several years ago all the shared libraries and all the apps with 4KL alignment. And when we try to load these libraries in a 16 kpI size kernel, we cannot do it because the hardware permissions are done at page granularity. So we need to compile the apps with 16KL alignment. So without any solution, without any solution, we have like less than 44% of the apps can run on 16 kpI sizes.
Now I will go over the approach we took to deal with this problem. So the main thing we wanted to achieve is being able to load these 4KB aligned ELFs without modifying the ELFs themselves, because as you will see later, this is very difficult to do correctly. So the main approach we use is to modify the dynamic loader to firstly detect when we have such a problem, when the ELFs are only 4KB aligned. And what we found is that for most standard ELF layouts, we can collapse the adjacent permissions into just one non-writable segment and one writable segment. What this allows us to do is we can read into the 4KB segments laid out with a 4KB segment alignment into an anonymous mapping. And since we only have one permission boundary, we can then shift that permission boundary to align with a 16 KB page boundary. And this allows us to load more than 74% of the top 3,000 apps. So this is the main approach we use. We call it the read executable rewrite consolidation. However, we found that this is not sufficient because there are other fundamental problems which are not due to Android-specific alignment. For example, here we found that most static linkers, like both GNU-LD and LLVM-LLD, have this bug where they don't respect the max segment alignment for the railroad protection. So the railroad would only be guaranteed to have a 4KB segment alignment after we apply the read-only protection. This is a problem. So the simple solution we have is that we simply detect this in the dynamic loader and we invoked our compatibility approach. So this gets us from the 74% to 91.4% compatibility on the top 3,000 apps. But this is not sufficient because this only works for standard ELF layouts. So what about stuff built with custom linker scripts or other complicated ELF layouts? Here, the approach we initially tried is to implement a sub-page type protection, which the idea is similar to what JIT does. We have a MemFD, which we back the boundary page by the MemFD, and we have a secondary mapping backed by the same backing memory. And we would intercept writes using a signal handler that happened on the read-only page, and then we would redirect it to our writable memory. This approach was quite complicated, and it has some drawbacks in that it does not work for system calls that would pass user space memory to the kernel. And we also found with some initial benchmarks, it can be like about 15 times slower than a direct write. So we ended up going with a more pragmatic solution, which is simply to map the boundary page using rewrite executable permission. And this seems like a security problem, but what we found is that many Android apps already do such things where they do a rewrite executable permission on the ELF mapping, and they do things like in-place decompression of the code, and other use cases like the ART-JIT cache effectively uses the MEMFD technique, which our security team deems equivalent to a read-write executable mapping. So it does not significantly make the security posture of the device any worse. So here we just chose to go with the simple functional approach. So over time, we went from 44 to 94% compatibility on the top apps. And yeah, we will talk about how we can solve the remaining 6%.
Yeah, another approach that we try is like, we were planning to rewrite the L files, and then the approach consisted in this. We are going to read the L file, read the relocatable sections, and then it's like find the symbols that we need to fix the offsets to be like 16K aligned. And then we were going to also change the size of the L file, because when you compile with 16K alignment, the L file is bigger because all the segments have to be 16K alignment. Right? And then in paper, it sounds good, but when we try to implement this solution, what we found was this. When you compile share libraries in Android or in the app, you compile with optimizations. So that means that all the static relocation information is gone. So we cannot find all the symbols that we need to fix the offsets. So then what we decided to do is like, okay, but we know all the sections that are executable. So our plan is like, okay, let's find out all the instructions that use the PC relative, that use the PC, and then fix the offsets there. But what we found is like in the latest compilers, the switch statements are in the section code. We find instructions and data. So we can know, when we are fixing the offset, we don't know for sure whether we are fixing a data or we are fixing an instructions. So that problem, it turns out to be very hard to solve. And then we abandon this solution, right? And then it's like, how do we get the 6% remaining of the apps? So there are two main problems here. Is like, one is the obfuscators, and another is that the apps do things that are not compatible with our solutions that we present. So what is the problem with the obfuscators? The obfuscators, the main goal of the obfuscators is like, we want to protect the intellectual property in the IP of the apps. So what they do is like, the obfuscator usually they modify the L file in a way that we cannot understand it. And also some of them, they use their own loaders and they bypass Bionic. So because we don't know exactly what they are doing, it's like we cannot provide a generic fix for this.
And the second main issue that remains is that some apps have inherent assumptions about the information exposed about the mappings, which is not compatible with our approach. So here I have a concrete example which can give you an idea of what I am referring to. Here the app tries to find the ELF mapping and open the path corresponding to such a mapping with OpenAT, but it does not work because we use the non-anonymous mapping, and the name here does not correspond to a real path, so it fails. Even if they were able to open this mapping, the offsets the offsets will not be correct since we shifted the ELF to make the permission boundary align with the page boundary. So we are still thinking about how to solve this problem, or maybe there's few enough that we can get the app developers to work around this. Yeah, and now we want to open the floor for discussion. If anyone has better ideas of how we might be able to solve this remaining 6%, or maybe if we need to revisit the sub-page protection, similar to what the PowerPC has, the sub-page prod syscall. But yeah, if anyone has any questions. I have some thoughts here, but I would like to take questions first.
I think when Apple first transitioned from Intel to ARM, like they had the issue, I suppose. I'm not sure. I think their solution was that Rosetta translator. So I'm not sure if there is some potential similar approach is feasible in this case to help with these last 6%. Like maybe you need to just run them in a VM or I don't know, do something funny to help.
I just looked up what because I've heard of this problem with the FEX project, FEX, which is the AR64 running x86 binaries on AR64 systems, and what we end up doing in like a Sahi project ended up using is they have like a MUVM, so they ended up using a micro VM to run, and that seems to be their plan going forward. I just had a look on the side again, and it's like they don't want to hack up the FEX project emulator to do it. They're just going to use MUVM to do it. So that's the only other solution I've heard about.
Oh, in Android, we do actually run x86, sorry, on ARM64 on x86, the other way around. But the translation is fine if the page sizes correspond on a different architecture.
Yeah, they just gave up on when the page size was different and used the VM.
Yeah, if I don't know if this is correct, but I think Apple at some point used the RWX approach to work around this issue.
Yeah, and also we want to let the partners know that we are working with Play Store to enforce. I mean, all the new apps that are going to be loaded to the Play Store next year, they are going to be required to be 16K aligned. So that, I mean, with that enforcement, we try to close the gap of the 16K compatibility. But but there are some apps that nobody has maintained for so long that's the reason that we are interested in finding these solutions.
I'm not familiar with Android that much, but I work with a regular ARM for servers, and the default alignment by the linker is 64K. It would be best if you would follow that, and then it would run on all page sizes that are available on ARM. If you limit it to 16K, like you're doing it now, then the 64K will be a problem in the future with the same issues.
Yeah, that's what we try to push for, but there are some pushback in Android. Mainly, we could end up using more VMAs, which is a problem we fixed for Android, and also we can end up making the ELF files larger. And on Android, on new versions of Android, this is not a problem because the package manager punches holes on those padding areas. But on all devices which can still receive updates, we need to be mindful not to increase the storage usage there. So that's why yeah, sorry. Thank you, John. Yeah, thank you, Chris.
It's the same team, but different slides.
Yeah.
Yeah, you know the slide.
All right. Yeah. Hello again. Yeah, we have another presentation. I promise this is the last one. So yeah, many partners have been asking us, hey, can you please give us some recommendations about the hardware changes and software changes that you need to do in order to run 16K smoothly? So that's the main goal of this presentation. So let's see. So it turns out that the little devices that we have here are way more complex than the servers that runs in the data centers. Why they are more complex? We have more little hardware devices, like we have GPS, we have Bluetooth, we have TPUs, we have group throws. All the things that the big servers has is like our devices has it, right? So most of these hardware components in the mobile devices, they work properly with 16K page sizes, but there are some when we brought up the Pixel devices with 16K page sizes and other devices, it's like we found we have some issues like with IOMMU incompatibility. So the recommendation for the new devices is when you configure the IOMMU, make sure, when you pick your IOMMU for the devices, try to make sure that the IOMMU page size is equals to the CPU page size. What are the advantages of this? It's like you have less page faults in the IOMMU, and when we run some benchmarks, when the IOMMU page size and the CPU page size are the same, it's like the performance improvement is around 2%, right? Some of the disadvantages of having, like the IOMMU, like being 16K page size, is like the virtual address space, it increase. So that means that if we have microcontrollers, so 32-bit microcontrollers that need to map several memory regions to access to some devices, they might have issues accessing to that. But the performance gains outweigh that problem. Yeah.
Another piece of hardware that some devices might have is compression decompression hardware for hardware for compression decompression acceleration, and this we are recommending for this hardware to be able to work with 16 KB page size buffers or larger page sizes, because in our testing we found that the larger page size increases the compression ratio. In 4 KB, the compression ratio we found in a heavy memory pressure test is 2.5 to 1, and in with the 16 KB page size is 3.3 to 1. The recommendation here is that if you have compression hardware, it should be able to work with 16 KB page size natively. The next problem is, or recommendation is that ARM has a very old document which recommends if you have separate DDRs to separate them by 30 gigabytes whole. This may be a problem in the future if we want to reduce the amount of levels in the page table walk to 2 when using a 16 KB page size, as the kernel can only map the half of this, which means that we won't be able to access all the memory if you have this hole. The recommendation here is that if you have separate DDRs, you make them contiguous so that the kernel linear map can map it completely up to 32 gigabytes of this. We have already raised this issue with ARM, and they agreed with this. I'm not sure if they updated documentation as yet. And another problem that can arise is the control status registers in some hardware need to be memory mapped, and you might have different users that need to memory map separate registers. But if the registers are only 4 KB aligned in hardware, then when you memory map them, you inherently, in this example, for example, you memory map the CSR0, you also inherently map the other 3. So this can be a problem if you may intentionally or unintentionally corrupt the other registers for the other users. So the recommendation is also to have this 16 KB aligned, so you may be able to map them individually on a 16 KB device. The trade-off again is that you may need to you need to have a larger virtual address space, and some microprocessors might face difficulties with mapping this and the other parts of the RAM that they need.
Yeah, the other recommendation that we have for the partners is for the factory partitions. They should be formatted with X4 4K block sizes, or EROFS 4K block sizes. And the reason of this recommendation is because X4 and EROFS, they can work with 4K or 16K page size kernels. And on the other hand, F2FS, it has these restrictions that block size equals to page size. So you don't for example, let's say that your factory partition is 4K formatted with 4K blocks, and then you are using F2FS in a 16K kernel, it won't be able to read that. So the recommendation is use X4 with 4K blocks block sizes. So you are going to be able to switch between 4K and 16K kernels without any problem.
Is this actually a good idea? I mean, I can understand maybe when you are developing, it's nice to have this, but like when you ship something, do you actually need that flexibility and the trade-offs?
I mean,
Is this still a good recommendation? I mean, do you still recommend that more precisely?
But I mean, there are workarounds. Right now, we have some workarounds. Like in some of our devices that we brought up with 16K page sizes, they were formatted with F2FS and 16K blocks. So in order to access to this data, we use the DOM F2FS tool to read the 4K blocks in F2FS, and then it's like to copy all this data to another partition. And the disadvantage of this is that it's slow because you are copying data from a 4K block a 4K file system into a 16K file system. So that slows down the system. Does that answer your question?
I was just thinking, like, I mean, for development, maybe you want that flexibility of being able to load 16K kernel and 4K kernel, but probably at some point you just have either one of them.
Okay.
So do you still recommend to actually keep the X4 with 4K base sizes if you decide to ship with 16K?
Yeah, right now we have the developer mode where devices in the field can flip between reboot into a 16 KB kernel. So you are right. The recommendation is mostly for that, but for 16 KB only device, yeah, you don't
For
necessarily
production,
need
is
this.
still a good idea. That's
Thank you. Yeah. The other issue that we already fix is like when you compile the kernel with 16K page sizes, well, the issue that we were finding is like the memory reservations for CMA, they have to be 32 megabytes alignment. And why is that? Because there was a constant in the kernel, the max page order. And that constant changed according to the page size and to the size of the page block order before the 6.17 kernel. So what does that mean? That in 4K devices, the alignment has to be 2 megabytes for the CMA regions, and in 16K, they have to be 32 megabytes aligned. So you end up wasting a lot of CMA memory right there. So in the 6.17 kernel, we introduced this new variable like config page block max order. And what it does is like if we configure it with 7, it requires the same memory alignment that in 4K page size kernels. So you don't have to change the memory reservations in your DTS. And this, and your DTS should work properly in 4K and 16K. Now, what is the trade-off here? Yeah. So the main trade-off here is like if you want to use transparent huge page sizes. So how it works is like you have to isolate different migrate blocks, right? In 4K, you would need to isolate just one migrate block because the transparent huge page size in 4K is 2 megs. But with this change and with 16K page sizes, you would need to isolate 16 page blocks. So that might slow down the system. And if you fail to migrate one page block, it's like the whole process fails. So it's like that we consider that this is not a big problem right now in Android because nobody is using TSPs. But if you plan to use TSPs, it's like you have to be aware of this. Yeah. Oh, sorry.
With a larger page size, the need to use THP is also reduced because THP is mostly used to reduce TLV pressure as well. And increasing the page size has the same effect.
Yeah. Yeah, I mean, it's like, yeah, that's true. You want to do something?
Yeah, I was. Yeah.
You can just use MTHP. Okay.
Yeah, you can use.
You don't have to use the PMD or the THP. You can use MTHP. ARM64 support that. Right? In the neural kernel.
Yeah, the cont PTE feature
yes,
is with 16 KB page size effectively gives you 2 meg 2 meg TLB entry. Which because yeah, I guess what one meant to say is no one is using 32 meg THPs. Or in Android.
Okay.
Yeah. Yeah, so questions?
Just that when you talked about the compression engines going 4K to 16K, is there any concerns? I've seen problems in the past where we've moved like hardware engines or even software things, and it affects reproducibility of results because people are like have expectations on the result of a compression, and if tests that it's right, and then you change the page size and the compression gets better and results change. And
Yeah, that's true. Indeed, one of the issues, one of the things that we found out is like sometimes when we disable in the devices that we enable 16K page sizes, the compression block didn't work with 16K page sizes. But when we run benchmarks, it turns out that with the compression hardware disabled, the system was faster. So it's like, yeah, the compression block is going to be like, we are not going to use compression blocks in the latest devices that are going to be released. Yeah.
Any other questions?
Okay.
Let's move to the end.
Yeah, I think that. Yeah, I think that. All right. Thank you.
Yeah, thank you.
Thank you. Thank you.
So this is it for the Android MC. Thank you all for having attended. Wish you a good rest of the day and conference. And on behalf of the rest of the committee, well, good luck. All right. Thank you so much.
No, I'm going to go.
Oh, okay, cool. You at the party then?
But it's not like Yes. All right. Yes. We need something for privacy. Yes, we need something. Yeah.
Some trace you. Yeah, so that's the problem because it's not really anything that stops you trying to think. I didn't really. We're not actively thinking back. Some forms and things that you're designing. It's just not. And yesterday, so I was good at yes. One of the first things that states they made was they were running in a single thread, 7 minutes so that we're getting 32 copies that are running all the time. Yeah, no, you're saying that. Okay. Yeah. Yeah, but oh, you don't know. Okay. Yeah, because I want. Yeah, I can understand. Okay, I won't find. Okay. What are you doing? I have a bit. Oh. Yeah. Don't forget these ones that I do not. I see. Yeah. It's because that I thought he is the author. Oh, yeah. So I thought that he should have. Last one. So yeah, that's good. Just need to have grace for. I don't want grace. Because basically now, I don't know. I don't know.
Your time. I was for that people that were like 10 or 15 minutes to the talk when you first started and was like running 3 to 4 minutes a month. Yeah. Saw some videos looking more quality. Cars in the street that are covered in water.
Updated.
It's just no this.
Okay, let's start. It's actually it's 1 more minute. Okay, so let's start. Welcome to Live Update microconference. It's the first time this microconference is organized as part of LPC. And thank you for all the organizers here who's been working on this, Alex Goff, Mike Rappaport, David Medlek, and myself. So the first talk is going to be Live Update Orchestrator. It's a new feature in Linux kernel, but first of all, I'd like to give a definition and explanation. What is Live Update? So Live Update is a new system capability. It's an ability to maintain the workflow across the full kernel update without terminating the workflow. So the workflow might be suspended, stopped, not necessarily, but it might be, and then, but it's not destroyed. So the mechanism for Live Update is to use kexec. So we skip the firmware by going through kexec reboot. The current kernel works as a loader for the next kernel, jumps to the entry point of the next kernel, and then continues booting. But the big difference between kexec is that we actually also preserve some resources and do not reset the devices that need to be preserved. So things like DMA activity can continue during the Live Update. And at the end of the life update, the next kernel adopts all the resources and workload that was preserved. So the basic architecture, basic architecture stack is first we have this kexec, which been part of Linux kernel for a while. I think it was added in 2.6. Then in 6.16, we added kho. It's an ability to preserve memory state across the kexec reboot, so kernel memory state. Before that, we had a way to preserve user space memories, such as using pmem or pstore. But actually, pstore allows to preserve some specific kernel memories, such as buffers, but not any general purpose kernel memory. But with kho, we can just specify, please preserve these physical pages across the reboot, and it does that. And then in 6.19, we also added LUO. So LUO is a feature that provides the UAPI for the live update functionality. It provides a state machine, and it provides internal kernel API for the subsystems to register with the live update and be able to preserve their resources. So subsystems that can register with the LUO examples are memfd, IOMMUFD, VFAUFD, and so on. So theoretically, like even KVMFD can be added. So the LUO core concepts is that we have file handlers. They are the subsystems that register with the LUO. We have LUO sessions. So a session is a collection of preserved file descriptors. And if session exists, then those file descriptors are preserved as part of the session. If session is closed, so for example, if VMM crashed or LUO agent, the user space LUO agent crashes, then all the preserved resources that were added into the session are going to be automatically released back to the system. So they're not going to be participating in live update. And we're not going to have some weird scenarios where we preserve some memory that without any owner. So sessions give us a very good ownership and easy to understand life cycle. And then there is also user space agent that is going to use def live update. So the agent is not implemented yet, but we've started writing the design for the agent. And the agent is going to be using the def live update device access to create the sessions, then pass those sessions to the VMMs or containers or whoever needs to be preserved across the live update. So for subsystems to register with the LUO, they need to implement some file handler APIs, and the API consists of can preserve. It's basically to check if this file descriptor belongs to the registered subsystem. Then preserve is actually when the subsystem goes into and uses kho to preserve the necessary state, and it passes back to LUO the 8-byte handler. And then also unpreserved, which is in case the live update canceled. Freeze is called when we are out of the user space, so there are no mutations can happen once freeze is called. So the file handlers might do some extra serialization at that time, but freeze is already part of the blackout, so it's critical for freeze to be fast. Unfreeze is opposite if live update canceled. Then we have retrieve, which happens in the new kernel when we get the preserved file descriptor back. And then we also have can finish and finish. So once the file descriptor is retrieved, it's not necessary that we can complete the live update, because the file descriptors that you get back might contain just general preserved information, but the user space still need to perform some ioctls on that file to bring it to and to be fully alive. And this can finish and finish other operations that check that the workflow is actually correct and there are no like circular dependencies and the state machine works as expected. So another feature that is not part of the initial LUO series that landed is FLB. So FLB is a way to preserve some global states. So very often a file descriptor can have some global state associated with it that also needs to be preserved. So one example would be that MemFD might be using huge TLBs for the preservation. And so multiple MemFDs would use the global state from huge TLBs, and FLB provides with this again a very well-defined life cycle that when the first FD of that type is preserved, that's when we create the FLB object with this global state, and when the last object is unpreserved or retrieved and finished, then this FLB gets destroyed. Okay, so this is just a very simple life update flow. So we have pre-life update, then when machine is just running in the normal state. Then we have this pre-blackout. So the user workload is still running, everything is good. So in this example, I'm giving the VMM as virtual machines, but it's not necessary just about the VMMs. So during a pre-blackout, we load the next kernel into memory, so using the kexec load. We are thinking to use LUO agent for that because we want to verify the capabilities of the next kernel, that it actually understands the versioning, the preserved state versioning between the current kernel and the next kernel. Then the LUO agent creates the sessions, passes them to VMM. VMM puts the necessary file descriptors into that session, such as so it would preserve VFIO, MemFD, its memory, and other things. And when VMM is done, it notifies the LUOD, so it might notify it by closing a socket, or maybe there is a actual communication between the two. So and the shutdown starts. So LUOD has to be the last agent that shuts down. So most likely the reboot command is going to be performed also by the LUO agent. So because someone has to keep the sessions open through the reboot. Once we enter into the reboot system call, one of the first things that we do is we call the freeze callbacks for every file handler that was registered with LUO and that have some resources preserved. So they can update the serialization. And then we go into jump into the new kernel. So during the kernel boot, FLB data is accessible. So that's the global data. The difference compared to the file descriptor is that the global data can be accessed from the very early boot. And once the user space is started, LUO agent can restore the sessions from the previous kernel, so it retrieves the sessions, and it passes them to the VMMs, so VMMs can retrieve the file descriptors from their sessions and resume the workload, so the VMs can be resumed. So post-blackout is when vCPUs are resumed. Then VMM can do some extra work on the file descriptors and perform the session finish operation. So once session finish is done, that's when we go into this post life update operation, and machine is running normally just the same as before life update. So this is the whole state machine. Okay, so for the future work, we have this LUO agent that we want to write. It's going to be, most likely it's going to be a reference agent, not something that is intended to be used by different vendors, because We suspect that every cloud provider has their own setup or own configuration, and so they most likely are going to be using the DF Live update directly without needing this LUOD agent. Then we also want to implement the file handlers. So already under review in submitted to LKLM the VFIO series, IMMU series. There was a PCI series proposed. So we want to have we want to add support for guest MMFD. So once guest MMFD gets the huge TLB preservation support, we will also add not as preservation. Once guest MMFD adds the huge TLB support, we want to add guest MMFD preservation as well. And we also want to add huge TLB preservation support for MMFD, and I believe that that series is also an RFC and sent out to LKML. And of course, we also want to support trust and compute. The architectures that we are currently targeting are Intel, AMD, and ARM64. And for the future work, we also want to reduce the blackout. So right now, all this live update work really depends on how well optimized the kernel to shut down and boot. But it's possible to do some very good optimizations, and there are also ways to make it truly seamless if we do something like orphaned VMs or something similar to that. But we can talk about this during the blackout reduction talk. So I think this is the last slide. And if there are any questions, yes.
Is it possible to build a generic protocol in between the new kernel and old kernel? Because I would like to use this for the multi-kernel update as well.
So yeah, is that Pratish? You should also take that.
Oh.
We already have KHO as the generic protocol, right? Like KHO, kexec handover.
Kexec handover is like provides this protocol by using the FTTs, right? Or are you talking about something else?
I'm talking about the user space one.
User space?
Yeah. Because you want to live update between the different VMMs, right?
So, so I think you're talking about the LUOD in this case, this agent thing that I also mentioned. And yes, it will have some protocol that is going to be described in the design in terms of how to know which sessions belong to which owners before the reboot and after the reboot. So,
thank you.
That's it.
So, hi, I'm Pratish. I'll talk about managing serialization versions for Lua objects. This is the rough agenda. I'll talk about the two sort of steps we need to take this in. So right now, live update is pretty simple. You have only one file handler, which is MMFT. It only has one version because it landed in this merge window, right? But eventually, we're gonna evolve the code. We're gonna add new features. We're gonna maybe change something. We're gonna find bugs. We would need to improve performance. So there is eventually gonna be a need for new versions. And I think we should start looking at how we're gonna manage those versions, because you don't wanna just let them run in the Wild West, right? You don't wanna boot into a new kernel and then find out that this version is not supported, because then your live update is gonna fail and you probably have to crash the machine and reboot something. So wanna have at least a way of knowing whether live update it has a chance to succeed, and then eventually maybe even like a version negotiation and other stuff that we can do. So the first step is the simple step, and that is to just list all the versions, right? I think that in VM Linux, in an ELF section, so you can call it, say, live update versions, but how Lua works is it has strings that sort of encode the version of the serialization format. So you take those strings and you put them all in an ELF section, and then your user space tooling can read the ELF section of your current kernel, and it can read the section of your next kernel, and then it can do this matching and figure out where the overlap is. And if there is no overlap, then it already knows that your live update is going to fail. And at that point, you probably want to abort the reboot and probably deploy a new version that can actually work. The way to do it is kind of simple. So I've designed like this simple data format here, which has a header with some magic and versioning for the data format. And then it's a simple list of strings that you have. So all of the versions are just listed in a table, and then your user space tooling takes care of matching, like which is MFT strings and which are IOMMU strings and so on. And you can do it in other ways, but I think it kind of works. And then you, instead of defining your live update handlers directly, I added a simple macro that makes sure the handler is defined, and then it also puts the right stuff in the right ELF sections, and then some linker magic to put it all together in the right places. So this is the initial thing. I sent out an RFC for this on the list on Thursday, so you can go out and try it out. I also wrote like a small command line tool for this. So I want to open some discussion, general ideas, what do people think? And then the question down below is, what sort of ABI this ELF section guarantees this ELF section is going to have? So does anyone have any opinions?
Actually, can we ask something else? Can we go a step before that? Why do we need, like as part of the Lua, to have the versions and don't leave like to each component that is going to register with Lua, leave like on the component to handle that? So for example, like in the KHO FTT, you can specify the version.
Yeah.
And like when you try to like restore things, like the component's going to say, okay, I'm not supporting that. I'm going to continue without.
So that's already there. And this is like the kernel runtime. At runtime, when the kernel boots up, it's going to find that out. But if you're already booting up into a kernel that doesn't know your version, you're just going to panic, right? So this is before you ever even do the kexec. So this is before you load the new kernel. You want to know which versions it can support, right? Because if your kernel version that you have speaks version A and the next one speaks B, like sure, when you boot, you can find out it doesn't work and panic, but ideally you want to find out before so you don't have to kill your VMs.
So what I want to say, like you don't need to panic, right? You just need to continue like kexecing like as if Lua was never there.
Sorry? No, you can't do that because there's devices running or IMMU and
you have to panic because you can get memory corruptions. You don't know where DMA activity is going.
And you don't know where the preserved memory is either, right?
Some of the things you pass over KHO will be mandatory and you will have to panic if you don't support them. Some of them are not. Some of them are accelerations, right? Some of them is, I have left the hardware in this state. You can pick it up really quickly if you listen. Or you can do what a normal driver currently does and reset the hardware and do all the discovery and. So there are mandatory things in KHO and there are optional things. And it's only when the mandatory things change that you will actually have to trigger this.
Do you really have optional things like...
but even if you do still, if you know in advance that you will anyway need to reboot, you can do it before you load in the new kernel.
I'm a bit new to this topic, but you're talking about it would be bad if we booted into a new kernel that was incompatible. Is it possible if the kernel did discover that it was incompatible to go and just do another handover to the previous kernel, which definitely...
No, it's not possible because the new kernel needs to re-serialize all of the state. And,
Okay.
that can't work if it doesn't understand.
So a couple comments. First one, we already have a compatibility string in the FTT, right?
Yeah.
Are you preserving exactly the same string and the same format, the same values? Okay. Do you support multi-compatibility?
That's the next thing I'll go to. Multiple compatible versions.
Because one kernel may be able to support like 3 different versions. Say we have 5, right? That certain kernel supports 3 different versions, but not the 4th.
Yeah, that's the next part of the presentation.
Okay.
So.
I mean, that is going to be mandatory in order to make this actually work.
Yes.
And it also goes into the design of your list and what you actually propagate there. I would like to, I haven't looked at your patches yet. It's Thursday, so very recent. But I would love to see whether we can somehow tie support for certain compatible strings with the exposure of compatibility in that section. So is there something where we can, for example, create handlers for compatible strings, or at least have some well-architected thing?
Yeah, that's what we have already. We have handlers, and the handler specifies the compatible it works with.
So you are generating the compatible
from the handler registry.
From the handler list.
Yes.
Oh, okay. Already done. Good.
I just want to mention that it's not guaranteed that you will always be able to understand that you can't reboot. For example, there is things like FDT protocol itself. There is things like KHO. I mean, this doesn't cover only Lua part, but some part is still maybe next cannot understand.
Yeah, maybe, but I think at least we want to solve this Lua part of the problem, right? But so I want to move on to the next section because we only have 6 minutes. Okay, so what Alex was saying, multiple versions. Multiple versions is pretty much a necessity if you want to actually ever roll out a new version, because if all of your fleet speaks version A, at some point you're gonna want to switch to version B. So you want your kernels to start serializing in version B. What you probably want to do is you want to deploy out version B, A and B both to the whole fleet while you still live update using version A, and then you make the flip, and then eventually once the whole fleet is refreshed, you would get rid of version A and then everything runs on B, right? So you pretty much need, because sure, you can detect incompatibility, but if you can't do multiple versions, then you can never upgrade your versions without doing a full fleet reboot. Also gives you more flexibility in rolling back. So what I propose is we add this multiple version infrastructure to Lua core. We can have upstream decide what guarantees it wants to take for the matrix of versions it supports, right? And then cloud service providers downstream can do their whole matrix that they need. But if the core, at least we should get the core infra into Lua, so it's common and it's nice and there's no hacks around. Doing it is, so the way to do it would be add a concept of a type, which you could do in the previous way as well. But the idea is you do a type, for example, memfd, and then and you list all the compatibles for that type. So memfd is going to have, let's say, v1 and v2. So you get the same table with the same header as we had, but now we have, instead of one string, we have a pair of strings, which says the type I describe and the version that this type has. Then this is sort of less important, some Lua core plumbing. Then you need to provide a way to select the type, and that could be a simple IOCL that we have. So we give it the type, so like your user space can do this negotiation, right? It can see what the both kernels support by looking at the ELF sections, and then negotiate the common types and make sure everything's there before it loads the kernel, so the kernel serializes in the right formats. In discussions before, Jason Gunthorpe was kind of not a fan of this idea, so he suggested an alternative is where you serialize all versions. So let's say 2 versions, you produce serialized output for both. That's an option as well. I am not sure. So we get away with some UAPI and ABI exposure for the version strings, but I think it's gonna add overhead in performance, and maybe we even run ourselves into an inflexible corner.
So
Not sure.
I think it might be okay at the beginning. First of all, serialization happens outside of the blackout window. So we'll use a little extra memory probably to like the metadata that gets serialized. But it might just work. It might not be like, I mean, we can start optimizing and do this selective versioning once we actually have a problem, like the performance problem or the memory overhead problem. But
Yeah,
before
and
that,
I think
maybe
we might, yeah, that makes sense. But also we might have another problem where maybe, I'm not sure, I don't have a real data, but like you might have two serialization formats that need the core data to be in different ways, right? So then they are incompatible. So you can't do two formats. But that's yeah, more hand wavy right now. So maybe this just works.
The other problem is that you now have also two objects that basically represent the same thing.
Yeah.
Then you need to have filtering logic again on the incoming side just to figure out, oh, it's actually the same object but the two different versions.
Yeah.
I mean, the way we handle versions is like a normal device tree way, right? So you just passing all of that out is tricky. I mean, we could basically say you could have a default field, right?
Yeah.
So when you define your serialization format, you could have like multiple handlers that can serialize and just have a default.
Mhm.
And then you can have effectively just a normal sysfs that globally sets the default to something different, like or like
Which is this IOCL
a
basically.
some cookie
Yeah.
somewhere.
We don't want to do sysfs, so do this with this IOCL. That's the main idea that I have. But yeah.
But it's one version for the overall system. It's not a version per individual piece, because then your combinatorial matrix is just going to explode, right? So you always want to basically say for example, you have a version current and version last as a canary, right?
Maybe.
Very hard to enforce.
So
to be very static. Like if you have one global version for the whole system and many different components and something small modified in a component.
Yeah, so when you're serializing, you're already walking through all the different handlers, right? And currently, you're just writing out the current version there is. And what I'm saying is, if you basically just have the same handlers with a current version and last version, for example, that's I think all you actually need. You don't need 5 different versions. You just want to say last. But you can extend that downstream if you really want to. You can have like make it extensible so it can be current, last, and any other version number that you want. But if you at least combine all of the, you want one abstraction level in between. You want like one number, one thing, one like last current entity that assembles all of the different 500 versions of objects that we can have.
yeah, maybe, but I'm not sure if that's. But yeah, please reply on the list. So the patch is out for at least the first phase. Go ahead, check it out. If you have opinions, would be very nice to see. And thanks.
Hello, nice to see you. My talk will be somewhat also cover serialization. My proposal. So my proposal is to have some framework for serializing kernel structs. It's a sort of common framework to make version structs with describing their fields and sort of field. It's produce field-aware format when we can describe what part of struct we want to preserve across left update and what part and what part we don't know. We don't want to restore. We just skip it. It's sort of description based, meaning we have describe structure with fields what we want to preserve. So here is a simple example. In case we want to preserve struct A, like in here, we propose we add some description like a state which has version ID, ID of state, minimally supported version, and set of fields which describe what part of struct we want to preserve, and it works by storing offset of the fields. So we can have general code that knows how to copy these fields and copies them back on restore. So binary format is kind of something like this. We have some header with probably version of format, and the next thing is state ID, which describes what kind of struct this is. For example, this could be a PCI struct, VFIO, memfd, or something else. Instance ID describes, it specifies concrete object of the structs. For example, for PCI device, this would be probably PCI ID. For lower file descriptors, this would be token, and the next there is size of data, and the last goes the fields itself, so the data. The v3 is on LKML is kind of more like a proof of concept. The plan for the future is to add more real users, like probably mostly on Lua side. This would be Lua file headers that describe headers of Lua of D, global state sessions, and I also want to drop some stuff to make it simpler, because there was concern that we don't need like versions fields, specify version for each field of struct. So this could be added later if we find it's useful. And one part is the struct focus approach is not always work. For example, things like memfd, they have a very complex state. It's scattered across different structs like struct file, address space, mapping, and so on. So it's not feasible to store them to describe the whole state as struct. So I also want to bring up discussion about what should we use what type should we use for state ID. For example, Lua is currently heavily obsessed with strings. I personally think that strings are kind of more for humans, and we have here machine talking to machine, basically. So we probably don't need strings, and it should be faster, and maybe it's over optimization, but it's kind of simpler to use also because integer is it's fixed size. So the idea of state is that we instead of using string like memfd or Lua FLB, we can have enum that have value for each string. Maybe someone want to add something about this, have opinions?
I mean, maybe can you hear me? Yeah. Okay. I mean, yes, we chose to use strings mostly, but I mean, U64 can also work, it's just not as descriptive. And the strings that we use, they're very short and they have a fixed size. We like for every version we specify the maximum length for strings because we didn't want to have this weird situation where with unbound preserved data just because of too long versions. So the versions are not too short. I don't remember, but it's 48 characters, but also not too long. I'm not sure that it's going to be a performance problem unless we have thousands and thousands of objects that have to be checked. If that's the case, then can help.
I think the string though is unnecessary. Like it's very easy to just write we can put the enum in a UAPI header, and then it'd be very easy to write a routine that converts those enums to strings for anytime we need to print. So it does make us have to do string comparison during boot to do all the version matching, and that could just become an integer comparison. But I agree it's unlikely to be really visible.
Yes, my point is that we can do like integers inside of string, absolutely. But I'm not sure that it's going to be a performance bottleneck.
I want to talk about something different from strings. So going back, you mentioned that memft has complex structures, and it's either that you'll find it difficult to use with kstate, but I think memft is probably the simplest thing.
I mean the state of memfd itself, like it's scattered across different part of kernel, like inode address space. So if we go into struct-based description, we would need to describe inode also and address space and things like this. So the preserved part is quite simple, but I mean it's we shouldn't describe it.
So my point is,
like
compared to IMMU, HTLB, PCI, anything, I would bet that memft is a lot simpler. So if we can't use this for memft, I don't think we can use this for the others as well, right? Because I wrote the huge TLB stuff, that is a lot more complex than the memft.
We can use it for memfd. We just don't need that part that.
But that is the only stuff that memft has. The only other thing it has is like file position, and size, like which are pretty simple, right?
Yeah.
So my point is like we need to see how it works in practice, and if memft is too complex in practice, then I think anything else is going to be even harder.
It's not too complex in practice. It's just it's not going to use that part with describing fields. It's basically will be one blob instead of fields. So it's simpler.
I think at some point we discussed that you can give it a try of porting memft to kstate. Maybe that sort of helps us see how it plays out. I think that would be really great. Like if with the next series, if you can port memft, so we have a real example, that would be really nice.
Yeah, probably next year. So another thing is also instance ID I want to discuss. So instance ID is ID of specific particular PCI device or file descriptor and so on. So we currently use, I think we use EU64 token for FD, and I don't remember are we using strings for something, but I was thinking maybe we can generalize it and use one type all the time, or should we have support to different ideas all the time? So, for example, sessions using strings, and maybe we can. What's your thoughts about using also int for sessions instead of strings?
In this example, I want to see like that specific object, like a particular PCI device here. Did you mean it's like instance of like a struct PCI def?
Yeah, it's like instance of PCI def that is concrete PCI device with. We can have many of this. So ID describes, but it's probably will be PDF. Yes.
And then this like for example, if I have like many these struct PCI def objects in my running kernel, then they are all at each one is going to attach one kind of like a case that metadata on top of it.
Sorry, I didn't get it.
I mean, it's like if I have like a lot of like this PCI device objects, so they are going to, everyone's going to attach one case that information of it.
Only the ones that we preserve. So yes.
I see.
I don't think we have. I guess we should use like solving problems to decide to do these things. I don't think we have any problem that would be solved at this point by like using a U64 for each of these different type of identifiers. So
it just simplifies eventually coded.
So just imagine this: session is like you have a fleet, you have millions of VM. Has some kind of identifier, and the identifier might be longer than U64.
But I was thinking in my head, design was that we have, for example, some user space that controls live update. It creates, for example, zero ID memory user space where it stores its states like running VMs and some user space stuff that needs that manages VMs on the host.
So by having part of this session, you can have like a unique namespace that you guarantee that there are no collisions.
Yeah, but you can do this in special, for example, zero ID memory block and store it using like master ID.
I think strings are also a lot nicer for debugging, right? So you would like your VMM can name things, and when you gotta debug something, you can read that this is my memory FD and this is my VMM's state FD instead of a number which makes no sense when you're debugging. So Okay, hello, I'm back again. Now I'll talk about MemFT preservation using Lua. So we started MemFT as the first user of Lua. It's memory, so it's probably like one of the more fundamental things that you probably want to preserve over a live update anyways. And this talk, I originally planned to talk about the shmem stuff, but it's merged in mainline now. It's relatively simple. You take the file map, list of folios in the file map, you dump them in an array, and you do a bit of special sauce for setting up the folios in the right places and so on. But recently I sent the huge TLB patches, and I think they're probably a more interesting topic for this talk. So I'll skip over. If you want to go look, we have it working, go test, and yeah. So the next step of the MMFT, so you can have two types of MMFTs. You can pack them with SHMEM, which is like your normal folios, or you can pack them from huge TLB, which is your huge pages, including gigabyte huge pages. Huge TLB comes with its own set of challenges because it manages it's in a way like its own memory management subsystem. So it does everything differently. And I want to talk about some of the challenges that I ran into during that work. And I sent out the RFC a couple of weeks ago, so it's out. You can go give it a try. It works. I've tested on x86, and I can get 1 gigabyte huge pages being preserved. So I'll discuss the challenge, and then after each topic, I'll open the room for discussion. First problem that I ran into when working on those patches was pre-allocation of huge pages. So how huge TLB works is you specify on the command line how many huge pages you want, and then early in boot when memblock is still active, where you can reasonably find contiguous chunks of memory, it allocates the huge pages, and then it goes and buddy comes up and the whole MMInit happens. So let's say you have, but this sort of has a very weird interaction with live update, because let's say you have a 100 gig system, you have 91 gig huge pages that you need for backing, let's say, guest memory, and or backing something else. And let's say you preserve 5 of those with Lua, right? We can do more, but I guess 5 is a nice example. So when you do this KHO boot, 5 of the huge pages are already KHO preserved as part of Lua. And then when the system comes up and if it goes through the normal initialization path, it's going to allocate 90 more because that's what it thinks it needs. And then when you restore the file, in the end, you end up with like 95 huge pages, which is more than what you need. And maybe your other process is and you run into problems. So one of the ways to solve this problem, and this is what I originally experimented with, was preserve the entire all of the pages in an etch state, right? So if you're preserving any file of, let's say, 1 gig page size, you just preserve all of the 1 gig pages with KHO. So the next time when you come up, you can just say, okay, I came up from a live update, huge TLB is involved. I just keep allocating the boot time memory, because you know that once Lua comes up, you're going to get your huge pages and you'll be in a good state. But it turned out to be more complicated than I thought, because the thing is, once you serialize, the state can't change from under you, and there's a lot of ways huge pages can move around, right? They can be added by sysfs, they can be removed, they can be demoted, there's compaction, migration, and so on. And the changes ended up being very invasive into core huge TLB. So I think it was people already kind of don't want to touch huge TLB too much. So I thought that's the approach that's not going to fly anyways. So I tried the other thing, and I was surprised how simple it ended up being. So what I did was just, when a file is preserved, it just counts, adds the count of the huge pages to its etch state. So like each etch state's get like a counter, and you just add, right? So for 1 gig, if you have 5 pages preserved, you just add to that. And then on the next boot, huge TLB reads this data early in boot and figures out how many it needs to allocate, but it's just subtracting. And a bit of accounting needed, but it turned out very surprisingly simple in the early boot paths. So yeah, you need to play around early boot allocation, but everything else becomes a lot simpler. And this is the way I used for my patches, and I think it's in my opinion, the way to go. But I want to hear opinions if people have. Okay, I hear none, so...
Makes sense, yes.
Okay, so I'll go to the next challenge that I ran into, which was this weird interaction with KHO Scratch and huge page allocation, and that's sort of independent of Lua, actually. It's there even now without the huge TLB stuff that I have. And what happens is 1G huge pages need to be allocated before buddy. So they are done when memblock is active. On x86, this happens in setup arch, but Mike is telling me I should get rid of that. So I'll do that, hopefully. So what happens is, when you do the first boot, everything is fine, right? So you get your huge pages, you get your scratch area and everything. But on the next boot, Memblock is in a scratch-only mode, so it's not allowed to allocate from everything outside of the pre-reserved KHO scratch safe area where we know there's nothing, right? So now memblock is in scratch-only mode. You try to allocate 90 gigs of memory, or scratch is probably not large enough to have 90 gigs, right? So allocation fails, and you basically boot in a system with no huge pages. And this happens even if you're using KHO for, let's say, reserve mem, right? So if you want to use KHO for reserve mem and you want to do huge pages, you can't do that. So option 1, disable scratch only mode a little earlier in boot. This would mean, so what happens is in Core init on ARM64 and hopefully on x86 soon, you do huge TLB allocations, and then you initialize KHO memory, and KHO memory init sort of reads the set of bitmaps that mark which pages are preserved. And then memblock free all eventually disables the scratch only mode. So it's like at the very end when we disable scratch only. What I propose in my patches is to move the KHO memory parsing earlier in boot. So on x86, this goes in set apart for now. But essentially, you parse all your bitmaps, you set up the memblock reservations, and then you immediately disable scratch only mode, so that when it's time for huge page allocations, they just go through normally, and they'll actually succeed. It mostly works. So this is like some x86 special sauce, but mostly works. Problem with that is, like, there's been ideas floating around to improve KHO performance that want to move the scratch only until buddy in it. So maybe it plays around with some of those, but maybe for now it's fine.
We might want just split KHO init to the part where it does the bitmap and the reserves memory.
Mhm.
And I don't remember what happens between huge TLB init and the free all. The idea of having KHO memory init as close as possible to free all is to reduce overhead on memblock that's not scalable, right?
But doesn't really add any overhead, because
So
you're adding the reservations
No,
anyways, right?
If you have all the reservations early,
Yeah.
then every other reservation takes much more time.
Yeah, okay, fair enough. I see.
So I don't remember what happens between huge TLB init and the
There's some
memblock
functions,
free
but yeah,
all.
yeah.
Probably it's only page allocator and slab, and that doesn't really matter.
Mhm.
But in general, this makes sense.
Okay.
Yeah.
I see. So I didn't list this in the slides, but there's another thing we could do is we leave memblock scratch on, but we add a special allocator for just huge TLB, which can read the bitmaps.
I mean, if we consider only gigabyte pages, then it's very easy to distinguish them, right? They have
Yeah.
this high order that is
Yeah.
used only by huge TLB. But then if we have 2 megabyte huge TLBs, then that order can be reused.
Yeah.
Like other folders. But yes, but
And
that
that
would be-
probably has different sizes as well in the middle.
Yeah. But I think so. But what I was thinking is another thing we could do is this huge TLB boot mem alloc. We add like a new memblock outside scratch or no scratch allocator that parses both the bitmaps and memblock reservations and finds out like the space in between. Maybe that works.
It will be even slower, I think.
Yeah, probably it will be very slow. But if it's 1 gig huge pages, I'm hoping you only have to do it like a few hundred times. Yeah. Okay, the other option that I explored was that makes this thing go away is if you preserve the whole edge state, because then you don't have this problem anymore. You're just not doing any allocations early in boot. But it's, as mentioned before, it's complex, it's invasive to HTLB, and if you're not preserving HTLB files, you still have this problem, because now your edge state, FLB state doesn't exist, and if you're just preserving, let's say, IMMU or VFIO, you still can't use huge pages. So I don't think this works, but I listed it just as a thing that I experimented with. So any comments on this before I move? Okay, so third problem is early access to Luo data. So these all allocations happen before Luo is initialized. So you would need, but we want to know, for example, how many huge pages are coming for each edge state. So you would want to go and fetch the data somehow. But usually, like the normal retrieve path that deserializes the state takes logs. It needs malloc. It needs.
It doesn't. FLB was specifically designed to be accessible very early. You can do the retrievals and do the callbacks. It's fine. It's just going to work.
It takes a log at least.
But it's always available, right? I mean,
But before shed init, you can't take mutexes, right? I thought.
I mean, I don't think so. It says it should be fine. Huh?
Okay, maybe, yeah. I thought before shed init you can't.
I mean, we can, of course, it should be fine, but if necessary, we can have like a special interface that is exactly the same as regular FLB, but without taking logs, because there's like no other CPUs at the time.
But then you expect the retrieve functions of FLBs to never allocate anything.
That it's you implement the retrieve function. You are the handler.
Okay. Yeah. Okay.
You know when this retrieve is called because it's up to
yeah,
you.
that works. Okay. But if you have like a two-phased init, like you want to have like you want to split up early boot init and late boot init.
It should be fine. Again, it's your logic.
But you won't. But you can't call retrieve twice, then, right?
You cannot call retrieve twice.
Yeah.
Yes, it's,
So
it's up to
maybe-
you. In the early boot, I mean, if the way FLB is implemented, you have retrieve once.
Yeah.
During like whenever you called it the first time, and then you have access to that global data that you preserved across the reboot and do whatever you want with it.
Okay, that works, I think. Yeah. What I ended up doing for the patches was a sort of a read-only access function, which is like incoming early.
Yeah, I don't think that is needed. I looked at that, so that I think that you should just use FLB directly, like the way it's implemented. It should just work.
Okay, so I'll try the mutex stuff, and if that's not a problem, then yeah, I can use that. Yeah, that's all I had. Any more questions? Okay, then thank you.
For the slide, so the slides here, you can either mouse or arrows. Oh, okay.
Hello, I'm Jason. So today I'm going to talk about the KX Hanover, the KXO, the performance improvements that we just made. And I'm going to present our talk in like 3 parts. So I'm going to talk about like what we're having now and what kind of improvement we did for the next step. And then I'd like to get some ideas from you guys, like what kind of like long-term improvement and optimization that we can make. So let's start with like what we're having now. So the KX Hanover is already in the main tree, like I think 16. And the idea is like the KX is try to preserve the memory on your host across the KX reboot. So the new kernel can become the piece of the memory that your first kernel preserved it. So obviously, there's some like key use cases. So like Pasha just presented before, KXO is one of the cornerstone of the live update. So you can like preserve your VM's memory across the KX and also some like a device driver status. For example, like you have some DMA buffer you want to preserve across the KX, then KXO can do that for you. So currently we have some like a bottleneck about the current KXO design. The first thing is we call it stateful KXO because like we have to maintain some we have to keep track the memory you want to preserve, right? So hey, this is the physical memory, that region I want to preserve. Then I have to keep track that, and then the memory I have to keep track that, and then finally we have to call like an explicit finalize function to like serialize all the memory we have preserved it and make it as a linked list, pass to the next kernel. The reason we have to do that is we keep track all the preserved memory address in an X-array data structure. And this is not good for passing to the next kernel. For example, this is a public data structure. So if people change that internal memory layout, the next kernel will never know that. So we need to have a stable data structure that we can pass from first kernel to second kernel. So that's why we need to serialize all the preserved memory into a linked list here. So the problem is, so if we have, now imagine you have a lot of pages that are preserved in a cache, then at the filelize moment, then you have to serialize them one by one. So this is like a linear operation, then it can be quite costly. And also we have to maintain this like state machines. So we need to know, okay, we are running the cache. Now we are in the filelize stage. Oh, something's wrong happened. We go back to abort the operation, or the user space can cancel us. We have to maintain this kind of state machines. It makes this stateful cache harder to manage. Okay, this is what we're having now. Any questions so far? All right, then I'm going to talk about the recent improvement we made in the cache. And this is already in, I submitted the patch set. So advertisement here, please take a look and review that. And then we call this a solution, the status cache. We try to address the problem we just taught before. So first thing is, the main concept is now the tracking in structure is the handover structure. There's no longer an intermediate bookkeeping data structure for keeping the stuff and then serialize that for the next kernel. So the structure here we are using is a Radas tree, like a customized Radas tree. So we get this idea from another JSON, and then I will talk about this structure a little bit later. But the whole idea here is we are replacing, we are using this Radas tree, replacing our internal tracking structure. And the handover passing now is become a constant time operation, because what you want to do is you just save the memory address of your tree root and put it in the device tree and pass to the next kernel. So this is the things. So there's no longer, just because there's no serialization anymore, then of course you don't need to call the filelize. No filelize, then no state. So this is the status cache we are recently proposing.
In a different kernel version scenario, how do you make sure the FTD is compatible? Assume it's a big kind of kernel update.
Yes. So I didn't put this FTT format in this slide, but but we do have an ABI specified in a header file. So this is the memory layout of our data structure here. In this case, it's our Radas tree. So yes. So also, if you change the memory layout of this data structure, of course, the next kernel will not know. Let's go back to our previous a discussion. How can you make a version of this? So right now we are using a special tag in the FTT called a version, or we call it compatible version. So every time if you have to update your internal structure, you have to change that version as well. Yes, this is the way we are doing now. Yes. So yes, over there.
So I think we should mostly care about performance of restoring and the finalized part. Does it benefit for restoring, make it faster?
You're right. So that will be the next pass in the discussion. You're right. Yes. And yes, before we go to for the next one, any more questions? Okay, Pasha.
We need to preserve some memory during blackout window, so high performance preservation is also important. After finalize, you cannot preserve.
So I am going to talk a bit more about this, our RADAS tree data structure. It comes with like two parts actually. So this is actually like a RADAS tree underneath, but the point is like how can we put the tree, of course, can save the physical address of memory, right? Of course, but how can we put the the page order information in the tree without adding extra overhead? So the idea is we encode the page order together with the physical page address and make it as like a RADAS tree key. So we call this key encoding. So you use this key to traverse your RADAS tree, then and preserve both a page order information and also the page address. So and then you will see the tree layout is quite simple. So each intermediate node here, is a table. So each items in that table is going to point to the next level of the RADAS tree node, and each node here that we specify it as a page size because that we want to because all the physical memory here in this tree will pass to the next kernel as well. So each node is in one page size, and the leaf node is it's a bitmap, and one bit is going to represent one page the client preserved as to preserved. So this and then so the nice properties of this structure is so now you think. Let's give a very simple example. Let's say you preserved a lot of high order page. Then if you go to this key encoding scheme, you can imagine we have a lot of a zero prefix in this key, right? So if you have a lot of zero prefix in this key, that means from the very top level of the key of the tree, you go 0, 0, 0, 0 over there. They all share the same path until the tree leaves. So you can actually save a lot of walking and also storage, of course. So this is a nice property of this RADAS tree. Okay, of course, new design, new architecture, it comes with some new challenges. So just like the previous question, so we will face some a new restoration bottleneck. What I am seeing now is the current form, in the patch I proposed it. So the KHO need to walk the whole tree in the early booting time. Of course, because it need to restore all the memory, reserve the memory in the mem block in the early stage. So you have to walk the whole tree and go to the mem block and reserve those memory in the mem block. It also make use of the page struct to put the all the information in the page struct. But this poses another problem is it assumes the page struct is already initialized at the moment. Then and in some a very large server which can have a large amount of memory, initializing the page structs can be slow. So there's a feature called a deferred initialization. But in this case, because the KHO is depending on the initialized page aways in the early stage, it just cannot use that deferred initialization. Then push.
But that deferred init is a problem with the current as well. I don't think that's a downside of this radix tree.
I think, yeah, it wasn't very clear, but apparently this whole slide is unrelated to radix tree. It's the problems with the existing KHO, and exactly the same problems exist today and with your radix tree.
Right. As long as you have to like access the page aways during the early boot stage, you will still think this will. But why I put this after the radix tree, because I have like some things like in the next slide that may be related to the tree things that make the things a little bit more complicated. But yes, now we are still facing this issue. We cannot use the deferred initialization. So so this is one things I want to hear the ideas like how can I fix these things. Then of course I have some like idea. So the one reason why we want to have the deferred initialization is at that moment the SMP is already enabled, so we can parallel. We can parallelize the tree walking other stuff. That's but right now we cannot. So I want to split the. I want to decouple the physical restoration and the metadata restoration. Metadata restoration here at particular means the page order information preserved in the radix tree. So why I said the radix tree make this thing a little bit more complicated, because now we have, when I walk the tree, I can of course walk the whole tree, but when I start with the tree, I don't know the page order of that particular address. Yes.
I think you do it the other way around. So you do normal pages, and then so if you're setting up memblock reservations, then what you do is per order you look at its children, and then it's faster, right? So for this order, I can find out all the
yes.
So doing it the other way around, I think is.
This is the very first version I proposed in the RFC, but it costs more like storage usage. So
no, but the storage stays the same. Like you basically take the original key, and then with that prefix key, you can look out what subtrees exist.
But now here is the same. I think like because the number of the order is a constant, right? I can still like exhaust the
But that's
order
20 or like I don't know. That's like 5 or 10 operations per.
I mean, that's why if I can like decouple the parallel walking, that will like help these things.
But you'd have to do this for each page. Like, are you gonna do this for each page? Like, you're gonna test all orders for each page?
No, you test each order.
Okay, maybe I don't understand, but.
But that's why I'm saying maybe I can like do the things reversely, store the order instead of the page offset. I don't know. Yeah.
Sorry to cut you off. I think also storing physical ranges in memblock doesn't scale if you have any fragmentation or any sort of sparse allocations. Like it doesn't scale at all. So if we care about performance, we probably want to get rid of memblock reservations.
Yep. Okay, so I think this is the time. So if any more questions, please like find me offline. Thank you very much.
All right, that's me again. So I want to talk a little about the blackout reduction. So I actually want to like give some thoughts about how the blackout can be reduced, how we can quicker reboot the machine. But it's more actually brainstorming. I want to have feedback as well about what we can do. So live update is not interesting unless we can reboot kernel very, very quickly. So if we can reboot under a second, that's perfect. But if it's longer, then yes, we do not destroy the user space, but still we get timeouts and we get complaints from the customers. So I mean, this is Nana Banana. It's like it's very good. Okay, so I'll start with the shutdown. So during shutdown, we've done some analysis about what is happening, and shutdown is pretty quick, but there are two things that happen during shutdown. So we have device shutdown callbacks, and we have hundreds of devices, and then we have the reboot notifiers. And we found some random slips in reboot notifiers. We fixed those during the device shutdown. We also found some slips that we can avoid by simply preserving those devices. So that's not a big deal. But I think one way to speed up device shutdown is to parallelize, because during shutdown we have other CPUs available. It's not like we are in a single thread that we have during early boot. So we should use those other CPUs. And the device shutdown parallelization has been proposed multiple times. So I added 2 links, and one of them, this version 10, is pretty recent. So hopefully that patch series matures and then finally lands. So that would benefit. And I think notifications during the reboot notifiers might also be parallelized. I haven't looked into that, but I suspect that there is no reason why some of those cannot run asynchronously. So during purgatory, that's time between kernels. We do several things. We do image relocation. So the kernel is during kexec load, we load the kernel image into memory. But then during purgatory, it's right before the purgatory, but let's call it purgatory time. We relocate it to its final destination. So we parse the ELF data and then put it into where those images have to be located. And then we perform also checksum, and that checksum is quite expensive. It takes about 0.3 seconds. And then during early boot, again, this is also not strictly speaking a purgatory, but we do the decompression. So on x86, the BZ image is compressed, and we first do self-extraction, and then we start booting, and we found that to be also quite expensive time-wise. And by the way, all of this doesn't have like a very direct way to measure, because no clock is working, so we have to implement some specific TC-based clocks that are available during this time. So my suggestion is disable checksum. There is no reason to do this checksum during purgatory, at least I don't know, during live update. Or do the checksumming before doing the kexec jump, so just right after load. The second one is we can avoid relocation. Kdump doesn't do the relocation. Kdump loads the next kernel right into its final destination. So we can do that as well, and optimize the purgatory so that nothing happens at all. And regarding decompression, I don't know, I haven't looked at this,
Sasha?
but yes.
Look up. Hi. I think for the second point, I remember I actually fixed that a few months ago.
You have? Nice.
So I don't know if it applies to all cases anymore. Like it might only be in certain loaders, but I definitely did put a bunch of logic into the kexec logic, so that you completely remove any copying whatsoever. So that should be there now. Second one.
So we don't do relocation anymore. Is that
you have the option not to do relocation anymore?
An option not to do relocation, and how do we specify an option with exec file load, because it doesn't take flags?
It should be on by default. Take a look at the code.
Okay, this is very nice.
It's
Yes.
a negative option, right? I added a flag, but which was broken by the way at first. I added a flag to disable it again, but the default should be to directly load straight ahead if you don't have anything else. Say again? Wait. Oh yes, it does need CMA in order to do contiguous
you would need
allocation.
to pre-reserve some memory, of course, where to put it, CMA. So
Yes, it does. There's like I did CMA enablement for that KXX piece. Just have a look.
So no new kernel parameters, like just CMA pool that is
just
big
work.
enough, right?
It should just work as long as you have a CMA region.
Okay, this is perfect. So checksum disabling optional that would completely eliminate purgatory.
That one is completely skipped because you don't even run the purgatory.
Yes, because you can do checksum, like you can do pre-checksumming if you are paranoid.
Right, exactly. The third one is interesting though, so keep going.
So I mean the third one, I don't have any suggestions except for like pre-decompress during the kexec load, and I haven't looked into like what it would take.
I mean, at the end of the day, there's lots of different options here. We could even go as crazy as having a different image target, right? Where we don't even use any of that preloader. We just basically teach, like, say, for example, the KXX file loader or our user space KXX loader to directly speak the internal protocol that, like, the preloader to the real kernel was speaking. I don't know, but all of that code that runs in real mode ahead of time that just basically does nothing but assemble a couple of like memory tables from things that you already know ahead of time anyways. It's completely useless. Plus the
And redoes KSLR.
And KSLR, which again you can just do ahead of time. Like all of this is something none of this needs to happen.
Right. So thank you for fixing the relocation. This is perfect. I really was looking forward for that to happen. Yeah, if you can fix the pre-decompression, that would be.
The compression is the hard one, right? And the relocation didn't buy me this much. I think it was like what, 5 milliseconds. But
depends on depends on the size of the busy image.
Sure, but
and on initramfs, and
it was completely negligible timing.
On ARM or
on ARM.
Yes, because on ARM I fixed the relocation speed by making it like to use virtual addressing. But it's still slow. It used to be very, very slow with the physical addresses. Like that relocation function was very slow. Okay, so the next is boot optimization. So to boot quicker, I mean, one way to boot quicker is actually if the hypervisor itself is configured correctly. So ideally, hypervisor shouldn't have any device drivers. Everything should be passed through into the guests, and so the fewer device drivers we have, the faster we can boot. Also, of course, this is common sense, but there shouldn't be any I/O during the reboot. So no disk access, no network access. And hopefully also no console writes, because console is very slow. So if like the console should be in a quiet mode, and then also do some other things such as deferred struct page initialization, which we've discussed before, but it's incompatible today with KHO. So we want to reboot faster during live update, and then we have to disable deferred struct page initialization. So that's not good. Okay, so another thing that we need is we need to a very precise way to measure the live update. So that's something that we would need to add probably to LUO to measure the blackout of session lifecycle in something very precise, such as in nanoseconds.
I thought ftrace could do kexec instrumentation, right? Maybe we can use that.
Is it fast enough? Like I'm not sure. Can you
but
get
I think the instrumentation you would do in a test environment anyways, right?
I mean, as long as instrumentation does not reduce the reboot performance, because we don't want to add overhead by actually adding the instrumentation.
But you could do that in a test environment when you qualify.
Test environment or not, but you want to know the exact downtime that happens during in production.
Mhm.
And hopefully, and you also want to get that feedback from the fleet. Like if something goes bad, if some updates take longer than expected, you want to know about that. So the telemetry should be available all the time.
Yeah, okay, makes sense.
There is a kexec and ftrace and kprobs boot chart and boot time that stores it to pstore afterwards. I don't know how much will it slow down, but it exists anyway.
Yeah, I understand. But what I'm saying is that I mean, if pstore solution does not slow down and can be part of the production and provides the time in nanoseconds and maybe even provides this like from very early boot when sked clock is not even initialized.
You won't know until you measure, right?
So, but my point is that we need some really good telemetry for live update, and that's.
Yes, I agree. However,
For continuous clock, that's
agreed. However, the question is also where does the telemetry live? And the one that you mentioned here, vCPU pause to vCPU resume, it's inherently a VMM property, like a user space. Your user space application that drives KVM today, right, is the only entity that really can know when it pauses those vCPUs and when it resumes those vCPUs.
That is correct. That's a problem if we measure vCPU stop to vCPU resume. I mean, of course, from KVM we can also do the measurement in kernel. It's not as good, but then we also have these sessions where we have the preserve and finish. So it's not the total blackout. It's a little outside of the blackout, but still it also gives some time.
You want to capture all of these, right? And you want to be very conscious about where you're putting that telemetry, and ideally have a way to combine them. But you need to enable your user space applications to at least emit telemetry for yourself.
Yes. The VMM has to keep its own tracking regarding the blackout. Absolutely. Okay. So, and then there are some ideas that how we can improve the blackout even better. So this multi-kernel, or the way I've been calling it, multi-OSing partitioning, is one way it was proposed. Devirtualization is another when you start the hypervisor in a VM and then devirtualize. So disadvantage of that is the hardware description is very hard to keep track of. Then reuse the hibernate resume kernel functionality where you hibernate VM once. Not VM, the hypervisor. So your fleet is pretty much uniform. You have just several SKUs of different machine families, but you can pre-boot the next kernel on one of them and then do the hibernate resume across the fleet. Might be faster, but the problem is hibernate resume does not have any kind of API guarantees about the versioning update, kernel version update. So it's probably not the best idea. I think one of the most promising approaches is just to keep vCPUs running during the live update. So basically, when we do LUO preservation, we give LUO KVM FD as well and tell it just keep it and keep the vCPU running. And what needs to be solved to keep vCPU running across the live update is how to handle the VM exits. But I think that problem is solvable for some VM exits that are simple, but it's harder to solve if VM exit has to go to VMM, so the VM has to be configured not to go back to the user space VMM, or vCPU gets stuck and waits until we are back in user space and resume. So that's the idea. Any thoughts? Yes. Yeah, I was planning to do a discussion, but all right. Thank you, everyone.
1, 2, 1. Alex? David? Do you hear me through the... Do you hear me through the... Yes, I hear myself. I switched the mic, so we now have two.
You might actually have implemented a new version and do a selection like from the old version to the new one. So that means that I am compatible. I have a different version, but I'm compatible with the later versions. Just want to make sure that this is a thing that
So right now, it's saying.
let's start there.
Now it's done. Yes, exactly. We had it out. So I saw it. Like when I'm preserving, this is right? Right? You say serializer position becomes I'm coming in and preserving from you, and for each one, I set a custom flags. And then it says the stuff. This flag is a bit in the. Yes, we also have that. In the so you can say that if one folio is pretty set, is that any this is pretty nice. Yes. And it won't be more complex than this. You will basically still want entry for the folio. I even consider you might just Yes, yes, actually, and basically, and then you do the scale. So my point is that one of the important scales is. No. The K plus the B line option, it should become a library kind of. But I can make sure that yeah, sure. So the question your version is fairly unique. Because so it means that you don't have a linear number and basically you have version 1.1, 1.2, 1.3. And you have like for like business reasons, this is justification.
Say that was lunch. That was the lunch they provided. And the library will come up with eligible. Oh, I expect because when you go working, you have a new but when you get it's really good. The new kernel should already know what you basically just say, oh, you have to that's a decision what you so you're gonna have that logic and not still right. So you are trying to reach and then you know the old and then you would process oh, it doesn't have this basic, the same as you're saying, but it would be much nicer because you actually switch and then well, instead of potentially losing its bottom level, and you just feel heavy shape of all the exercises that this you don't need to I know you're gonna need like case understanding and if you might just click on and then the library is also information. So So you're constantly writing organization of each truck class, for example, array of code, and then you write a truck class. Especially if you go Also, I think your argument is I can understand. I have a feeling that you get a lot of information now, maybe less. Because right now there are no one so.
One, two.
Okay, we're going to get started. So my name's David Matlack from Google, and I'm here to talk about supporting VFIO devices during live update on behalf of myself and my colleague Josh, and then Vipin, who couldn't be here today. So our goal is that VFIO PCI devices that are passed into VMs can continue running uninterrupted during a live update. So from the guest point of view, it just looks like during a live update that the VM was paused for a couple of seconds, but all the devices passed into the VM, which may be GPUs or NICs, kept running. So we don't want to be resetting the device on the host or dropping DMAs from the device or quiescing it or coordinating with the guest OS So any in-flight IOs that the guest posted before it was paused should be able to continue running. And if it's a NIC and it receives traffic, it should be able to post it into guest memory, etc. So this is a big undertaking and requires changes not just in VFIO, but in IMUFD and the core PCI layer and the IMU drivers, etc. So to sort of get there, we have this roadmap. So we already have KExec handover and live update orchestrator in place. So the next step is just VFIO PCI CDEV file preservation without actually preserving the underlying device. So this just gives user space a way to preserve, take a VFIO CDEV FD, give it to Luo to preserve, and then after a live update, get the file descriptor back from Luo. That way, the rest of the device preservation has a concrete user space triggerable thing to key off of, as opposed to sort of preserving bits of device state that can't be triggered in any way. So the first version of that series is out. Sort of the next step after that is preserving the DMA mappings for those devices by preserving IMUFD and its VFO PCI device attachments. The next talk is going to cover that. Then, or sort of in parallel to that, we need to preserve a lot of the core PCI state, like the addresses of the bars and bus mastering enabling on parent bridges, things like that. And then finally, once all of that's in place, then VFIO can keep the device in a fully running state and preserve its state, like its virtual config space and other pieces. And then beyond that, we want to support SRIOV, so preserving PFs with VFs and sort of more. So this first step is on the mailing list. Like I mentioned, it just lets user space give a VFIO CDEV FD to dev live update, but the device is not actually preserved. So VFIO in the series still resets and restores the device just before KExec so that the next kernel can receive it in a consistent state. That's temporary and eventually will go away. The series also introduces, uses the FLB support that Pasha talked about so that the PCI subsystem can itself track which devices are preserved. And VFI is using that to prevent user space from opening a CDEV for a device that was preserved, and will be used in future patches for that PCI step I mentioned in the previous slide to preserve core PCI state like bar addresses, and then self-tests to demonstrate end-to-end. So from now, for the rest of the talk, I just have some discussion topics of different problems that need to be solved and sort of what the proposed solutions are in case there's any feedback. So the first is interrupts. So if the guest enabled interrupts on the device, which it very much will, then the device could signal those interrupts during live update when there's no interrupt handler registered. So when we're in the middle of KExec, for example. So the solution we're proposing to start with is that we require user space, so the VMM or whatever's in user space, to disable all interrupts on the device prior to KExec. And this is going to be enforced by the kernel. So KExec will, the reboot syscall will fail, be keyed off of the live update freeze callback if user space fails to do this. So that way it's guaranteed that the device or that the CPU doesn't receive any interrupts from the device during the middle of KExec. And then the implication of this is that user space will need to inject interrupts into the guest after the live update. If it can figure out which interrupts the device signaled, it can just inject those. Otherwise, it has to inject spurious interrupts. Two alternatives to this is you could do the dropping in the IOMU instead of doing the dropping in the device. That doesn't really buy you anything other than more complexity. Or you could capture all the interrupts that the device sent in posted interrupt descriptors if you use that. Yes.
So I assume you mean like the actual MSIX vectors you're disabling in the device?
Yes.
So how do you know that? So since the device is DMAing and it expects to post intro, how do you know that devices won't misbehave if it's DMAing and it's MSIs have been disabled?
If a device misbehaves because its MSIs have been disabled.
Yeah.
I guess that is, if such a device were to exist, then that would be a reason to drop the interrupts in the IOMU instead of dropping them in the device. If you're aware of any devices, such devices, that would be very
Yeah, our GPU is that, right? So for the GPU is we were waiting for the interrupt comes back, so we know the work is actually complete. That's re-injected.
An MSIX is really just a DMA transaction, which means if you have a card that effectively allows your guest to DMA to any address that it has access to, which most cards do, you just basically create whatever DMA operation on the card. You may as well just provide the DMA operation onto the MSIX window, and that way trigger interrupts even through your effectively disabled interrupts on the card. You cannot trust the card.
Yeah, I agree with that. You should block them at the interrupt controller in one way or another.
Okay.
Oh, sorry.
Can we just mask them though? Use PBA and know what's fired, and that would have less effect on the GPU, and then re-inject the ones that have fired?
Yeah, and that's something we've I forgot to mention it here, but that we've discussed.
No, because PBA is an on-card mechanism, so the whole DMA from the card thing will still work if you could. You need to filter at the IOMU level if you cannot accept it.
I mean, I think realistically, guys, we assume that there's going to have to be some accommodation from the drivers that want to support this. And if there's little bugs, like they get unhappy if they get a spurious interrupt or something, they're going to have to get those smoothed out.
This is about, like, for example, what if you're in the early boot phase, you just happen to not have any handler registered? I mean, the alternative is to just not have that issue.
Well, I mean,
basically always allow interrupts even when they're spurious.
This is why you have to block it at the IO menu or the mapping. You have to block the interrupts off because you're not going to be prepared to handle them.
Either block them, or the second thing that you have there is basically to always allow them because they're always posted anyways. Either you mandate posted or you block them in the IOMU. But I think your alternatives are actually the only things you have. Yeah.
Okay.
I'm gonna throw this far.
That's really where you want to talk to your hardware designers. I think IBM solved that problem a long time ago by having mechanism to block interrupt and be signaled that they happen while blocked, which allows you to harvest them back afterwards at the PHB, at the host bridge level, or at the MMU domain level, or at the interrupt domain level, or whatever. So these kind of things can be fairly easily solved in hardware if your interrupt controller is not completely dumb. Fortunately, it seems to be doing send interrupt controllers has become hard.
So this dropping of interrupts at IOMMU level, does SMMU v3 support this? This is Intel specific or?
In the ARM world, this would be masking them in the GIC.
Yeah.
And in Intel world, those GIC tables are effectively in the IOMMU driver for some reason.
No, can't. Yeah.
Well, I'm just stating that on ARM, I think you cannot mask it as SMMU level. It's an MSI write. I think it makes sense to do it at GIC level. That's what Jason just said.
I mean, yeah, you have to get your whole interrupt subsystem in a nice, tidy state so that when you do the K-exec, the new GIC driver, new interrupt driver, new APIC driver isn't confused by what's happening. right? So you do want to do things like clear off the IRTE so that the next instance can turn it back on when it's ready and it doesn't get interrupts that are spurious and it can't handle. Like, that just makes sense, right?
With modern devices, spurious is not the end of the world. So you could over-signal most of the time. It's going to be just fine. It's losing one that's a problem.
So you on the slide you're saying in the current proposed solution you still inject interrupts after live update, right? Which most likely are going to be spurious in that environment.
Yes.
The same goes for the disablement.
Yes.
And I think that's mandatory. You just have to effectively create a spurious interrupt.
Yes, unless you can.
So it's either disable and spurious or always keep it enabled by having a posted interrupt table available throughout the whole process.
Right. Okay. We can continue this offline if I can just get to a couple other topics. Next is bus number stability. So we need the PCI bus numbers to remain stable so that DMAs can continue to be translated through the IMU during live update. But the next kernel can assign new bus numbers, for example, if this option is enabled. So I think just the proposal here is to always inherit bus numbers from the previous kernel when doing a live update, even if that option's on. And that requires some small changes to PCI scan bridge extended.
I think the same also applies to things like bar probing. Right? You don't have to do bar probing, like you don't have to worry about it so far because you're not executing anything that would access the bar, so it's fine. But it's just wasted time.
No, you can't do bar programming because something could be DMAing into the bar.
Oh, because you might have the peer-to-peer DMA. Yes, in that case with peer-to-peer, you absolutely have to avoid bar probing.
Yes. I mean, yeah, that's another thing we'll have to do. Yeah.
For the command line argument, because I think for the live update, we already have a command line argument for that. Can we just like, if we see the live updates enabled, then we always want to have this bus number stability, then we don't need to introduce a new argument.
Yeah, I'm not proposing adding any new arguments, but just if that argument was set, that's an existing argument. If that argument was set and we're in the boot after a live update, then don't pick new bus numbers, just inherit the ones that are there.
Gonna be easier. I must have missed something earlier today. I don't know if you've already talked about this, but how do you deal with the fact that PCI scanning is fundamentally destructive? So the bars get temporarily unassigned during scanning, which is a problem with peer-to-peer. Bus master enable bits can be turned off during scanning, etc., etc. It's a defect of the PCI standard, if you ask me. But we talked a little bit about that in the context of KHO. I don't know if you remember, Alex, but some of the ideas there were to generate a snapshot of the PCI hierarchy in a device tree form, for example, and pass it across kexec, allowing the new kernel to effectively recreate the PCI hierarchy without doing bar sizing and without messing around with the device enable. You can still use normal config space for a lot of things, so you would just pass the minimum across. That's something to think about because fundamentally PCI discovery is destructive.
Yeah. There's going to be a talk that Chris is going to give in 2 talks after this where we can talk more about PCI. So,
and I'm sorry to interrupt everybody. It's time. So we are going to the next talk.
Thank you. The next talk's remote. Sammy, are you
online?
Yes, I'm here. Can you hear me?
Yeah, can you take presenter and then you can.
Take presenter, take presenter. Oh, yeah, here it is. Okay, that works. Hey everyone, this is Sami, and I'm going to talk about IOME preservation during live update. So basically, we want to preserve IOME state during live update so that the devices can keep on doing DMA. The DMA mappings that were set up by the VMM are preserved. There's one thing that I forgot to put in this slide is that the DM mappings that we have, the DM mappings that we are preserving, we have to make sure that the memory that these DMA mappings are targeting is also preserved. So this involves like preserving the MMFTs and all those things. We want to preserve the page tables that contains these DMA mapping. We want to preserve the IOMU device state, and the root tables for the Intel IMU domain IDs. We want to preserve the IMU specific state of the preserved devices, like POS ID tables and other things. So I sent out an RFC for this around in October, the version 1. There was interesting discussion on that, and I have sent out version 2 like 2 weeks ago. And this is already integrated with the VFIO CDEV preservation series that David just talked about. I'm going to go through how it works and what kind of design decisions and basically how it is working, and I'm looking for the feedback on that. So there are a bunch of sequence diagrams. So basically, before the live update, we have to preserve a bunch of state. So the way it starts is that VMM marks the HLUPTs that it wants to preserve for preservation. For this, I've added a new ioctl, which basically can be called with the ID of the HLUPT, and the HLUPT gets marked for preservation. And then VMM preserves the IOMMUFT file descriptor using live update orchestrator. And the IOMFT during preservation will preserve the marked HLUPT by using an API into the IOME core. Basically, it will ask the IOME core to preserve the associated IOME domain. And it will use the generic page table to preserve the page tables. There are a bunch of, so one of the collector walker inside the generic page table, I'm basically using that to walk through the page tables and preserve the pages. All this state is saved in FLB because we require this during the early boot in the next kernel. I'm going to talk about it more later. So this basically preserves the IOME domain. So the next step is the VMM says, okay, now I'm going to preserve the VFIO CDEV. During the VFIO CDEV preservation, the VFIO CDEV would do its device preservation part, and then it will also ask the preservation of IOMU specific state of this device by asking IOMFT. And the IOMFT will basically ask the IOME core to preserve this device. IOME core first checks if the associated IOMU is already preserved. If it is not preserved, it basically preserves it and asks the driver to preserve it. The driver preserves the IOME device state, the root table, the context entries that are associated with this device. This state is saved in the FLB, and then the IOME core asks the driver to save the device state. Here we save the pass ID table and domain IDs. So in my RFC, I'm not saving the pass ID tables right now, but when I send the non-RFC version, I'll be basically putting that in. So once all this is done, we have saved the IOME domain, we have preserved the IOME device, and also preserved the device-specific state, context entries, and everything. So now the preservation part is all done. So now we can basically jump into the next kernel. So before jumping into the next kernel, during the shutdown, we basically clean the root table and remove the context entries that are relevant to non-preserved devices. So only the preserved devices context entries are left. And then we jump to the next kernel. The IOME driver, during the boot, it has to allocate the IMU, initialize the IMU devices, and register them. So basically, it gets the preserved state from the IMU core, it reloads the root table, reserves the domain IDs that are allocated to domains, and sets up the IMU, and then registers it to the IMU core. Once that is done, the IMU core goes through the preserved devices. So at this point, IMU core basically does the IMU probing of the devices. During the probing, it also sets up the domains. So it will go through the preserved devices and restore the IMU domain that was preserved for these devices. And we'll again use the generic page table to recreate the IMU domain and reattach it to the preserved devices. So here, if two devices were sharing the same IMU domain, that domain will be reattached with those two devices, preserved devices. So at this point, the IMU core, IMU driver, it's basically done with the restore part. The domains are restored, the pass IDs, everything is done, the context entries are set up, the devices are attached to their domains. So now all we have to do is basically reassociate this state with the user space. So here, at some point, VMM comes up. It asks the IMU, it asks the LUO to get the IMUFD file descriptor back, and the retrieve of the IMUFD is triggered. During retrieve, IMUFD reclaims the ownership of the restored IMU domain, and also it creates the HLUPT that was preserved earlier. So this HLUPT that is created is immutable, and it cannot get new mappings and unmappings. So this can only be used to basically this basically points to the restored IMU domain, nothing else. And then the VMM restores the VFIO CDEF, and it triggers the retrieve of the VFIO CDEF. At this point, the VFIO CDEF can auto bind with the IOMFD that it was bound with before live update. And this part is actually not in the RFC yet, so this will be added later. And here, the IOMFD also reclaims the DMA ownership of the device that it does during binding. Here, it's a little bit weird because the IMU device that it is claiming DMA ownership of, the group of that device already has a domain attached. That was the restore domain. So IMU core will say that basically return EBZ. So we have to make it live update aware to check those things, do some verification, and allow that basically. So once all of this is done, now the IMFD is restored and the CDEP is also restored. There are some caveats that I'll talk about later, revisit this part. So once all of this is done, the HLUPT is restored, the VFI CDEF is restored, IMFDs are restored, all is good. Now we want to basically finish. But before we can finish, we need to replace the HLUPT that is attached with these devices with a new one, because the HLUPT that is attached right now is a restored one, and it is immutable. It cannot be used. So what the VMM can do is it can cook a new HWPT in which it can put all the mappings, DMA mappings that it require and set it up properly. And then it can ask the IMAFT to attach this new HWPT with the preserved device, with the device that was preserved. So during attach, this attach should be replaced. The IMA core can replace the restored domain with a new domain in a hitless way. So the tricky part is that because the HWPT is not completely reassociated with the VFIO CDEF, the IME core will say that this group has already an IME domain. It will basically return EBZ. So this is something that I will talk about later, but we need to do the replace here. Once that is done, then we will try to do finish. And then LUO will call can finish on all the file descriptors. And the IMFT file can finish will verify that all the HWPTs that all the IME domains that it restored are now vacant. They don't have any attachments. So we won't allow any finish until all the attachments of the IME domains are gone. Basically, the devices that were attached to it are now has got a new domain. It's replaced. So once that is true, then can finish will return true from IMAFT and others as well, and the finish can happen, and then we can basically do the cleanup. The reason we cannot do this before the domains are attached because I think there's a question.
Yeah. So when you replace the hardware page table, you said it'll be done hitlessly, but I'm not sure I understand how that's possible in the sense that there is some window where DMAs can fault, right? It might be a small window, but how are you doing that hitlessly?
Right now in the Intel IME driver, it is not done in a hitless way. Where,
it could
be. Yeah, it could be. We have a proof of concept that I've tested with. Where you basically replace the context entries with a new page directory, and you do a flush, and then basically DMAs keep on working.
So it is currently implemented in ARM already, Vikram. And if you're doing nesting, you have to do this anyway because, and the way it works in ARM is that the STE is mutated without making it non-valid. And if all you're doing is changing the table top pointer, that's a single 64-bit value in the STE, you can write the single 64-bit value, flush the cache, and then the hardware will start walking the new table. You can't restructure the geometry of the table because that would require breaking update.
But you might update the pointer, but you're saying you're flushing the TLBs also. That can't possibly be atomic.
It doesn't need to be atomic. They're TLBs. So if it's not present in the TLB, it'll walk the new table and get the new table's TLB. What we're saying is that if you look up in the new or old table, you get the exact same result because they're equivalent translations.
Okay.
Right. So at no point does the table walk return non-present. At no point does the STE lookup return non-valid. So you never fault a DMA.
Okay.
Alex, so then
I got the mic. How does all of this work with things like, say, credential guard or like the VSM logic that we're going to introduce soon, where you're snipping up the IOMU page tables and remove entries, for example, or mutate them? How are you going to restore all of that state again after such an update? Like you would need to have...
It's the VMM's problem. It has to record all of that and pass it to its next self. It has to know anyway, right? If it has to operate your credential guard feature, it has to know what it was when
No,
it was.
It doesn't today. Like today, it only needs to maintain the memory attributes table for KVM and snip along on VFIO, right? Or it could even, in theory, it could just basically only tell KVM to do stuff. The user space itself doesn't have to have any access protection mechanism.
the way this has been architected is that the VMM has to keep track of all of this kind of state and bring it back to the kernel, because we're trying to minimize the state that the kernel carries across. So any of these kind of features, like KVM doesn't maintain any state whatsoever through live update.
But what I'm saying is, if we want to do that, and we can debate on whether that's the right way or not, but if we want to do that, then this replace and the recreation needs to be a lot more elaborate than what we probably can do today through the APIs, right? Or not?
I don't know. I don't know what your credential guard does, but presumably if you could have created it in the preceding kernel, I don't see why you couldn't create it in the following kernel.
And sorry to interrupt you, folks. We are out of time. Thanks, Sami.
Thank you very much.
Hello, my name is Chris Lee, and I'm from Google. And today I'm going to talk about the PCI subsystem and how the PCI device do live update. And first of all, like, why do we even need the PCI subsystem get involved? It seems like we are only interested in the device itself, right? Why can't we just get the device to do their live update thing and then forget about the PCY? It turned out that it's slightly more complicated than that, like because during this live update and the PCI subsystem, their bus and the device number, they cannot change, otherwise the DMA will fail. And also we need to preserving the bus master bit on the bridge devices so that the device can continue receiving the DMAs. And after K-exact, we also need to change the PCI subsystem that do not do their normal device driver probing, and which can initialize the device and then you lose the device state. And how are we going to do that? It's basically by using KHO to preserve the PCI device state. And the exact mechanism is by building a list of the PCI devices that need to participate the live update, and then by working the PCI bus and using these device dependencies. So a simple introduction to the PCI device and their internal data structures. This is a very basic view of the device. And the in the kernel device tree structures, they have this struct device, which is serving as the base object of all the device drivers, including non-PCI ones, and including the buses. They all have this like device struct. And then this device will also have a pointer, the struct device, point to the device driver. And what interestingly, the PCI device, it's containing or embedding a device struct inside that. And then the PCI device itself also have a driver pointer and point to the PCI version of the driver. The PCI version of the driver itself embed the common driver struct inside. And this is actually not too complicated, but when you get to the buses, and then it's a lot more complicated. But I'm not going to show that kind of dependencies inside here. And then here's the PCI device live update for the device dependencies. The mainly two kind of dependencies we notice. One is that the device on the leaf node, they will depend on their parent to preserve the bus master bit so that the DMA doesn't get interrupted, because the bus master will need to recursively go all the way up to the root bridge to enable this DMA transfer, doesn't get interrupted. The other one, more noticeably, is also the VF device. They would need to depend on the PF device. Basically, PF device are the one that creating this VF device. So you need to preserve or let the PF device get into the life update device list, and they might not preserve the whole PF device, but they need to able to get into the life update device list so that they have a chance to recreating this device during the after the KExec. And then the way that we preserve these devices is we build a dedicated a new list of the life update device. And then there's a certain small structure add to the PCI device struct to track that this device have some life update related state. In the earlier version of the patch, that struct was added to the device struct, but get some resistance. People say that, oh, you're only doing PCI related stuff. Do not mess the device struct. And then that's why the later version will be in the PCI dev. And then in order to get this list, by the way, it's a new list. It's not the existing device tree list for each PCI device, not that list. It's a completely new list using that new life update struct to link them. And then the list was built, it's by walking the bridge downwards, and then to see every device, you give them a chance to mark their parent, and then walk in the interesting order so that you will let, basically backwards, so that you will let the children have a chance to mark its parent and the VF because they create after the PF, so that they have a chance to mark the PF, and then the PF have a chance to mark their parent bridge and etc. So that you will eventually, after this walk, you will construct this live update device list. And then once you have the device list, you will want to preserve them. And in here, they are very uniform, and we are only saving the device, PCI device struct. And then in here, we use array, simple array, and then get a folio, and then remember the size, and then put them in. And then the new kernel, when they boot up, they will actually need to find this preserved PCI device array, the folio, and then they will read the number of devices in them, and then they initialize, they find, basically they will, for each device, they will find, oh, whether can I find this device in this array by using the BDF order, and then they will basically save a pointer to their device struct pointing to these structures, and then they can easily reference the data in that device, in this serialization struct. Is that a hand? Yeah, there's a hand. Microphone, please.
I have a whole list of concerns here. I will start with, you need to preserve a lot more than just the device state. You need to completely inhibit all bar assignment and bridge windows reassignment and resizing. There's a lot more that need to preserve than just the state bit. Secondly, there is an existing mechanism today to create a PCI dev from a representation without probing, which is used by a couple of architectures like Spark and PowerPC, among others. I think there are a couple more, which you can create a PCI device from a device tree, like as in flat device tree. Wouldn't it make sense to effectively serialize your state into a flat device tree and reuse the existing infrastructure on the other side to recover it? And the reason I mentioned that is because you want, in my opinion, you want to go one step further here and generalize in the Linux device representation the ability for devices to serialize into a device tree, whether they're PCI or something else, because you really want to extend that. For example, large storage servers really want to save all the SCSI device state in there, rather than having to reprobe all of them. Otherwise, they're going to spend minutes, if not hours scanning large amount of SCSI devices. And this is just one example out of many. So I really believe that what we want here is a more generic solution at the struct device level to provide hooks for subsystem or drivers to effectively generate a representation that gets preserved and then recover it on the other side, following the dependency hierarchy, which is natural. Most of the time, the natural bus dependency. PFVF, we can have a little special case. They're still kind of siblings anyway. But so this is interesting, but I think it doesn't go nearly far enough.
I mean, you're sort of redescribing Luo, right? Luo is the generalized mechanism for subsystems to store, like your SCSI example. SCSI subsystem should directly talk to Luo and directly store its discovery.
But then you SCSI have dependencies on the PCI devices that they come from. Why do we
the SCSI discovery doesn't need to have any special ordering, right? The normal.
But how do you map a specific SCSI host with a specific set of data that you're carrying across?
That's
it's because of its PCI.
That's what the live update orchestrator subsystem is dealing with. It lets you index your data.
How do we preserve the enumeration stability?
Enumeration stability?
Yeah.
Oh, yeah.
If a device is named device 1, it should continue to be named device 1 after resuming, right?
Yes.
So the one problem is that SRIV devices are, well, appearing after initialization.
No, we're not doing that, right? We're not doing that. We're just preserving the hardware. It's up to the user space to sort out the new names of the new kernel.
Right. So
how can you sort out the PCI device IDs?
Well, the BDFs stay the same. That was the previous slide.
Okay.
But like if that becomes ETH3 on your next kernel, your user space has to figure out that ETH3 is the one that you think it should be. And maybe it's an ETH4 now.
Yes, no, ETH is easy because that is, you can have UDF just renaming it. I mean, everyone is doing it all the time, right? But the SCSI one actually is a harder problem because enumeration is pretty much hard-coded, and you have to space the driver probing in the sense such that you get the same enumeration.
Well, again, you don't care about the user space names. The user space should say, like, I know that this LUN's GUID is blah, so I'm going to find what name I got in this kernel for that GUID.
Right.
Right.
Sure, and everyone is doing that.
If you're building a system around this live update stuff, you have to do these special things, right? It's so specialized, right? We're not, at least I'm not expecting like,
I don't completely agree with you, and particularly the case is not just a VM case leveraging a hypervisor, and the SCSI case, in fact, is often going to be useful for large servers that are not virtualized. But it's exactly the same thing that we want, is to carry a whole bunch of states simply because of the time it takes to rediscover otherwise. Yes, it's not a reliable per se, it's an update of the kernel and the reboot, but it is a fundamentally the same problem, which is to reduce the time it takes, and carry state across. I don't like the idea of creating a whole bunch of ad hoc mechanism for every subsystem under the sun, while we already have a nice hierarchical mechanism to express a whole pile of hardware states. And we already have code to generate PCI devs on the fly based on this. And it would be trivial to add code to do other things, especially since things like SCSI are in fact already well specified, USB is already well specified, etc., etc. It's a matter of taste, I suppose, but I don't like it.
I think you'll find that when you get into the drivers that they're not going to like, there's going to be a lot of special stuff to hook up the drivers, right? Like even a SCSI's case, like you have a SCSI, whatever your SCSI is, you need to carry a lot of information for whatever your HBA is to hook back up to your
and
LUN.
A device type structure gives you a nice key value pair that your outgoing driver can put whatever it wants into, and your incoming driver can recover whatever it wants from.
I'm just saying that it's not general, right? Your driver, whatever your HBA driver is going to have to do, is going to have to understand what information needs to record and record it in its special way.
No matter what, yeah.
However, no matter what. So I'm just saying it's not general. It can't really, it's not really struct device based in a general way. Everybody's going to have to do their special bit. We haven't seen, and here we have to end.
Yeah. Sorry, it seems like I reached to the time's up, and then let's continue offline on this.
Hello, so I'm Evangelos from AWS, and today I would like to discuss a list of bad ideas I had. One was like navigating Tokyo without smartphone, and the other one was trying to cache PCI configuration space accesses. While I can't provide a very good motivation about my choice of commute style, I think I do have some arguments about why I would like to cache the configuration space. And the fact is that modern servers are becoming more and more complex with more and more complex topology with a lot of devices, either in the form of PFs, like we have a lot of GPUs, have a lot of disks, or even VFs, like we have a lot of network cards, again, lots of disks. And when we try to enumerate everything, all of a sudden we end up with a lot of PCI configuration space accesses, both like enumerating PFs and when we create VFs, even though the VF is probing the config space of VFs is quite better. This tends to increase the amount of downtime or blackout time that we're having. So if we introduce a cache somewhere there, we can actually save quite a lot of time there. And if we do that in the kernel space, we get another freebie, is that most of the times these VMMs, for example, the Cloud Hypervisor VMM, they tend to have like a shadow config space. And when you recover from your kexec, then all of a sudden, all of the VMMs try to create the config space at the same time. So a lot of config space access happening there that can overload the VFs, especially like if the PF is a bit susceptible to that. So let's introduce a cache for that. How would this cache work? Actually, it's quite simple. We just sort of inject our cache within the read and write operations. For read, it's fine. We go through the cache. For write, let's keep it simple. Write and validate. Don't try to go through the cache. Try to write straight to the device, but at the same time, validate the cache. We also have added support for resets and how to properly query when device is up and ready after a reset and all that. So our cache is, as I said, quite simple. Exists of the cached values. One bitmap of what we can cache, and what we can cache, we can actually infer that from the spec. We can discuss about in the future optimizations if some proprietary devices, they can have an API to query the cache. I can also cache this kind of registers. And we obviously have a bitmask what is already in the cache. And now where it comes really interesting is what if we actually persist this cache across kexec. That means that most of the configuration space access during boot, we don't need to access the hardware. And I said it is a bad idea, but sometimes bad ideas sort of work. So with this cache in place, we've managed, don't take it super critical because there are a lot of variables that these numbers depend on. We have managed to achieve cache hit rate of around 80%. So that means we don't have to do 80% of our hardware accesses. And these translate, again, these are just some numbers for reference. It's going to depend from device to device, around 450 milliseconds of blackout time. And what is the current status? An RFC has been posted. There are some gaps there. The most important one is I said it's easy, read, write, but map bus can be a bit harder to handle. There are some ideas how we could handle that, but I don't have a very concrete solution right now. Also, this current version that is posted RFC doesn't use this Luo. Thanks, Passat, for merging it last week. But the new RFC is gonna have a proper integration with Luo. And I would really like to integrate with what you're doing, Chris. So also make it part of your freeze PCI for life update to actually persist the cache there. But the main question I wanted to discuss here today is like, is it even sane? Is this something that we would actually want to do? Like introduce the custom configuration space accesses? Any opinions?
Hi, Vittori. Do you have some data about where the majority of those access come from? Are they coming from the PCI core during probing? Are they coming from drivers? Where the majority of them?
Yes, so most of them, like when you are setting up the device, you are initializing the capabilities. This is like a very big hot point. And the other big hot point, but again, this is not 100% for kernel, but it's more like specific to the VMM case and the hypervisor case, come a lot like on creating this shadow config space register for VMMs. But I don't want to like, this is a user space thing. Like, I don't want to.
I can add in the kernel space as well, when the kernel initialize the capacities and then they only, the code will look for, oh, I look for these capacities, and then they will scan the whole space for that, and then it stop.
Yeah.
And the next capacity will scan again to find the one that it want, and then the kernel was also doing a lot of redundant over and over read the access the config space as well.
If this is your biggest hit, then it might be simpler and easier and faster to just have a cache of the capability list. But there's always a worry because config space has all those interesting side effects, right? So there's always a worry we miss something or we get something wrong here. But yeah, I mean, it's yet another mechanism that all do the same thing. We have the old device tree stuff. We have that. There is this other one that all try to do this kind of competing and similar things on PCI in different ways.
I could argue it's sort of the same, but not really the same. Plus, yes, plus one more thing is that if you take a very good look at currently the struct PCI dev, what it is like sort of an anarchist way of caching some things, but not really caching things. Like it's so like what we are trying to propose here is like formalize that and generalize that a bit, not like try to cache just only this value because I don't know, like when we added advanced error reporting, we said, okay, let's also like store in PCI dev like the one value out of this.
I'll just give one example of a strange thing that happens in VFIO is that devices can be backdoor reset by the driver. And so like when we see that it's writing the memory command bit, when we think it's already set, we go check the bars and we'll restore them. So this is something that could get in the way of that. So just keep those sorts of things in mind.
Yes. So this is where we're very selective in what we are caching.
Maybe I'm mistaken, but as far as I remember, you can write from user space to this PCI config space as well. How will you handle your cache mechanism?
So here is the interesting thing. If you do it through map bus, and then you access through that, then it becomes interesting. I don't have a very good solution right now. But if it's just like a generic write that you're doing, this will propagate to like actually calling the write, the ops write, which will go to the device, straight to the device, and invalidate the cache.
From what I know, we do it from map for debug purposes.
This is where I said like it starts to become a bit more interesting for map. Like the safest approach, and we probably could start with that, is like if you use map, just bypass the cache. But again, it's a bit of one of the things that I want to finalize.
And how will you decide which region is cacheable, which region is not cacheable?
So currently, most of the regions are, not all of the regions are inferred from the PCI spec. So if you are really careful, you can infer what I can cache and what I can't. Like some, for example, registers are status registers that are expected to be changed from the device. You can't cache them. Some others are like you could cache under certain conditions.
Okay.
Ben, did you wanted to say something?
I was wondering whether it was worthwhile comparing this to a simple mechanism that just reads and builds a static list of all the capability offsets. and how much that gives you compared to this. Because, I mean, it's great, but it carries a significant amount of risk around all the crazy things devices do, such as what you mentioned, or side effects or whatnot. So if you can get 90% of the benefit by just having memory of the capability list structure, which is reasonably guaranteed to be fairly stable, you might be taking less chances there.
But one example of something that costs a lot of time, especially in live update, is that VFIO takes a whole copy of the config space into its own memory, right? And that's actually the biggest offender we have, as far as I know, because it actually happens twice on every KX stack, because once like the PCI core was doing it, and then the VFIO was doing it again. So this is not gonna be about like, oh, I'm enumerating I'm just walking the list, right, of capabilities. This is really somebody wants to take a full snapshot, and just preserving the snapshot makes the most sense. Now, do you want to preserve the snapshot in VFIO, or do you want to preserve the snapshot in a generic fashion? Well, this kind of fits into PCI, really. Like, if you have a caching mechanism, may as well just have one instead of two.
Like core itself already have a crappy mechanism to save the part of the config space, which kind of sucks for suspend resume. So there is definitely ways to plumb into that. I've been in PCR land long enough to understand that the kind of crazy things devices do. And so I suspect I'm going to end up with a few quirks here for specific devices, but fair enough.
Have any other question from chat? No. No. Then, if no other questions, thank you all very much, and wait for the new RFC.
Hello, everyone. So my name is Brian Vasquez, and I work for the kernel network team at Google. And I'll be talking about like IDPF live update support. IDPF is a networking driver. So I'll give like a quick introduction, explain very briefly like what is the IDPF driver and what it implies in the context of live update. So, I mean, what is live update? I think that I don't need to go over this right at this point. But why is live update for network drivers, or why do we want it? Yeah, network I/O is critical for VM workloads. It traditionally causes like network downtime. And yeah, the idea is that we want to basically quickly restore network connectivity. And in the picture here, I'm just quickly displaying like the bottom part will be the network device, and the dark gray is the IDPF PF that will have the IDPF driver, and the other are BFs that eventually are devices that are passed through to the VM. So what is the IDPF driver? It's literally like what it means is infrastructure data plane function. It's a modern driver. It's Intel. I'm linking there like the Linux implementation and the spec, but the key characteristics is that it does support SRIOV. It supports also like many virtual functions. It does this virt channel interface to talk to the firmware that is basically similar to dedicated hardware queues. And yeah, basically it is allows you a lot of offload features that might be not super relevant for this talk, but my point is that IDPF is complex, and because of that, it's a good case of study. So what do we need to restore, or what do we need to save on an IDPF driver, or like in a networking driver? And if we look at it, there's a lot of state that we need to preserve. We need to preserve registers or config status about the device. We also need to preserve like the queue descriptors or like the mappings to the memory, and also configurations that were done to steer traffic. We need to store like interrupts, and yeah, and a bunch of state. But if we go back to the use case where basically the objective here is to update the host kernel without affecting the VM, then the question becomes like, do we need all of this to preserve? Do we need to save all of this for the PF? The PF lives in the host kernel, and the answer is no. Like, we actually are updating the host kernel, so we don't need it. So what do we really need is keep the communication to the firmware intact, so that reduces the complexity to only really restore the position of the pointers of the head of tail of the descriptor ring that we are using to communicate to firmware. So we basically don't disturb the VFs. Like, the goal here is not to hard reset them, so we pretend that we are not destroying the device, and it's more like we are just updating the resources. And so after this, like, what makes it easy is because IDPF, regarding the VFs, it only does the management, so it only creates and destroys them. So that being said, basically our job is to prevent the destruction and making sure that we are ready to, or that we know like how many resources we had on when we come back. And yeah, this is how more or less the code looks like when we do this, which is basically code to making sure that we restore the descriptors position of the ring, and also that we are avoiding at all cost possible the hardware reset. But yeah, live update isn't just like a driver problem, right? Like, it requires like other subsystems to another kernel core components. So yeah, like for drivers or devices, like, we rely heavily on PCI subsystem. Some of the challenges here is that the PCI is the one that is doing the heavy work for the driver. Like, they are the ones that are saving the config space and the ones that are preserving that information and allowing the accesses or not. So one of the challenges that we are facing is that basically we want the PCI layer to be more flexible for drivers. And yeah, and the way it works for live update is that the PCI subsystem basically records to Luo, and then the PCI layer will be the one forwarding the callbacks to the drivers, so drivers can prepare or save the state. But yeah, this is part of the Luo. And then, yeah, the discussion that I wanted to have here is, again, like, for drivers, we relied heavily on other subsystems. So right now, like, for PCI, like, it requires the device to preserve everything, but basically all the hardware or all the devices are different.
Why did you write that you have to preserve like MSIX when we just had like 2 presentations ago? We sort of said we're going to turn MSIX off and not preserve it.
Well, I mean, it's just for completeness to say that you can't preserve all the capabilities or like all the features. But yeah, I agree that MSIX is not longer there. But
you mean the objects that are linked to these MSIX, the AQs,
yeah,
driver
so,
objects?
I mean, you need.
But I want to go back to the ring buffer of the PF. I don't understand why do you need to preserve it, because it's not serving anything for the VFs. And the VF ring buffer itself resides inside the VF VM, which you don't need to preserve anyway.
This is the descriptor ring of the beer channel, which is the communication channel to firmware. And the only reason we need to preserve this, and this is like a quirk of the device that we are working with, is that we cannot reset the PF because it will, on the background, kill the VFs. So
So if you kill this and reset it, the VFs are gone?
exactly. Yeah, and this is like how the device works.
Yeah, I know how IDPF works. Okay, weird. Yeah.
Yeah, so
Like
yeah,
the Nectix 3.
Yeah, this is weird. So
I would maybe just pause there and opine slightly that I know that other devices have gone and changed their programming models to accommodate live updates so that it works better. Just throwing that out there.
yeah. That's I mean, the idea here is basically to go over like the complications right now and try to see what we can do better. And yeah, I guess that my PDF was already uploaded, so it was kind of hard like to remove MSIX. But yeah, like it's not only MSIX. Like if you look at the driver, like how much you preserve and how much PCI or other subsystem will configure or like will restore for you, in my opinion, should be negotiated. So
Why? Why would you not want to restore SROV? Like, how could you not restore SROV?
No. SROV, I agree, but other state. I mean, interrupts, we say that we...
And interrupts you don't. So what other states on your list? Power management? It should be powered up if you're doing KEXAC, I think. So what's left?
What's left? Yeah, I guess that, yeah, without MSIX, you might be right. So yeah, this might be not longer apply. Okay. Sounds good.
Well, you have to preserve the bits which actually enable SRV and which configure the PF such that it can control the VFs. I mean, especially that, not the IDPF, because that's the virtual function, but you only get this if you set the PF to create the virtual functions. And especially that when it's running on the ICE, the Intel 100 gig, right? And that is particularly nasty if you have to configure it. So you actually have to use the PF to drive functions on the VF. So that's a bit of a nasty beast there. I'm not sure whether you can just restore it independently.
Well, you have to, they all have the same, like VFO has the same issue. If you're using SROV, you have to keep the SROV enabled in hardware, in config space. You can't do anything with it.
Yeah.
Otherwise, you'll break everything.
Yeah.
So when you
correct.
come back into your new kernel, the PCI subsystem has a new discovery mode that it has to recognize that SROV has been left enabled. And then it has to sort of recreate all the VF drivers without going through the normal
going through the BF drivers. Yay, brilliant.
Like
Okay.
there's this huge, I haven't seen any patches to fix this, but clearly it's going to have to be fixed.
Yep.
And then the way SROV, but the way SROV works is that the PF driver is the one that was supposed to enable it. So you also have to defeat the enabling it's a mess. I don't know.
Yes, it is a mess, especially here, especially with these drivers, because there are drivers for which the SRV functions are standalone. You can use them as is, as normal devices.
Yeah.
And there are others where you have a close interconnect between the PF and the VFs. So i.e. you need the PFs to be able to do functions with the VFs, which is completely nasty programming model.
Yes. And what I've told many people in many contexts is if you're doing this live update stuff and you have that kind of scenario where your PF has to be involved, strongly recommend you implement it in user space and VFIO, and then rely on the VFIO preservation and treat your user space like a VMM.
Yep.
And you'll have something that's robust. If you have to do what you're doing in the kernel here, good luck.
Exactly.
Yeah, and yeah, basically the other topic was on those lines. We're basically sure like the PCI preserves the VFs, but at the moment we were still relying on like an external actor to enable the feature and just is to kick it in. And yeah, basically what we are doing is like we are still relying on user space to explicitly enable the number of VFs, but just to trigger the functions. But yeah, like again, like it's like I'm asking for feedback or like how can we make this, because also running this function inside the driver with restoring the right number of VFs like seems also like maybe not the right path. Yeah, and some open question is what are we doing with error handling and if save restore fails in this specific case of the device. Basically, if we fail, we want to actually reset the hardware and making sure that the hardware like cleans all the internal state that it has. So I mean, this might be like device specific, but
Which error are you talking about? Like an error suspending or preserving?
like assume that the kernel that is taking over, like
Oh, if we've sort of had the position, if the kernel that takes over has some sort of bizarre issue, you're basically screwed.
right, but that's my point. Like if a driver already restores certain or like
I
assume
mean, you're
that,
basically screwed as in you call panic.
yeah, but okay.
So it doesn't matter what you do.
Yeah, I guess that my point is like I want to make sure that if it's screw, like at the very least, like I just touch the register to reset the internal state.
Well, but why, right? You're panicking your kernel. Why would you reset your device?
You will have to clean up all the structure that you preserved with the KHO previously. You can't just reset the device and hope everything will work.
Yeah, I mean, because I guess my point is that I don't know, like if something fails, like maybe it doesn't direct into a panic because it might fail in different areas. So
I mean, it doesn't matter about other areas. It's did your device successfully restore itself? Yes or no? If it successfully restored itself, then it's operating normally and it doesn't need a reset. If it couldn't restore itself, then it's operating during the blackout period. Like if it was never even attempted to restore, it's operating like in the blackout period, and you're going to get a panic.
okay, so basically it's kind of like if I restore correctly and someone else messes up, it's someone else's problem.
You should be a properly working device, and if you get hot removed, you should clean up everything in a normal, ordinary way. So you don't need to worry about that. And if you never got restored, then you're running in the blackout period, and you're relying on all your preserved memory, which is still preserved. So you don't need to worry about that either. The only case is if you've partially restored some of your device and you get stuck and you can't get it all the way done, maybe you'd reset then, but you probably just panic because you're in the weeds.
Yeah, I want to double down on that. Like, you have a chance of having the corruption propagate if you continue. I think it's much better you just panic rather than like get the bad data hit the disk.
Couldn't you just use EHA and PCI error handling here? I know that there is only, I think, 1 or 2 drivers actually implemented, but EEH, that's that thing, yes. So it's not error handling.
No, he's talking about you're talking about PCI error handling.
Yeah.
He's talking about I couldn't deserialize my preserved state for some reason.
Yes, that means that the device is not functioning, and as it's
No, it means the device is functioning. It means that the kernel software couldn't fix itself and start working again. Subtle distinction, right? Yeah.
So you're screwed.
Yeah. So you've got a device running in the background doing DMA to a bunch of memory that the previous kernel set aside, and your new kernel couldn't figure out what the previous kernel had done, and now what do you do?
Yeah,
you're dead. Yeah, you're not. You can't keep going. Well, yeah.
Yeah, sure, you always do.
Right. Yeah, and the next open question, I think that is already answered, or at least from my point of view, is that the standardization efforts in drivers, like, I don't think so. Like, it seems that this problem is so specific and it requires like deep involvement into the device that you are trying to save. For example, in my case, I needed to save like these 2 registers because that's the device. And that's where it is. So I don't think that that's possible. But in that case, I guess that we should try to provide a lot of documentation on the other subsystem that the driver consumes, because I think that as a driver developer, like it requires also to know a lot of things that like are constantly changing. Yeah, that's it.
Thanks.
Hi, everyone. So actually, this is a continuous of my colleague Brian here. We're going to talk how we solved all the issues he was discussing by simply avoiding them. So my name is Saeed from NVIDIA. Aditya here with me. We worked on the KExec live update for the Connectix device driver. And so we'll start here with a recap on what a generic cloud architecture looks like. I'm pretty sure most of you are aware. You have your cloud hypervisor running your device drivers with some management software on top to serve few tenant VMs that do some workload. And the plan here, should click. So the plan is and requirement is to preserve the state of these VMs while they're running their workload and be able to do upgrades on your hypervisor kernel and your management stack, whether it was an SDN stack or GPU stack on the hypervisor, while the VMs keep running without noticing or being aware of any upgrades or live updates happening in the background. Naive solution, which Brian tried to do, is basically add full support to your kernel driver with KHO serialize, deserialize on every object, every stack. And for example, in MLX5, it's like we have 10 stacks. I don't know if I could count. We have the NetDev, RDMA, VDPA, Virtio, you name it. All these stacks needs to be preserved in a KHO live update manner for the VFs to continue running, which is too complex, as Brian said, and almost impossible to do in a short time. Yeah, as we said, a lot of stacks, a lot of objects to preserve and make sure they work. Also, the error handling is mostly impossible to do. So it's cumbersome. And we came up with this creative solution where we avoided doing that by creating a simple VFIO user space program that all it's doing is serving these VMs or tenant VFs requests to the device, to the underlying device, by preserving the state in a user space program while offloading all the live update mechanism through the underlying VFIO PCI driver, which should support live update. And we would offload all of the SDN management software into a VM, separate VM, through a separate physical function. And that physical function would also reside inside a VM, which can simply be preserved also through the VFIO PCI and as well as a tenant VM. So all you need here with this special deployment is preserve 2 VMs and this small VFIO PCI MLX5 user space driver, and you could hit KExec and everything which should be preserved without the need to re-implement MLX5 from scratch to support KHO and state preservation. I'll pass the mic to Aditya here. He will jump into details and explain how we did it.
Yeah, so I'll start off with the user space program we have. There we go. So it's, like Saeed just mentioned, it's a VFIO PCI user space process that just drives the PF. It is managing memory for the VFs that we've created. We can point it to a memfd file descriptor or somewhere where we can store memory that we can unpack after a KExec, and it's aware of that process for suspend resume. On the next slide, we show just a quick sample application we built where it shows the output the exact command line that you can run. Here we have the SDN running in a VM. So as you can see, we have it popped up right there. During enablement, the user space program will create that VF. This SDN on the offload enablement can look at that VF, manage it, and there's no state stored here. So we boot from one VM, discover the VF, and then it'll attach the pipeline, and the eSwitch pipeline runs that way. Since it's in a VM, we also have a nice property where if we want to update the SDN itself, if we want to update that entire software stack, we can just start one in parallel, have it updated, and then once ready, we can activate the new one. This is with a devlink UAPI change that was submitted as well. During that switch itself, the tenant won't notice any downtime. And a nice added property of this is this can also be done outside of a kexec to update the SDN. This way, you can also now, during the kexec update or afterwards, just do this at some other time as well. I know we're running a little close on time, but the last slide is just the links, the patches that we've submitted upstream, and then the library and sample application as well.
So questions, comments?
One thing I'm actually curious about, two things, but first one is, my understanding is that typically for PF-VF relationships, you basically have the PF driver that goes in, effectively propagates the VFs, and then needs to even tell the kernel to enumerate them. How does all of that happen when you're running VFIO PCI as the PF?
VFI PCI can manage SRV by itself.
Can manage the PF portion of it? Oh, nice. Okay, I didn't know.
Yeah, that's a cheat we did. So.
A good cheat. I like it.
Yeah.
And then I suppose, like you mentioned, you're using MemFD to pass it on. How do you update that user space program? You mentioned that for the SDN, you can just basically create a second and flip over. But
you don't update that. That's the piece that you preserve. Yeah, it supports update. So it's a library basically. It's not a user space process. So your management software, your virtualization management software, orchestrates that library, and it has suspend resume properties. So it is suspend resume aware, technically live update aware.
Including actual update, like I use a new version and it can go from one version to the next.
It can be done, yes.
Okay. I mean, the whole thing to me, like the very first, like my very first sentiment when I saw this was, this is a really good way to avoid the GPL. Has this taste to it, right? Like
yeah. It's
basically
creative,
trying to make sure you don't have to go and put code into Linux. There are some nice properties to it. I just don't know if this is really the best way for everybody around.
That wasn't the motivation, right? The motivation was to use VFIOs
to simplify the stack.
To simplify the
so
whole
is that library fully open?
We can make it open. It's open source. Yeah. It's not open in terms of it's not available, but yeah, it's open source.
I think it would be good to at least fend off that sentiment that it's really there to avoid licensing issues.
Yeah. We'll can work it out.
So from my understanding here is that for the VF there or PF there, the main idea is that you're using the user space VFO driver and then using the piece data, process data there to perceive the state, right?
Yeah, it's the user space process.
So yeah, then my main question is like, how do you do that in the kexec process?
The user of the caller of the library, your virtualization management software needs to make sure that the library takes a special memory, preserved memory area, and we use that for all our DMA space. So that DMA space is preserved throughout the kexec.
Okay, thank you.
Can we go back to the slides where you have the command line parameters? Oh, this the memory size. That's the where you save the state, right? That the memory.
Yeah, this is just a sample application. It orchestrates the library, but yeah, the memory is, in this example, it's a memory allocated through VFIO, mapped through VFIO, allocated through like a normal user space allocation. But in actual KExec use case, you would take it from a preserved area in the kernel.
Okay, good. Thank you.
In the, yeah. I think that's it. Thanks, everyone.
All right. Thank you, everyone, for attending. This is the end for this micro conference, and we have an evening event right today. So see you there.
See you next year.
And see you next year.